Kanchan,
Well,
this is Professor Barry Arnold. You must know him.
Yeah, I know him,
Yes.
Professor Arnold.
He might be visiting India.
Good.
Possibly during the winter season.
He delivered a talk for us,
Yeah, let's see.
Professor Arnold.
Yeah.
I requested
I,
him and he agreed to that. That was really kind of him. So,
Yeah, he'll be at Delhi.
I never turned down an invitation.
We'll discuss about it. Barry will be here in India, hopefully, maybe for some time, for a few visits here and there. But you have to see that, he is traveling at, in spite of his age, he doesn't look old at all, but he's still, you have to get to our usual age that is there. But anyway, he'll be here hopefully and he'll be talking.
Yeah. I try to pretend that I'm not that old.
That's what I'm saying. You're not that old. Yeah.
Yeah. Say that Donald Fraser had lost his birth certificate and didn't know how old he was, and I'm going to try to follow the same theory.
I see. Okay.
people are joining.
Yeah. Somesh is here. Teacher Rao is here. Hi, Somesh. Good morning.
Good morning. Good morning.
Good morning.
Good morning to you all.
Yeah, good morning.
Good morning.
Yogen is here. So, Barry, there is no more corona, right? In US, and at least in California, no COVID anymore.
Is what anymore?
COVID or corona?
Oh no, I think it's done. I hope.
I hope, yeah.
No, everybody's acting as if it's over with. So, and
that's good.
And I haven't seen very few people wearing masks. We're doing good, I think.
Okay.
So I hope it's good in India too.
That's a similar situation in India.
Yeah, good.
Japan, they are taking the 7th or 6th, I think, the dose. Timothy wrote to me that he and his wife had to go and take maybe the 5th or 6th dose for the corona. They were still having off and on.
Mm-hmm.
In US, everyone has taken the 4th dose, I think.
Satish is here. Okay. Hi, Satish, good morning.
Good morning, Professor. Good morning, classes.
Good
morning to you all.
Yeah, good morning.
Devendra has joined. So Devendra is here.
Good morning, sir. Okay, I think let us start the program, inaugural function, because now it's 9 time. Others will join in the meantime. I hope Shubha is here in the group.
Yes, sir. Yes, sir. Good morning.
Okay, please let us initiate the inaugural function.
Thank you. Thank you. So, dear, good morning, good afternoon, and good evening, dear professors and esteemed participants. Welcome you all to the 8th International Webinar on Recent Trends in Statistical Theory and Applications 2023. We are having a star-studded gathering with many prominent members of the statistical fraternity with us today. First of all, we would like to thank you all from the depth of our hearts for being a part of our journey towards academic excellence. Let us begin the inaugural session. Before starting the official functions, I would like to request you all to please remain silent for a minute in gratitude to the Almighty. Thank you all. First of all, I would like to welcome Professor Satish Kumar sir Professor, Department of Statistics, Director, School of Physical and Mathematical Sciences, University of Kerala, and Chairman, WSTA 2023, to formally welcome the gathering. Professor Satish Kumar sir is actually the single person behind these academic successes of our department. A person with solid vision, untiring energy, and persistence. We are lucky to have you, sir, on the helm of our affairs. I would like to welcome you, sir, once again to formally welcome the gathering. Thank you.
Very warm good morning, good afternoon, and good evening to all professors and distinguished faculties and delegates from various parts of the world. And happy National Stats Day. We are in the inaugural function of the 8th international webinar on recent trends in statistical theory and applications 2023. We shortly WSTA 2023. In conjunction with the 5th annual convention of the Statistics Fraternity Kerala. This event is organized by the Department
Satish sir? I think sir's video got stuck. Satish, yeah.
I hope you can hear me. There is a network issue, I think so.
Yeah, now it is okay, sir.
Okay. This event is organized by the Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala, in association with the Indian Society for Probability and Statistics and Kerala Statistical Association. I find this day very auspicious as several stalwarts in the area of statistics and statistical sciences from all over the world join together in the coming 4 days to interact with us in this virtual platform. Eminent statisticians like our Professor Barry C. Arnold, distinguished emeritus distinguished professor of University of California, USA. Professor B.L.S. Prakash Rao, former director of Indian Statistical Institute. For Professor Vijay Nair, former director, International Statistical Institute. Professor Ashish Sengupta, August University, and professor from our Indian Statistical Institute and several organizations and associated. And Professor Kachashvili from Georgian Technical University. Professor Thomas Matthew from University of Maryland, distinguished professor from the University of Maryland, Baltimore, USA, country. Professor Bimal Sinha, Professor T.J. Rao of Indian Statistical Institute, and C.R. Rao, Advanced Institute of Mathematics, Statistics, and Computer Science. Professor Malay Ghosh, University of Florida. Professor David Banks, University of Duke University, USA. Professor Michael Evans, University of Toronto. Professor Peter Lohamander, Sweden. Professor Carlos Coelho from Nova University, Portugal. Professor Gauri Datta from University of Georgia. Professor Ghulam Kibriya, Professor Indranil Ghosh from University of North Carolina. Professor Lynn Ohio from Ohio State University, from Lynn. Professor Sumitra Datta from University of Florida. Professor Chatterjee from Minnesota. Professor Jaya from Rutgers. Professor Debasis Kundu from IIT Kanpur. Professor Somesh Kumar from IIT Kharagpur. Professor Gede from University of Dodoma. And there are several well-known scientists in the area of statistics and related fields are there in this group. Sorry for not mentioning all the names of in this occasion. More than 18 plenary talks and more than 8 invited talks, including special invited talks of top-class scientists in the area are scheduled in this mega virtual event. All these details are available in the website of the conference. Those who are interested can please visit our website for further details. In this occasion, several honoring sessions are also scheduled in order to honor well-known statisticians of our country, in particular, Professor P.C. Mahalnobis, Professor C. R. Rao, Professor S.N. Roy, Professor D. Basu, Professor U.S. Nair, Professor K.C.S. Pillai, Professor K.R. Nair, Professor M. Mathai, Professor J.K. Ghosh, Professor P.V. Sugatmi, Professor R. Krishna Pillai, Professor Eliamma Matthew. We hope deliberations of this conference will enlighten the statistics fraternity to work together and generate new knowledge, which are essentially for our society. The statistics community, in short, is vested with the responsibility of working hard to rise up to the requirements and expectations of human society. As part of the, now it is okay, isn't it? Can you hear me? As a part of the conference, yesterday we have conducted a national level online quiz competition at two levels, UG and PG level, undergraduate and postgraduate level, in honor of our great legend, Professor P.C. Mahalnobis. We hope to announce the results of this competition during the valedictory function of this event on 2nd July evening. Today, we have Professor Ashish Gupta with us to inaugurate this international conference. I utilize this occasion to welcome you to this auspicious function.
Thank you.
Professor Kalyanaraman sir and Professor Yagin Thomas sir are also with us to extend felicitations. I utilize this occasion to welcome Professor Kalyanaraman sir and Yagin Thomas sir, our professors, to this function. Also, I utilize this occasion to welcome each one of you, in particular my colleagues and students, to this occasion. Please note that the certificates of the conference, those who have attended, will be uploaded in the website as we did in the earlier times. Any updates with regard to the conference will be displayed in the website. In fact, there are several other professors also there in the group. I hope that Professor Bala also joined with us in this inaugural function. I hope.
He's there.
Yeah, Professor. Okay, welcome, Professor Bala, to this, to your support and blessings for your support. We are always grateful to you, Professor. And thanking each one of you for your sincere cooperation, support, and blessings, without which these types won't be successful. Once again, extending my deep sense of gratitude to each one of you, I remind. Thank you all. Thank you.
Thank you, Professor Satish Kumar sir. Now it's time for the official inauguration of our webinar. We are actually blessed to have Professor Ashish Sen Gupta sir with us as the inaugurant of the function. Actually, Professor Ashish Sen Gupta does not need any official introduction to the statistical fraternity, but we can't help say a few words about his excellent achievements in the area of statistical research. A CSIR Emeritus Scientist, Government of India, Professor Ashish Sen Gupta is currently the advisor and consultant of Arizona State University and the Indian Statistical Institute, Kolkata, an adjunct professor in the Department of Population Health Sciences, Medical College of Georgia, and a distinguished professor in the Department of Statistics, Middle East Technical University, Turkey. He has also rendered his service as editor of many prominent statistical journals. He's a member of the Project Advisory Commission, DST, Government of India, a fellow of Indian Statistics and Indian Society for Probability and Statistics, a fellow of the National Academy of Sciences, and a fellow of the American Statistical Association, as well as an elected member of the International Statistical Institute, Netherlands. We're extremely privileged to have you with us and actually to have your continuous support to all the programs arranged by the university, and we are privileged to have you to inaugurate today's webinar, sir. I request you to please inaugurate the session and speak a few words. Thank you, sir.
Thank you very much, Dr. Nair, for your kind introduction. So let me try to share the screen. Can you see the screen?
Yes, sir.
You can. Okay. So I'm going to now make it a full screen.
Yes, sir.
Okay.
Yes, it's
Is
visible.
it there?
Yes, sir, it's visible.
Okay. Thank you. So I think I have about 10 minutes for this inaugural talk. First of all, a good morning to all of you and a warm morning to many of us in India. A good warm morning. I would like to thank Professor Satish Kumar, our Indian Society for Probity and Statistics ISPS, and the Kerala Statistical Association KSA for giving me this opportunity to give this inaugural address. So I'll start very briefly by giving you an introduction to Professor P.C. Mahanabis. It's impossible to cover his achievements in a talk like this. But since today happens to be the birthday, 130th birthday of Professor Mahanabis, it's an auspicious occasion for us, for Indian statisticians, and also a notable occasion for statistics and statisticians worldwide. I'd like to say a few words about Professor Mahanabis. So he was actually the OBE, the Order of the British Empire. He was awarded with that, FNA, FSC, FRS. He lived almost 80 years, one day short of his 80th birthday. And he was a physicist by training, a statistician by passion, by intuition, to which area he was introduced in 1915 while he was in England. And then after coming back, he also got into the government and became a planner and economist, I'd say by conviction and by appeal. He has a unique blend of theoretical and applied statistics at the highest level, which definitely had contributed to his fame and his widespread achievements in various areas beyond statistics. He is hailed as the father of Indian statistics, being a founder of Indian Statistical Institute, and also instrumental in finding NSSO, the National Statistical Survey Organization, and CSO, the Central Statistical Organization, which are doing quite well, the last two, in fact. He has been described as the plan man, the architect, an economic planner, being the member of the first planning commission in India. And he was instrumental in carving out the second-year five-year plan, and it goes by the Mahanabis plan. Statistics help grow the economy. That's what has been mentioned about the contribution of Indian statistics in the world arena, as I'll show you a little later. And definitely the road had been paved and led by Professor Mahanabis in this area. I also think of him as an Indian ambassador of statistics. And the reason is he has been propagating statistics to various different countries, both in terms of theory and applications. Let me move on to the next slide. So you see in the 213 International Year of Statistics, this map was produced by the ISI. And here in India, the contribution of India was mentioned to be as the one I talked about earlier, the growth of the country in terms of economy. And that's where Mahanabish glittered through and led us through in the development of the economic planning of India. He had lots of other surveys, and these surveys at that time, given the restrictions, the constraints, the hazards, difficulties, he was a trailblazer. He did overcome all those to the extent that the Nobel Prize winning economist Angus Deaton and co-author Valerie Kozel wrote in 2005, where Mahanabish and India led, the rest of the world has followed. So that today most countries have a recent household income of expenditure survey. Most countries can only envy India in its statistical capacity. This is, of course, in 2005, okay? But it's still a tribute to Professor Mahanabish. Here is one reason more that I'd like to share with you. This particular photograph was taken from the organization in China, Beijing, where I visited several years back. And in this photograph, you can see Professor Mahanabish and Mrs. Mahanabish. Together with them is, many of you remember, is the very well-known Premier Zhou Enlai, the Premier of the People's Republic of China. Okay, so his fame and name had extended well beyond even to attract the premiers of different countries for his visit, during his visit there. So this is the photograph. And of course, I'm sorry, I don't know Chinese, but my good friend, Professor Ong from Malaysia, helped me to translate this. And the caption goes, International Exchange and Cooperation. This was the very first international exchange post-founding of the People's Republic of China. And in that, Premier Zhou Enlai meets visiting delegation from Indian Statistical Institute with Professor Mahanabish and wife, fifth from left. So I was so proud, so pleased, and so impressed to see this photograph. This is kept in their exhibition hall in the center. I took the picture and brought it, and I hope that there will be occasion like today to share this picture with all of our friends and colleagues in statistics. Now the sample surveys, that's one of his major areas of contribution. And the fascinating part is his knowledge, his awareness towards the requirement of the accuracy or the challenge towards the veracity. His contribution of subsample of half sample to estimate the variance has been one of the major contributions in large-scale surveys. And it also shows that what is the statistics without an estimate of the error. And this is something that is also needed in the current scenario of the Indian surveys going on, and obviously in the worldwide survey. Mahanabish D-squared is one of his theoretical contributions. All of you know about it, but for the young generation, it's easy, maybe it's well known, how to measure distance between 2 points, be it in the Euclidean or non-Euclidean manifold. But it is not so obvious, at least in those days, to find out how to measure a distance between a point and a group of points, or between a point and a distribution. This is where Mahanabish's ingenuity came in, and he developed the measure, which is based on using the location as also as the scale matrix for a multidimensional point from a distribution. This particular measure became widely popular, has transcended the decades in statistics to even the current generations in terms of the big data analysis, where you find in statistical machine learning its impact and we rediscover its applications in our big data analysis. National Statistics Day, 29 June, has been declared by the Government of India and to felicitate, to commemorate the birthday of this incredible human being. And the theme of this year is the alignment of state indicator framework with national indicator framework for monitoring sustainable development goals. But towards this end, it is here worthwhile to recall what Harold Hotelling had mentioned. No technique of random sample has, so far as I can find, been developed in the United States or elsewhere which can compare in accuracy with that described by Professor Mahanabis. With the given national theme, this is a very relevant aspect, and in the footsteps of Mahanabis, we look towards the challenge of meeting this, compromising this, consolidating this, the aim of having the alignment of these two national indicators and our state indicators, keeping in mind the checking of the veracity, implementation of the accuracy, and declaration of the accountability on both the government, state, and national government's part. Unfortunately, ISI is a fall from grace, as we know. That's from statistical glory. Not much of this kind of surveys have been going on. I don't want to go into the reason, but we need a statistical leader to bring us back his glory in the path given by our Professor Mahanabis. Two incredible marks in the international statistical arena by our Indian statistics in 2023. The Indian American C.R. Rao was conferred the prestigious international prize, Nobel Prize in Statistics, and India's re-entry in the global official statistics by being elected to the United Nations Statistical Commission. I mention these because in this conference, we are covering a wide variety, and we will have occasions to visit some of these accomplishes and also the areas that are being covered in these two different, yet the two achievements of the statisticians. The WSTA seminar is showcasing several of the brilliant minds in today's statistical era, both from India and abroad, with lectures covering a wide and rich spectrum in statistical science. We're looking forward to an academic enrichment of a very high degree in both theoretical advancements as well as emerging applications of statistical science. So I'd like to remark that by following what Professor Mahanabis had said, statistics is the universal tool of inductive inference, research in natural and social sciences, and technological applications. Statistics, therefore, must always have purpose, either in the pursuit of knowledge or in promotion of human welfare. And I think nowadays it applies for both. The final one, the efforts put in by Professor Satish Kumar and his invaluable team members are beyond words of commendations. I hope this webinar will inculcate in the budding statisticians the urgently needed conviction to carry forward with reclaimed glory the torch of statistical science that Professor had so meticulously lit decades ago. I wish WSTA a gala success. Thank you very much for your patience. Thank you.
Thank you so much, sir, for your wishes, for your wonderful words and apt look into the life of dear Professor Mahanabis. Professor Kalyanaraman sir and Professor Yagin sir are with us to felicitate the function. Actually, the presence of these two great personalities have been the the blessing that we have always sought. Their words have always been a motivation. Their paths were are followed by us in every endeavor that we have taken up. And now I request Professor Kalyanaraman sir to please bless this webinar by his words. Kalyanaraman sir.
Yes. Thank you, Shiva. Greetings to all. Wish you all a happy National Statistics Day, which is being celebrated to remember the contributions of Professor P.C. Mahalanobis to the Indian statistical scenario. On this occasion, I take this opportunity to congratulate Dr. Satish Kumar for having been elected as a member of the International Statistical Institute. So, with this congratulation, we'll just go into the details of what is happening here. For quite some years, things are happening in a very, very bright manner as far as the Department of Statistics, University of Kerala is concerned. And I only appreciate the work done by the team, which started in a very small way and has reached a level of world congregation as far as this webinar is concerned. I hope this being taken to its logical continuation and meet very high standards of conference evaluation. And I really congratulate and happy to be part of this seminar in a way that is possible for me at this age. And all that I can do as one of the elder member of the faculty to bless you all with the Rig Shatamanam Bhavati Shadayush Purushendriye Sharendriye Ayushvendriye Pratitishthati. Thank you for this. Happy going, and let it go with all happiness. Yes, thank you.
Thank you, dear Professor. Now I request Professor Yagin Thomas sir, former HOD Department of Statistics and Emeritus Professor UGC, to please bless the gathering.
Good morning to all of you. Eminent statistician
Yeah, Yagin sir.
There may be network issue.
Yeah, there is some network issue.
Recent trends in statistical theory and applications, 2023. You know, we are living in a society facing more and more acute problems of life. The next phase of green revolution has to be accomplished to feed the fastly growing population with a limited but shrinking cultivable land. The next phase of industrial revolution has to be accomplished to provide employment to the growing number of unemployed youths and for creation of enough wealth for the emerging society. With increased life expectancy, the population of old people is increasing. Emergence of new diseases like COVID-19 put medical scientists in stress. Necessity of crop insurance to protect farmers. Necessity of instituting new insurance policies to protect newly emerging businesses, etc. are all problems which require in-depth statistical study. Thus, we see that the problems of modern human society are much complex. As complexity becomes severe, attempts for solution to problems rely more and more with the statistical methodologies. The type of data that is being received today for analysis is much different from those made available in the previous time. We are constrained to change or modify the already available methods to deal with such complex data sets. With the fast developments in technology, more and more social problems emerge in the society. Also, reformed statistics-oriented strategic plans are to be evolved to drive the society in a forward direction. So it is high time that through the presently organized webinar, the delegates are destined to contribute a lot by inventing necessary statistical theories to solve the new challenges of human society. I congratulate the organizers for organizing such a webinar. May the delegates get enriched by new knowledges imparted through the talks and the presentations of the webinar. I wish you all once again with our ever best greetings. I conclude. Have a nice day.
Thank you, dear Professor. So now we have reached the end of the inaugural session. Actually, this also marks the beginning of the next technical session. So today, as we celebrate the 140th National birth anniversary of Professor Mihail Nobis, I would like to use this moment to express our gratitude to the esteemed gathering that we have today. Respected Professor Ashish Sen Gupta, Professor Satish Kumar, Chairman Wsta, Professor Kalyana Raman, Professor Yagin Thomas, and all the esteemed dignitaries present in the function. It is our duty to express our sincere gratitude to one and all of you for the continuous support and encouragement provided by you to all our endeavors. The Department of Statistics, University of Kerala, started this journey towards academic excellence through sharing of knowledge and technical expertise in and around the country, actually around the globe, by arranging international webinars, international conferences, and seminars under the HOD-ship of the then HOD, Professor Satish Kumar sir, in 2016. From day one, we were fortunate enough to get the continuous support and participation as well as encouragement from all the eminent personalities in statistics in and around the country. Today's audience too is a direct proof of that blessing which we have received over the past 8 years. Today, I take this opportunity to express our heartfelt gratitude to one and all of you for believing in us, for being a part of this journey, and for your continuous support and encouragement. On behalf of the department, of the organizers of Wsta, I would once again like to express our sincere gratitude, and we wish and hope for a continuous association with each and every one of you through the coming years to make our dream of international collaborations and continuous sharing of resources a truth. So thank you once again, and I request all of you to be present for the first technical session that will be starting within moments. So thank you once again to all, each and every one of you, for your presence. Thank you.
Thank you, teacher. Thank you. So now it is 9:35. Within 5 minutes, we can start the first technical session. Ms. Anjana? Anjana?
Yes, sir.
Yeah, yeah. Now I think just introduce the chair and then after invite the speaker. And
Sure, sir.
further proceedings we can go because 4 minutes left by the time we can, so that the time will not lapse for the keynote talk.
Sure, sir. Good day to all. It is with great pleasure and honor that I introduce and welcome our esteemed session chair for the first technical session of Wsta 2023. We have our emeritus Professor K. Kalyanaraman sir from the Department of Statistics, University of Kerala, chairing the session. Throughout his illustrious career of over 5 decades of professional experience in academics, research and consultancy, Kalyanaraman sir has made significant contributions to the field of theoretical and applied statistics. His expertise and research have been widely recognized and has had a profound impact on both the national and international academic audience alike. He is also an elected fellow of the Kerala Academy of Sciences, an unparalleled member of the WST 2023 Advisory Committee, and a true inspiration to all of us. So, without further ado, I humbly invite you, Professor, to chair the session. Over to you, sir.
Welcome, sir.
Thank you for providing this opportunity. I pay my respects to Professor Prakash Rao for having accepted to deliver the keynote address. And I am having this opportunity, perhaps maybe due to my age, and I was introduced to Professor Prakash Rao way back in somewhere around 1980. And Professor Newts was here in India for quite some days. Professor Newts did a lot of work in branching process. And Professor K.N. Venkatraman, who happened to be my professor at Madras University, asked me to join him for some work, and along with Professor Newts. At that time, he introduced me to the book by Basava and Prakash Rao on inferences on stochastic process. And there is a wonderful chapter on branching process. I think that it's around 20 pages. And from that, you can get a whole idea of Dalton-Watson process and what is that? Markov branching process. So that is the way I came into know of Professor Prakash Rao. From that day onwards, I have a lot of respect for him, and we are very eagerly waiting to hear his topic on what is called as mixed fractional Brownian motion and statistical inference. I hand over the mic to Professor B.L.S. Prakash Rao, requesting him to deliver the keynote address. Over to you, sir.
Well, thank you, Dr. Satish Kumar, for inviting me to this webinar. And I would like to thank Professor Kalyanaraman for his kind introduction. As all of you know, as Professor Kalyanaraman mentioned a few minutes ago, my work was mostly in inference for stochastic process for the last 44 years. So it's mostly advanced in probability. So my work falls on the boundary between probability and statistics. So in probability, mostly I use stochastic process, those techniques, and inference, of course, we all know estimation and things of that sort. I've been interested in this subject for several years now, as I told you just now. And it turned out this is playing a major role even in the recent times because of applications to biology, finance, and these areas where what are called, just like in analogy with differential equations in mathematical models, we have stochastic differential equations in statistical models. So for instance, an immediate application of some of these results was in the area of statistical finance. So there is a lot of work in what are called option pricing. So when you have a stock, when you want to purchase a stock, just like oil, which India imports from abroad, the oil fluctuates so much, share prices. So you can give what are called a strike price and then fix up an option cost for that and then buy the strike price. So they cannot sell for more than that. If you really want to use it, you have an option for that. So such things have been discussed in literature for the last few years. In fact, I was fortunate to introduce a course on statistics and finance for MSc students at University of Hyderabad a few years ago. So what I'm saying is, so the interest in these areas, especially internet traffic, internet traffic and the biological models, financial models, there is a great interest in using what are called diffusion models. So they started with Norbert Wiener several years ago as a Wiener process, they call it. And later on, it has been extended to what are called diffusion process. So that's how the first application was to diffusion process. So I'll just start my presentation.
Whether we need.
Yeah, I'm just trying. Just 1 minute, please.
Okay, please. Okay, please.
Well, as expected, I am not able to share.
Whether we present from here, please.
Yeah, maybe that is better.
Oh, okay, please. Okay.
Oh yeah, okay. Oh yeah, I got it. Yeah, you have projected it?
No, professor. No.
Yeah, can you see me? Can you see now?
No, not yet. There is some.
Hello?
Hello, yes, professor.
Yeah, I can.
Not visible?
Yeah, I can see that. Can you see?
No, professor. Not yet.
Not yet.
We shall try from here. That's better. It is not. Or otherwise, you can try once again, professor. Huh?
Pardon?
Whether we need to try from here now.
I can hear you. Yeah.
Okay, please.
Can you see my transparency?
Yeah, now it is. Yeah, now we are presenting from here, professor.
Now it is seen, sir. It is seen.
Oh, you can see that. Okay.
Yeah, you can see.
Yeah. So, there is this. I was talking to you a few minutes back. So the financial models. There is what called a Black-Scholes model. The economists Blocks and Scholes, they have introduced a Black-Scholes model for studying option prices in the stock market. So that was a model that has been used for several years. And then people found out that stock prices don't just depend on the immediate past, but in the long distance past also they depend. So in other words, if you look at the time series of stock prices, they form what's called a long-range dependent process. So the question is, how do you model a long-range dependent process?
Excuse me, Rose.
Yeah.
Whenever we next, so that he will move from here.
Can you see now?
Yeah, professor, it is.
Yes, it is seen. It is seen.
Excuse me.
You can see it.
Yeah. It is sharing from here, professor.
Yes, first slide.
So how to move from the?
Yes, I can change it. If you can see, I can change it from my side.
Professor?
Professor, next slide. First slide is seen. Next slide.
So,
Can you see the next one?
Yes, sir. Next, please show next one, sir.
excuse me, Professor. It is sharing from here. From Nikhil is
It is
sharing.
stuck on first slide.
Okay. Then I will say next slide, and that we can.
Yeah, next slide, please go, sir. Next slide.
Yeah, next slide, please.
Yes, sir. It is coming, sir. It is seen, sir.
Okay.
We can see.
So the question now is, so if the process is long range dependent, what is the alternative model that we can use? So one suggestion was you can use what's called a fractional Brownian motion. Brownian motion is sort of a Gaussian process. It's very well known. And now there's a notion called fractional Brownian motion, which I will talk about in a few minutes. But then you see there are some underlying assumptions in modeling financial markets, especially market behavior. One assumes it's rational in the sense that you will not have arbitrage opportunity. Arbitrage opportunity essentially means suppose you have an exchange between dollar and rupee. If the dollar and if $1 is 80 rupees in India, it should be equivalent to one in America. But if there is a difference between the rates, then that gives arbitrage opportunity for people who buy rupees or dollars in a large size. So one expects that if it's a rational market, there should be absence of arbitrage opportunity. So, however, when they found out if you want to use long range dependent series, a model like fractional Brownian motion, it creates arbitrage opportunities. There are arbitrage opportunities. So therefore, they thought this will not be useful. So statistical inference for a fractional diffusion process satisfying stochastic differential equations driven by a fractional Brownian motion has been studied earlier, and a comprehensive survey is given in a book by Mishura and myself later in 2010. Next slide, please. Third slide. It has been noticed that there might be long-range dependence in the behavior of movement of stock prices in a share market, and the log returns may possibly have heavy-tailed distributions. Next slide, please. It was suggested by some researchers that the driving force for modeling of prices of movement with long-range dependence may be modeled by stochastic differential equations driven by what's called a fractional Brownian motion of what is called Hurst index. So a fractional Brownian motion is a Gaussian process with mean zero with what is called a Hurst index. And Gaussian process, you know that means every finite dimensional distributions is multivariate normal, and it has some covariance function which is given later, which I have written as half of absolute t to the power 2h plus absolute s to the power 2h minus absolute t minus s to the power 2h. It is what is called a self-similar process. That means if you have a process xt, x of at, a is any constant, x of at is a to the power h x of t. That's how they have the same distribution. That's called self-similarity. So self-similarity means there is a sort of shift. So if you want to know the distribution of x of at, it is a to the power h x of t. So that they have the same, and it is not just one-dimensional, it's multi-dimensional distributions are like that. So it's called a self-similar process. So for instance, if h equal to half, fractional Brownian motion reduces to usual Brownian motion, or what is called a Wiener process. So it's a self-similar process with stationary increments and exhibits long-range dependence when h belongs to half 1. So even if the index h is a constant, for at least for our person right now, h is a constant, it is between half and 1. So if h equal to half, which is outside the range, then it's a Brownian motion. But if h is between half and 1, then this process exhibits long-range dependence. Long-range dependence can be defined in several ways, as I have intuitively explained a few minutes back. That means your present random variable depends on the several past variables. Or an alternate way of doing it is covariance between x0 and xt. If you sum that covariance, it's divergent. So that's a mathematical way of doing it. So next, please. So there is Buzorg, Hull, and Kuznetsov observed that the use of fractional Brownian motion as the driving force for modeling stock price movement is not justifiable, as it allows arbitrage opportunities, which is contrary to the fundamental ideas of rational market behavior. So even though fractional Brownian is good for modeling processes which are long-range dependent, but for using for financial markets, it turned out to be not that useful because it allows arbitrage opportunities. I have explained to you a few minutes back what I mean by arbitrage opportunities. So if the market is rational, there should not be arbitrage opportunity. And in fact, one way of saying it, there is no free lunch. You have to pay for it. So that is the idea. And this is the basic assumption in all financial statistics. So the fractional Brownian motion it is good for modeling long-range dependence, but it creates arbitrage opportunities. So this is not useful. And that's where the mixed fractional Brownian motion has come into the picture. I will explain to you in a minute. Next slide, please. In order to avoid this problem, Cheredito, he has introduced the use of mixed fractional Brownian motion as a suitable model to capture the fluctuations in stock price movement. So here, mixed fractional Brownian motion is, by its name itself, it's a mixture of a Brownian motion and a fractional Brownian motion. So that is the idea. So it's a mixture of the two. Now, what sort of mixture you take, it can be taken as long as it's not just reduces to Brownian motion or a fractional motion. Maybe it is a mixture where a constant is of any type which you like. So usually it is in the literature we work with the standard Brownian motion plus standard fractional Brownian motion. Just recall, I'm just going back to my fourth slide to show you covariance. It's absolute t to the power h plus absolute s to the power h minus absolute t minus s to the power 2h, sort of normalized by half. Now I am slide number 6 now. Okay, so the mixed fractional Brownian motion, this number 7 slide. The mixed fractional Brownian motion is a Gaussian process that's a linear combination of the Brownian motion and independent fractional Brownian motion. And one can study its properties. For instance, if H is the Hurst index is between 3/4 and 1, then you can show that the mixed fractional Brownian motion is equivalent to a Brownian motion, and hence modeling price fluctuations via mixed fractional allows arbitrage free market. So then there won't be any arbitrage. So you can, it's a genuine model for studying stock market behavior. So there is some mathematics which I have to introduce. So sometimes it's known as what's called a semi-martingale. It has certain properties. Semi-martingale is a local martingale plus a function of bounded variation. So now it's like a differential equation. Now we have to go back to some differential equations properties. Usually you cannot, as several of you might know, the Wiener process sample paths are not differentiable, almost surely, but they are also of unbounded variation. So you cannot do integration with respect to a Wiener process. So you use what's called Ito integrals. But then for Wiener process that can be done, but fractional Brownian motion, how do you define an integral?
And there is a you see, because when you talk about stochastic integral equations or stochastic differential equations, you need to define what are called stochastic integrals. And for instance, I have written. You look at I am on slide number 9 now. So you look at my differential equations number 2, which I have written in. So dyt is equal to ct dt plus dwt tilde h. W tilde is the mixed fractional Brownian motion, which I am talking today. So and ct is the what's called a drift function, and usually there is also a diffusion coefficient, which I have taken equal to 1 in this discussion. So if you look at the dyt equal to ct dt plus dwth tilde. But an alternate way is the first one is the integral representation. A differential equation can be written as an integral equation also, as in the above form. Next slide. So we can define differential equations. So the question is, how do you define stochastic integral with respect to a fractional Brownian motion? So fractional Brownian motion has also an unbounded variation. For those who are familiar with integral calculus, for instance, or Stieltjes integrals, you can define integrals as long as the integrator is of bounded variation. So you cannot define stochastic integrals if the integrator is of unbounded variation. So what is the alternative? So there are some methods for defining integrals. For instance, for Wiener process, fortunately, Ito has developed a special integral called Ito integral that takes care of that. But for fractional Brownian motion, there is no way of defining integrals in the standard Ito fashion. And therefore, there are alternate methods of doing integration. And I will not go by what is called a fractional calculus. Those who are in pure mathematics, there is a notion called fractional derivative, fractional calculus. So using such notions, you can define pathwise integration with respect to a fractional Brownian motion. So even if it is of unbounded variation, you can still define. So you can define integrals, but the basic idea is to estimate the drift function. If I go back to my slide number 9, you can see the differential equation dyt equal to ct dt plus dwt tilde h. So usually the w tilde h is called the driving force. For every differential equation, there is what's called a driving force, and then ct is the drift function. Sometimes it is a linear function. There are some unknown parameters in that function ct, which I will come to in a few minutes. So how do you estimate these parameters if you observe the process, say yt, over an interval 0 to t? For the present, for this talk, I will assume I can observe the process yt continuously up to some time capital T. So there are problems if you do it discrete observation, which is actually, that is the only possible. You can never observe continuously. But so here, ideally, you can suppose you observe continuously. How to estimate the function ct? No, if it is known but for a parameter, there are some methods. You can use some least square methods, maximum likelihood methods, and so on. But if it is completely unknown, then you use some non-parametric methods, which I will just highlight to you in my talk. I don't have much time to explain to you. So the basic problem right now is this process yt I observe from 0 to capital T. How do I estimate the drift function? And typically there is also a diffusion coefficient, but I am taking it as 1 today. And there are ways of estimating the diffusion also in general, but I will not discuss that today. Today we are only concentrating on the drift function. And so how do you estimate that? That is the basic problem which I will talk. That is my statistical inference aspect of this discussion. But how do you talk about a fractional Brownian motion no, what are the, say if you want to study the estimation problems, as all of you know, you need something like a central limit theorem, you need loss of large numbers. If you want to study properties, for example, maximum likelihood method, if you want to estimate the parameter, then you would like to know whether it's asymptotically normal, whether it's consistent, all these questions arise. So you use techniques like central limit theorem, loss of large numbers. So what are the various, how do you tackle such problems? And that is a very important issue. Next slide, please. Now, recently in 2016, this is number 10 slide on my transparency is number 10. So there is this Chai and a few others. They published a 60-page paper in Annals of Statistics. There, they present a new approach. So for not just fractional bound motion, but for any mixed process, which is xt equal to bt plus gt. Bt is the Brownian motion, gt is an independent Gaussian process. So if you have process of this type, how do you study properties of such process? Not differential equations is the next step, but how do you study properties of such process? So this paper appeared in the Annals of Statistics in 2016, and that came in handy for studying statistical inference issues. So let's take a special example. All of you probably know, if you are familiar with the first course in stochastic process by Carlin's book. He has written Einstein-Uhlenbeck process. See, all of you know, Brownian motion models position of a particle in a liquid. Einstein-Uhlenbeck process models its velocity. So now we can talk about what are called mixed fractional Einstein-Uhlenbeck process. So that is given by the differential equation dxt equal to theta xt plus dw t tilde h t greater than 0, and let us suppose that you start at 0. So here wth t tilde h is a mixed fractional Brownian motion. This is an analog of the Einstein-Uhlenbeck process in the literature. So this is a continuous time first order autoregressive process for those who are familiar with time series analysis, and is a solution of a homogeneous linear stochastic differential equation. The only difference from what is done in the literature, there they use a Brownian motion. By the way, for those who are worried about this stochastic differential equation, it's just an extension of linear models. It's like, y is equal to x beta plus epsilon, where x is the covariates and beta is the regression parameter and epsilon is Gaussian. So linear model framework, this is a generalization. You have a stochastic differential equation dxt equal to theta xt dt plus dw t tilde h. So this is a stochastic process, and then you observe the process over the interval 0 to capital T, say, and you would like to know how to estimate the parameter theta based on the observations. A more practical one is, suppose you observe only at discrete time points, then how do you estimate theta? So that's another issue, but I will not go into that aspect in this lecture. But those who are familiar would like to know, they can see in my books over the years. So the problem, the basic problem I should explain. So I want to observe this process xt. I'm speaking slide number 11. So the process you observe is the process over the time interval 0 to t, but now it is driven by a mixed fractional Brownian motion. I have explained to you why I use mixed fractional Brownian motion, and then how to estimate the parameter theta. So this is the basic problem which we'll discuss today. So there is a technique which they have suggested, Chai and that group in 2016, and also Chigansky and Klepsina from Israel and Soviet Union or Russia. They have a paper, not Russia, he's in France, now Klepsina is in France. So Chigansky and Klepsina, they have written You see, you might not be able to do it directly from the fractional Brown motion, but there are methods. You see, we all know, at least those who are familiar with stochastic process, there are a lot of results in, as I told you a few minutes back, you need to develop first limit theorems like loss of large numbers or central limit theorems. So we need to develop this technical tools before we do statistical inference. So they said, well, you might not be able to do it the original process itself because fractional Brown motion is not very easy to handle, but then there is a technique. You can transform this into a martingale. So that's what said. One can construct an integral transformation that transforms the mixed fractional Brown motion into a martingale. And how do you transform? There are some mathematics involved, so I will not go into that. So it's a very complicated equation over there, but it can be. So you transform the process. You look at equation number 4. You transform the process mixed fractional Brown motion by that integral, and then you get a martingale. You can show that that's a Gaussian martingale. And so now that needs some computation. You can show that that has a martingale, and this integral also it can be well defined. There is no problem, even though it has unbounded variation. For it's inside it's a deterministic function. There are ways of defining that integral, and then the equation number 5 it shows what's called its quadratic variation. These are important quantities if you want to do limit theorems. So and then even the original process is not a martingale, you can transform it into a martingale. And now there is a whole literature on martingale limit theorems. You can, if you have a martingale, how do you show that after suitable normalization, it's asymptotically a Gaussian process, things like that. There are theorems in literature, starting with Patrick Billingsley work on inference for Markov process in 1962, the first time such a result was proved, and later on several works are there in this literature. So you use this martingale, and I have written a theorem here. So the martingale, my previous slide number 4 in the equation. So that's the basic idea of my talk today. This is the martingale. Using this martingale, you can transform your original differential equation to another differential equation. Now it is driven by a martingale. So that is the next theorem, it says. So you make a transformation, and this is the original process equation number 7. You see, I transform by this function g. You get a new process zt, which is also what's called a semi-martingale. And for those who are not familiar, that's fine. I just want to tell you the ideas only. So if you are very keen, you can look into my books or other books. So you can transform the process zt. So now it is driven by a martingale. You can look at equation number 8. I am in the slide number 15. So you can use the martingale, and then it's written in the integral equation form. And then you can, you can reduce the process. Now, I want to say for those who are interested in statistics, what is the advantage of this? You see here, this is an important idea. The natural filtration, that means the information contained the observations up to time t, either in the original process y or in the transformed process z, are the same. This is statistically a very important observation. Once the information is same, whether you use that differential equation or the other differential equation, the first one yt is defined by the process driven by a fractional Brown motion. The second one is defined by a martingale. So you are not losing any information. So in statistics we learn you should never lose information by throwing away observations, and that is not happening. The sigma algebras are in mathematics they are called sigma algebras. Filtration in statistics is just information up to time t. So and same thing happens in Z. So whether you use this martingale formulation or the information about the original one, it is the same. So that is a very important advantage. And then I go to this. So once you have this important information that you have transformed the process to a martingale-driven work. So then, standard, for instance, what do you do you have to write the likelihood function. If you want to study the parameterization, inference aspect, I am on the slide transparency is number 18. So if you want to study that, you have to, what is, in standard likelihood theory, you use the density function. Maximum, if you are able to write the density function or the likelihood function, you have to write. You need to maximize the likelihood. You get the maximum likelihood estimator. So that's one way of doing it. If you have discrete observations, you use least square is another way to approach to that. So what is the analog here in this continuous framework? The analog is what's called a radon-Nikodym derivative. For those who studied measure theory, they would know that if you have two measures which are absolutely continuous with respect to each other, you can compute their radon-Nikodym derivative. A radon-Nikodym derivative is the analog of density function. And then, so once you have radon-Nikodym derivative, say up to time interval 0 to t, then you try to maximize your likelihood function, and you have the maximum likelihood estimator. And of course, you have other, later on you have to study its properties. So now, this is what I explained to you a few minutes ago. Since the filtrations generated by the process Y and Z are the same, the information contained in the families is the same, and hence the problem of estimation of the parameters involved in the observations YS are equivalent. This is slide number 19 now. Okay. So now I will take a very special case. This is called linear stochastic differential equation. Just like you have linear models, here it is a linear stochastic differential equation. dxt equal to atxt plus theta times btxt plus dwt tilde h. So the question now is, if I observe the stochastic process t continuously over the interval 0 to t, and the process is now driven by the mixed fractional Brownian motion, how do I estimate the parameter theta? That's the basic problem. Now, of course, I have considered only one-dimensional case. So multi-dimensional cases are more complicated. So this is the drift function. That is the CT function which I told earlier. So in this case, CT is a very simple one. And then you can transform this process. As I told you, the original process you cannot handle directly. You have to transform this into a martingale-driven process. And you have to go through some of these mathematics, which I will not go into that. So this is the differential. This is the number 23. So 23 slide number, equation number 18. So that is the radon-Nikodym derivative. Now you see there is a parameter theta involved there. In the linear case, you can actually compute this. So we now consider the problem of estimation, number 24 slide. We now consider the problem of estimation of the parameters theta based on the observation of the process or equivalently ZT. So the maximum likelihood estimation. So we consider the problem based on studied asymptotic properties. So this is the standard ideas. You have the likelihood function, you maximize the likelihood and find a parameter theta hat t. This is number 26. Number 26 on my slide. Please show that. So LT theta hat t is supremum LT theta. Theta belong to theta. So theta hat t is there could be many, but let us say the infimum of them. So that is the maximum likelihood estimator. And then of course you would like to know how to, what are the properties. So in the linear case, I can actually compute this transformed process easily. And I can also compute the log likelihood ratio. It's quite simple in this form. By the way, this you can write down the likelihood equation number 22 on slide number 28. My transparency number 28, you can see that transparency number 28, equation number 22. So you have a likelihood equation that arrows actually depends quadratic variation, that's called, and then you can actually compute the likelihood estimate. So this is the likelihood estimator, theta hat t minus theta naught. This is number 29 slide. So this is the final case in the linear model case. Okay, theta hat t minus theta naught is there is a numerator, is a g2t, but now it is with respect to a martingale, and the denominator is j square t d quadratic variation. Quadratic variation is actually a non-random function. Okay, quadratic variation here in this case is a non-random function, and you have that. So you have you can well, even if it is random, there is no problem here. So you see these two. So if I want to study any consistency properties, equation number 23 I am talking about. So theta hat t, does it converge to theta naught? Or what is its asymptotic distribution? How do you normalize that? So there are limit theorems for integrals with respect to martingales, and there are strong laws of large numbers too in stochastic process. For instance, you get the following theorem. The maximal likelihood estimator is strongly consistent. That means theta hat t tends to theta naught almost surely as t tends to infinity. That means in this case, it's provided this condition is satisfied. So you can, there is a strong law of large numbers, and also there is a proof I have given here by using strong law of large numbers. It was written, look at slide 31. If you look at slide 31, there are theorems in a book by Lipshar and Shiryaev in 1989, or my book. It was written in 1999. So then, of course, limit distribution. For instance, what is it asymptotically normal? Now, it turns out, for those who are familiar with my book with Basawa, in what are called non-ergodic models, it is not necessary the maximal likelihood estimator is always asymptotically normal. In fact, in branching process case, it is not asymptotically normal, it is mixed normal. So here also the same situation arises. Under some conditions, it's normal, but not in general. It could be a mixture of normal distributions, and there are some conditions which you have to go through with that. So this follows from limit theorems for martingales. See number 33 slide, number 33 in my transparencies, number 33. Now, so I'll skip some of these things which I have talked about. So in the special case of fractional Ornstein-Uhlenbeck process, you can also, once you have some ideas on maximal likelihood estimator, asymptotic normality, then you would like to know how much time you have to wait till you get actually a normal distribution. And so in other words, what is the rate of convergence? So such results can be also obtained. For instance, what are called Berriesian bounds. That's written on 37 slide number. And then there's a proof here, which unfortunately I don't have time to go through that. It needs some ideas from techniques from stochastic process. For instance, if you have a Wiener process, if you have some quadratic variation, so you can stop the Wiener process. If you have a random variable x with some distribution, you can always stop a Wiener process at the right time, at some stopping time, so that the Wiener process at that time will have this distribution. For instance, if you want something like a something like gamma distribution for some random variable, so you can look at it, you can stop Wiener process at a certain time to get that distribution, stopping time. So using that, and there are some technical lemmas, using Michael von Zagel has written a technical lemma where when you this is slide number 41 slide. So there is a nice, very interesting lemmas which were proved in 1971. Using such results, you can obtain this Berriesian bounds. And there are some results. Next slide is 42, which tells you what is the what is the difference between a Brownian motion stopping at a random variable v and normal distribution. It's a lemma due to Hall and Heidi. It's a theory of martingales.
Sir, 5 minutes more.
Yeah, I'll stop that now. So there are some of the results of this. Now I can also talk about Bayes estimation. I just want to introduce several problems in the area for those who are keen or interested. You can also talk about Bayes estimation. Same problem with you want to estimate the Bayes estimation. So that's also can be done. So I have only 4 minutes, so I cannot go into any further details. So then there is something called Bernstein-von Mises theorem. It was proved by me in Markov process several years ago with my colleagues. So you can prove a similar theorem. It just says the Bayes estimators and maximum likelihood estimators have the same behavior asymptotically. So it's a very important theorem, just called Bernstein-von Mises theorem. So the same results can be obtained for this. So in the finite time, they might differ, Bayes estimates and maximum likelihood estimate, but in the long run, they have the same asymptotic behavior. So this is what called Bernstein-von Mises theorem, and a similar result can be proved for this. So this is the theorem under some regularity conditions. This is slide number 50. Posterior distribution, slide number 50, please see that. Posterior distribution goes to a normal distribution after suitable scaling. So this is called Bernstein-von Mises theorem, and then there are several results in optimal estimation and how to estimate theta I. For instance, you look at the differential equation number 44. So you can see that you want to estimate now. It's a multidimensional parameter, and there are results in this direction which I have published recently. And then you can also talk about Bayes sequential estimation. This is slide number 52. So Bayes estimator is always obtained with the conditional mean, and all of us know when it is a squared error loss function, posterior mean is the Bayes estimator, and similar techniques can be obtained here, and you can develop this theory. And then finally, before I conclude my talk, you have also talked about non-parametric estimation. So here you look at equation number 50, slide number 57, equation number 50. So dxt equal to sxt dt plus epsilon times dw. Now here for mathematical convenience, we fix t, time fixed, and let epsilon is called the small noise that go to 0. And you want to estimate s. S is an unknown function, completely unknown. So you use non-parametric estimation. You use kernel techniques. You can use kernel methods of estimate. So look at equation 52. That gives you the kernel idea of kernel estimator. Equation number 52 on slide number 59. So you have that. So then, of course, you would be interested in trading properties. Is it uniformly consistent and all that? So these results and then you want to know its asymptotic distribution and things like that. So, and then of course there are other, instead of what's called a linear multiplier, equation number 54 on slide number 63, you have results on the linear multiplier case. So I'm sorry I can't go into details, all those things, but so these are some of the references in this area. Annals of probability, not annals of statistics. I think I was wrong at that time. So annals of probability 2016 is the paper, a very, very important paper. And then of course Bernoulli paper, and I have my books on 2010, and I have written a long article in Journal of Indian Institute of Science, fractional process and statistical inference. Indian Institute of Science, there is a Indian Institute of Science. Last year, it was published in last year. For those who are very keen, are interested, not necessarily very keen, but interested, they can look into this book, which is a review paper, which I have written. My earlier book was 2010. Well, thank you very much for spending.
Thank you very much, Professor, for giving a wonderful lecture on that. There is one hand raised, and is there someone by Nagesh? Nagesh? I think that, yes. Mr. Nagesh? No. So then, is there any other questions? Anybody who would like to ask any question? We can take 1 or 2 questions, possible. Yes. It seems that.
Well, if I have no question, I just want to say one sentence. Say this area it falls between probability and statistics, so it might not be of immediate easy for everybody, but then it has a lot of applications in finance. This one and biological models. So there, these are being used. So it is not just mathematics for mathematics' sake. It has applications, quite a few things. Thank you very much.
Right. Yes, sir. I was about to say that. I wanted to request Professor Satish Kumar to consider this financial related analytics in the other portion. That is, there's a program on data analytics and all that in the department. So you can just think of including this as a topic in consultation with Professor Prakash Rao, and at least at the elective level, that will be very useful, because that's a very interesting topic and a very useful topic also in the end. So I think that I heard a lot of old names like Radon-Nikodym theorem. Hearing Radon-Nikodym theorem, mind goes somewhere in the old memories, and very nostalgic about those things. And I'm very happy, sir, that you delivered a wonderful lecture on that. At least I enjoyed it by hearing some of the very important, concepts by name. So on behalf of the Department of Statistics and the organizers, I thank you for delivering a wonderful lecture. Let us appreciate it.
Thank you. So I would like to thank Dr. Satish Kumar for his invitation. Thank you very much.
Thank you, Professor, for your wonderful talk. In fact, no doubt it will be benefited. Several will probably contact in time, because due to this online program, probably they can't able to contact you personally, but they will contact you through email or other way.
Thank you.
Anyway, as mentioned by our Kalyan, we can also include these topics in while revising our syllabus and also to our researchers. It's a very odd and very interesting topic. Very useful concepts are there. I utilize this occasion to extend our gratitude to Professor Prakash Rao for your nice talk, and Professor Kalyan sir for chairing the session. Thank you so much.
Thank you. Bye-bye.
Now let us move to the next session. Bhagya is there in the group.
Yes, sir.
Bhagya, please raise the next chair and do the needful for the proceedings.
Hello, everyone. We are moving on to the second technical session of Wsta 2023, which is a special session in honor of C.R. Rao that shall be chaired by Dr. Narendra Kumar. Dr. Narendra Kumar is a professor and former head to the Department of Statistics, Punjab University. His areas of interest include statistical inference, multiple comparison procedures, and applied statistics. He has collaborated with academic experts from various universities across and outside the country for research projects. Dr. Kumar has published several research papers in various national and international journals and proceedings, and has given lectures in more than 100 national and international conferences. He is a member of Indian International Statistical Association, IISA, and Indian Society for Probability and Statistics. An excellent academician with experience over 3 decades, we are really lucky to have you, Professor, chairing the session today. So with great joy and honor, I cordially invite you, Professor, to chair the session. Over to you, sir.
Welcome.
Thank you, Ms. Bhagya Lakshmi, for giving me this opportunity to chair this session, and thank you, Dr. Satish, for this opportunity again. So I welcome Professor Debashish Kundu. So in fact, he doesn't need any introduction. So he is a a very well-known professor. But I have to give an introduction because only for those people who have entered into this profession, particularly maybe this year only. So welcome, Professor Kundu. So could you please put on your camera so that everyone can look at you?
I'm sorry. I think it is already on.
Hello. Oh, I was not able to. I'm sorry.
Yeah. Can you
Morning
see it now?
and welcome to the session, please.
Thank you. Yeah.
So I have to introduce you because maybe, as I said, few persons have entered into statistical community this year, and I'm taking that opportunity to welcome you, right? So you have a very long list of your vita, so I have to go through that. So I could have taken the full 30 minutes for that, but I have picked up few things from that just for introduction purpose. Professor Kundu is one among the nationally and internationally acclaimed statisticians. He is Rahul and Namita Gautam Chair Professor in the Department of Mathematics and Statistics at IIT Kanpur. His research interests are in the area of statistical signal processing, nonlinear regression, survivor analysis, generalized exponential distribution, statistical computing. Professor Kundu has, to his credit, over 360 publications with total citations of over 15,000. So big number. H index of 63 and I-10 index of over 200. He has also published 4 books from highly reputed publishers, so which are widely used by the researchers. Professor Kundu has also received many honors and awards, such as Chandana Mathematics Award from Canadian Education Foundation, and Professor P.C. Mahalanobis Distinguished Educator Award by ORSI, Excellence in Teaching Award from IIT Kanpur, to name a few among the long list he has. In addition, he is also a fellow of NASI, so which is a very prestigious academy, National Academy of Sciences, India. So, and he got elected to it at a very young age of 40 years. And he's also a fellow of Royal Statistical Society, London, so to which he was also elected at a very young age. Further, he has delivered many keynote, plenary, and endowment lectures, etc. So now I invite sir to deliver this plenary address in honor of Professor C.R. Rao sir. Over to Professor Kundu, please. Thank you so much.
Thank you for the kind introductions. Can you see my slide?
Yeah, it is.
Okay, good. Yeah.
You have 40 minutes, so can we do like 35 minutes for?
Sure, definitely. Yeah. See, when Professor Satish Kumar has called me and told me that he wanted to invite me for this C.R. Rao lecture, and I could not find any other better topic than this, because this is the topic which was introduced to me by Professor Rao way back in almost like around 37 years back. That's what I can remember. It was in 86. I just finished my comprehensive exam, and he has told me, he has given this one of the problem in the statistical signal processing, and one of his standard way, he said this one, that, well, if you can solve this problem, I will give you PhD. So it was a long back, and it was a long journey, and so that was the beginning of this particular type of problem. And after that, I mean, still today, I mean, he has basically introduced me to this area, I would say, and till today, I can find there are lots of interesting problems which are cropping up, and in fact, many of my PhD students, and I'll give the list, those who had worked on the statistical signal processing, and those who are some of them are still working on it. Okay, so let me just start with that. This is more or less the outline. I'll give a brief introduction, and then I'll go through along this one. So let me start with the basic formulation and the basic motivation of the problem. So this is basically
we are trying to model the periodic data. Dilip, are you saying something? Okay.
No one has said.
Okay. So basically, we are trying to model the periodic data, and which we observe actually in everyday in your life. I mean, whether you are looking at the number of visitors in Taj Mahal or the daily temperature, or even the EEG, ECG data of a normal human being, most of them are either periodic or nearly periodic. Okay, so there is a need to analyze this question. Okay, so now there are two natural questions: what is a periodic data, and why do we really care to analyze the periodic data? Okay, so let's not go into the formal definition, but I think we have rough idea about the periodic data. What we can say that it shows some kind of a repeated pattern in one dimension. I mean, that I call, we have a formal definition, but let's not go into that. I mean, there is no need for that. But we understand, we had some notion about this periodicity, that it has repeated nature in one dimension. Interestingly, actually, it has a notion even in the higher dimension also, 2 and 3 dimension also. And in the higher dimension, it has whenever there is the symmetric nature, we call this one as a periodic one. Okay, so we'll come back. We'll see some of the picture about the 1-dimensional and 2-dimensional periodic data. Okay, so now the next question is, why do we really care to analyze the periodic data? Of course, there is a theoretical reason, because I mean, all of us nice to have nice mathematics and all these things. So we like to have a theoretical reason behind it. So let's try to model a periodic data, that is of course. But I think more practical point, if you're looking at it, that suppose you have a periodic data, say for example, suppose you have a data for the EEG or the ECG, definitely there is a need for the prediction. Okay, so what I'm expecting maybe after a few seconds, I mean those kind of prediction, definitely that plays a major role for the analysis of the periodic data. And there is another big thing, what is called these compression purposes. That means suppose you have a periodic data of a huge length, but if we can model it properly, I don't need to keep the entire data set. I mean, I can just keep the few parameters, okay? And therefore, there is a big compression which can take place, okay? So these are the mainly the reason that we really care about analyzing the periodic data, okay? So let's look at some of the very, very standard the periodic data. This is a very, very well-known data. That's an airlines passenger data in the US for in each month, and you can see that there is a pattern, and there is a peak in each year, and those peak actually during the summertime. Okay, so there is I think 1, 2, 3, 4, 5, 6, 7, 8 or 8 years data they have, and you can see that it is gradually increasing. Of course, there is an increasing trend, but definitely there is a periodicity in this data set. This is another data set, which is the brightness of the variable star. This has been collected in some of these astronomical society in Australia. Things have been collected in IIT Kanpur only. This is a vowel sound of a male vowel. He's trying to utter the word woo, and so there is clearly a periodic nature. And this is the ECG data of a normal human being. This is also has been collected in IIT Kanpur, the electrical engineering lab. Okay, this is the data which is in the 2-dimension. This is called the texture data. So it's a 2-dimensional periodic data, and you can clearly see that there is a pattern, there is a symmetric pattern. There is a 3-dimensional one, there is a 3rd dimension which gives the color. So this is a 3rd dimension, and this is also another 3-dimensional periodic data. Okay, so you can see that there is a pattern, there is a symmetric pattern in this one. Now let's comes to the basic formulation, and I think which are all of us are familiar with. If you're looking at the simplest periodic function, I mean those you have studied even in class 11, 12, that which is the sine and the cosine function. So I can plot the function yt, which is a cosine omega t plus b sine omega t, which is basically a simple periodic function with the period 2 pi by omega. Okay, so it repeats in a periodic manner. Okay, but now Suppose we have if we go a little bit higher than that, suppose we have a smooth periodic function and with a period 2 pi by omega, so then you have the standard Fourier expansion of the function yt, which is an infinite expansion, which is ak cosine omega kt plus bk sine omega kt, and that's what I have. We have an infinite expansion of the Fourier expansion, and I know how to get this AKs and BKs. So we have this simple formula for the AKs and BKs. This is the standard Fourier transformation. But often in practice, we do not observe exactly the periodic data. What we observe that it comes with a noise. So there is always an XT, or the additive noise. I mean, I am assuming that it has an additive noise. So the additive noise is always there. Okay, so there is an additive noise XT which is there present. Okay, so that is what we observe XT instead of observing only the clearly the periodic signal, which is an infinite dimension. But now we can see that there are infinitely many parameters. Okay, AKs and the BKs. So we cannot estimate. We cannot estimate all those infinitely many parameters. So what we do, we truncate it. We truncate it up to a certain stage P. So we modify the model slightly, and we look at this model YT, which is AK cosine omega KT plus BK sine omega KT plus XT. So now this model has received a tremendous amount of attention in the statistical signal processing as well as in the time series analysis. Okay, so this is the one what we'll be dealing with in the one-dimensional. So this is what we have. That means we observe these YTs, the signal, which is of course corrupted with noise, which is XT, but the model which is in this form, and for some P less than infinity. So of course in practice, my P is unknown definitely. So we need to estimate P also. So you can see that the model has two components. One is of course the deterministic component, which is the mean part, which is up to the P component k is equal to 1 up to P, AK cosine omega KT plus BK sine omega KT. So that is the deterministic component, and of course there is a random component. Okay, so our problem is that we have to extract the deterministic component mu t, okay, which is the mean part, that is the main signal, from the noise corrupted component xt. Of course we have this some noise assumption. So based on the reasonable noise assumption, so that is of the theoretical nature, but in practice of course we know that there has to be some noise, and so we have to come up with a reasonable assumption on the error xt. Of course the minimum assumptions the better, but our main aim is try to extract mu t from xt. Okay, so what we can see that, so what we usually do based on the available data, we have this deterministic component. So estimate P, as I said, the P is often unknown. So number of components, estimate those A1, A2, AP, B1, B2, BP, as well as estimate omega 1, omega 2, omega 2. So you can see that there are so many components which you need to estimate from the data YT. And of course, we need to estimate the error component also. And of course, this is purely for the statistical reason, because we know this one, that whenever we make a model assumption, I mean, if you simple linear regression case, if you're looking at the model assumption, one basic thing is that to estimate or test the error analysis. That is a very, very important thing, that because otherwise all our inferences become useless unless we do a proper error analysis. That means whatever error assumptions we are making it for the model, whether it makes sense or not from the given data. Okay, so that is a very, very important one. Estimate xt and basically verify whether the assumptions what you are making about xt, whether it is satisfying or not. Okay, so the procedure usually what we follow, that is that assume certain structure on xt, you assume certain thing, maybe the of course, see this without loss of generality, we can take it to be the mean 0, because otherwise we can always put it in the mean component of the signal. So we are assuming it to be mean 0, and then we make certain assumptions, maybe the independent, maybe the correlated, whatever it is. So make the certain assumption on xt. I will come back to those the standard assumptions. Then of course we estimate the deterministic component mu t. Based on the assumption, you estimate the mu t. Then you go back and estimate the error xt, as I said, the error analysis, and verify the assumptions. That is a very, very important one, that whatever assumptions you are making about the noise component xt, whether it is making sense or not, you verify the assumptions. And if the assumption is satisfied, then stop the process. Otherwise, of course, you have to modify the assumptions and go back to step 1. Okay, so this is the usual procedure what we follow in a situation like this. Okay, so now let's look at the different estimation procedure for this type of model. Okay, the most important and interesting, or the most classical one, what it is known as the periodogram estimator. And interestingly, actually, this particular model has been extensively used by the engineers, particularly if you're looking at the electrical engineers, civil engineers, even the physicists also, they use this model. And so one of the standard thing what they use, what they call this the periodogram function, or the periodogram estimator. So they compute this I theta. Okay, you can see that they write this function I theta, which is the data, which is yt, and then cosine theta t square, and then this one cos square. So this they look at this function I theta over the range 0 to 2 pi. Okay, why they consider this one? Of course, you can do the mathematics and all these things, and but before let's not go into that one. But let's look at the plot of the function I theta, where the x-axis is between 0 to 2 pi, and the y-axis is I theta. And I have taken this specific signal. Okay, you can see that my yt, which is 3 times cosine 0.2 pi t, but sine 0.2 pi t plus this one. So that means your omega 1 is 0.2 pi, and my omega 2 is 0.5 pi. Okay, so that's what it is. And now I plot the function I theta, this particular function I theta here, and you can see that there are 2 peaks in the function. And where are those two peaks? Those 2 peaks is actually at the point omega 1 and omega 2. Okay, so that is the reason this particular function is a very, very popular one. And people, what they do whenever they have this, and by the way, I have taken this xt to be IID normal with mean 0 and the variance half. So that is a noise corrupted data, and I simply plot this function I theta, and which gives this one. So there are 2 peaks at the point omega 1 and omega 2. In this particular case, it is 0.2 pi and the 0.5 pi. Okay, so these are the 2 places where the 2 peaks occur. Okay, so this is the very, very standard method. People do use it, and things are quite nice. Okay, but well, not that everything is so nice all the time. Okay, otherwise it would not have received so much of attention, because looks like a very, very simple problem. Now let's look at a slightly different one. I'm taking the same mean function. There is no change about the mean function. Okay, so 3.0 cosine 0.2 pi t plus this one blah 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 plus xt. Only thing what I did, instead of the variance half, I just make the variance 2. Okay, so I just make the variance 2, and I am looking at the function I theta in this case. And now you can see that things have completely changed. One peak has vanished. I have only one peak. Instead of 2 peaks, there are only 1 peak now. Okay, so now you can see that. So therefore, the method works very well as long as the variance is small. Okay, so that is the only thing what I have changed. If the variance is small, the method works very well. But if the variance is large, the method does not work well. Okay, in the signal processing literature, they have a very, very standard technique, and even the statisticians and the computer scientists also nowadays use this term. They call this signal to noise ratio, SNR. If the signal to noise ratio is high, that means your signal power is more than the noise power in some sense, I mean, in a loose sense, then you can estimate the parameters effectively. But if your signal power is not that high compared to the noise power, then you cannot estimate, which I think intuitively also makes sense. I mean, the signal has more power than the noise, and then you'll be able to estimate. So in the second case, of course, your signal power is much smaller compared to the noise power. because the variance is high, and therefore the noise is dominating. Okay, so we are not able to do this one. So now let's come back to our basic statistical tool, which has been used in centuries, and simple least square estimators. Okay, so that is the one. What we can do by using the least square estimator. Interestingly, actually, Fisher has also looked at this problem, and he has stopped it here. He just mentioned that, well, just look at the least square estimators, and that's it. Okay, but fortunately or unfortunately, he did not follow it up after that, and then actually it has opened up a huge amount of problem because of this. Okay, because although it looks a very standard classical method, but it is not that simple to solve this problem. That is the whole issue, actually, that solving the least square estimators is not an issue. It's not a problem. What are the problems? There are numerical problems as well as there are theoretical problems. So what are the numerical problems? It is a highly nonlinear problem. Okay, so it is a nonlinear function, highly nonlinear problem. The least square surface has several local minima. So that is one of the very problematic things. Okay, there are lots of local minima. We know that in most of these nonlinear cases, we go for the standard algorithm like this Newton-Raphson algorithm and all these things. But in this particular case, the Newton-Raphson algorithm does not converge. I mean, that has been observed by many people. And not only that, because it has several local minima, even if it converges to the global, it converges to the local minima than the global minima. Okay, so that is also another big problem. So you really do not know, what solution you are getting it. I mean, you are getting a solution, but that may not be the least square solution. You might be getting something else. And not only that, and another big numerical issue is that if P is large, it becomes a higher dimensional optimization problem. I mean, as we can see, we'll show that some of the data analysis that P can be even say 20, 30, 40. Okay, so you can see that there are 120 parameters, because for each P there are 3 parameters. So if P is 40, so there are 120 parameters. So that makes the problem very difficult one. What are the theoretical issues? Theoretical issues that, well, as I mentioned, that this I can put it as a simple nonlinear regression problem, which can be written in this form, and the Wu and Genrich, they have 2 very good paper in Annals, and they had given basically the sufficient conditions. I mean, Genrich was the first one, which is Annals of Mathematical Statistics. He has given the sufficient conditions for the nonlinear regression, nonlinear regression least square estimator of the nonlinear regression parameters to be consistent. Who has generalized that one, but unfortunately in this particular case, none of them work, in the sense that, well, those sufficient condition this particular model does not satisfy. So therefore, we need to have, I mean, there are 2 possibilities. One possibility is that the least square estimator may not be consistent. That can be one possibility. Second possibility is that you might have to develop a different theory completely to establish the consistency and the asymptotic normality, because the results what we have developed by Wu and Genrich, they are all sufficient conditions. Okay, they are not necessarily insufficient. So either that if they are not consistent, there is a possibility, or you need to develop a completely different theory for that. Okay, fortunately in this particular case, we can develop the theory behind that one, that, well, they are consistent estimator, but interestingly is that the usual in the nonlinear regression case, the convergence rate is n to the power minus half. But in this particular case, what happens, for the linear parameters, the convergence rate is n to the power minus half, but for the nonlinear parameters, it is n to the power minus 3/2. So this is a kind of an unusual situation, what we have observed here. Okay, but what we could do, that now we know this one, that the least square estimator is a consistent estimator, but still the numerical problem still remains, because if it is a higher dimensional problem, suppose my P is very large, then of course I know that it's a very difficult to solve, because suppose this P is say 15, I have to solve a 45 dimensional optimization problem, which is a very difficult one. So what we have proposed this one, what is called as a sequential procedure. That means I can estimate one at a time. Okay, say what I can do, for example, I can simplify it is kind of a, I would say, in the multivariate setup, suppose we are looking at the columns are all orthonormal. Okay, so it is basically that way. The principal component analysis actually is kind of thing. So we do it step by step. We first estimate the first component, then you go for the second component, then you go for the third component, and so on. So what is happening? The main advantage of this one is that each time I have to solve only a one-dimensional optimization problem, and therefore the implementation becomes a very, very easy one. And the nice part about this one is that they have the same theoretical properties as the least square estimator. So we are not losing in efficiency. Okay, we are not losing in efficiency. We have the same efficient estimator as the least square estimator, but computationally we are saving an enormous amount. Okay, so that's what I had tried to put it here. Suppose it's a 25-dimensional P is equal to 25. I need to solve a 25-dimensional optimization problem, which is a really, really tough job. But if you follow this sequential procedure, I have to just solve 25 one-dimensional problems, which makes the things very, very simple. There is another method, what we have proposed, what is called this one, the super efficient one. And this is a very, very counterintuitive one. And when you have first observed this one, that it was difficult to believe. But which is theoretically true, that we can modify the Newton-Raphson algorithm, okay, slightly, which is called the step factor modification, which you could do it. But then what we can obtain that the asymptotic variances of this super efficient estimator has variances lower than the asymptotic variances of the least square estimators. Okay, of course, it is due to that it created some biasness in the finite sample. Of course, asymptotically it becomes unbiased, but it created some biasness for the finite sample. So that's a compromise what you make, but it produces the lower variances in the broad variances. Okay, so the main theoretical results, I think I had already mentioned. The least square estimators are consistent under mild assumptions on the error. Least square estimator has the convergence rate into the power minus 3/2. Sequential estimator have the same convergence rate as the least square estimator. Asymptotic variances of the super efficient estimators are smaller than the least square estimators, and the periodic curve estimators are consistent, but it has a convergence rate into the power minus half. Okay? So these are the major theoretical problems. Now let's look at the nearly periodic model, which has received a considerable attention in the last 10 years in the signal processing literature. So far we have talked about the sinusoidal model, which is a clearly a periodic model. But this one we are talking about what is called a chart model, where there is what they called as a phase component. So what we have something in the t-square component also. So this yt, which is a times a of cosine alpha t plus beta t square plus b of sine alpha t plus beta t square. Okay, so this is for the one component, and the general one, of course, it has the p component one, and of course the additive term. Okay, this one has various applications in the audio signals, ranging from the bird songs, music to the animal vocalizations and the speech. By the way, you might be wondering that why we bother about the bird songs modeling. Actually, it is being done quite effectively to detect the endangered species. Actually, okay. So they put the microphone in the forest, and they try to capture those the bird songs, and they try to identify, they classify, and then they try to identify. So it has a very, very specific practical applications. Of course, it has been used extensively in the radar and the sonar systems, and it has been used also in the EEG signal also. But this problem becomes a much more theoretically challenging problem. Here also, what it can be shown that the least square estimators are consistent under some kind of a stronger assumptions on the error assumptions. We need to have a fourth order moment to be finite. Of course, it has the convergence rate for the linear parameters n to the power minus half, and for the alpha parameter n to the power minus 3/2. Surprisingly, for the beta parameter, it is n to the power minus 5/2. Okay, so these are the very, very interesting fact, theoretical one. Okay, that is interestingly that we have found out a nice connection with one of the number theoretic results. There is a we have a result similar for this chart kind of model. Instead of cosine θ1 n, which have θ2 n square, we have this kind of things, and there is, based on these things, it can be shown that the sequential estimators are also consistent in this case. So we can do this one. That is one number theoretic conjecture actually, which is also available, which has not been proved, but we have also verified. Many people have verified this one with extensive simulations that that results holds. And so if we assume this number theoretic conjecture, so this then what we have that we can show this one that the least square estimators, the sequential least square estimators have the same asymptotic distribution as the least square estimators. It has a two-dimensional analog also. The same thing what we have shown for the one-dimensional for the sinusoidal model. There is another one what we have recently proposed, what is called the chart-like model. So in this particular case, it is of the form of AJ cosine alpha jt. That is a plus sign, BJ sine alpha jt, plus there are the t component and the t square component. We make it separate. So this model also has received a considerable attention. Just one final one. So this is the recently what we had proposed. What we call this one as a weighted least square estimators. Instead of the least square estimator, we have proposed this one as a weighted least square estimators. So we can choose the weight function, and the basic idea about the weighted least square estimator is that to provide the robust estimations. Okay, so if you go back to our usual robust estimation by the least absolute deviation estimator or the Huber M estimator, the basic idea is that so whenever there is a large residual squares, residual component, you make it smaller. Okay, and that is precisely what we can do it here with the proper weight function Wt by n. And so if there are outliers in the data, so this method works quite well, and that also we have seen in our extensive theoretical results that if there is an outlier in the data, it behaves much better than the usual least square estimator, and it is at par with the least absolute deviation estimator or the Huber M estimator. But the nice property of this particular estimator is that you can establish the consistency and all the asymptotic normality and all these things in a much more weaker assumptions than what is needed for the least absolute deviation estimator or the Huber M estimator. Okay, so that is the nice part about this one. Okay, these are some of my students, those who have worked, and some of them are still working on these things. Ovinek and Anjali are still working on the signal processing problem, and these are some of the references. We have a recent book actually on this signal processing one. The statistical signal processing came out in 2020, and with this I think I will stop it. Thank you for your attention. Thank you very much.
Thank you, Professor Kundu, for a very interesting talk. So I have been greatly benefited with this. So personally, I'm sure all others have also enjoyed your talk. So there is one query I have.
Yes, please.
If the dimensionality is here,
yes.
So maybe say in 20 or 25 or whatever. So can we have dimensionality reduction techniques and periodic data also? Or? Yeah.
So that's what we have done it actually by using this sequential procedure. And in fact, that's what we have done. I mean, if you use a sequential procedure, we can solve the one dimensional at a time. That's what we had done it actually. And what we could show that that even in this case also, you have the same asymptotic properties as the least square estimator. So you are not losing in efficiency. Okay. And in fact, we have used the data set for particularly some of the EEG data set where you can see this one that we need to fit, and maybe say P is equal to around 60. So you can see this one that If it is a 60, that means you need to solve a 60-dimensional optimization problem if you're trying to do the straightforward least square estimator, which is almost impossible, okay, which is a very, very difficult one to go for a 60-dimensional optimization problem. But in this particular case, you can do this one sequentially. So basically, I have to solve 61-dimensional problem, which is a much easier one, which you can do it in a much more easier manner.
Right. So that they are like alternative to principal components and all that.
Absolutely. Yes. Yeah.
Are there some applications in neuroscience as well?
Neuroscience, yes. Actually, that's what we are trying to do nowadays. I mean, recently we have started working on this, what is called this one as a multi, what do they call this, multi-channel data. That means you have more than, say, you are having this signal from the different channel, which can be used for these neurosciences. And that's what we are trying to develop the model for the multi-channel. I mean, there are models, we are trying to look at those things and we are trying to develop the properties and the information techniques and things like that. Yes. So, yeah.
So, is there any other queries the participants can ask?
I would like to share some of my observations. Sure. In the University of Madras, in the late 50s, this happened to be part of the core subject teaching. There was something called as a periodogram. Is it not the same as that?
Yes. It is the same one.
Yeah. So
the same periodogram thing. Yes, exactly.
It is the same as periodogram. Am I right?
Yes. It is the same thing. Yeah. This one is an old method. This periodogram technique is an old technique actually. It has been there for, maybe more than 100 years. Yes.
Any other comment, query, please? So anyway, if there are no other queries, so let us thank the speaker for a very interesting talk, and it was very thought-provoking. Right? So let's thank the speaker.
Thank you very much. Yeah.
Thank you, Professor Kundu, for your excellent talk. We are always grateful to you, Professor, for your support. In fact, we on behalf of the organizing committee, we would like to express our gratitude to Professor Narendra Kumar also for chairing the session in a very nice way. And
thank you.
Thank you so much.
Thank you, Professor. Thank you. Now let us move to the next session. Professor T.J. Rao is there and Professor Hanagal to chair. Swapna, please introduce the chair and invite him and support him for further proceedings.
Good morning, good afternoon, and good evening to all. We are moving on to the technical section 3 of WSTA 2023, which is a special section in honor of Professor P.C. Mahaloban. That shall be chaired by Professor David D. Hanagal. Now, Professor David D. Hanagal is a faculty at the Department of Statistics, Savitribai Phule, Pune University, India, from where he obtained his MPhil and doctoral degree in statistics. Professor Hanagal has made significant contributions to both teaching and research, shaping the field in profound ways. He was also elected as the Fellow of Royal Statistical Society, London, in the year 2003, and his credit over to research papers published in various international journals. He has worked as an editorial member of the Industrial Journal and was granted the Treasurer of Indian Statistical Association from 2003 to 2014. He is deeply interested in the areas of statistical inference, reliability, survival analysis, and so on. Indeed, it is with great pleasure and honor that I cordially invite you, Professor, to chair the section. Over to you, sir.
Thank you for the nice introduction. Am I audible?
Yes, Professor. Yes.
Okay. Good morning to all of you. Welcome to the special session in the honor of Professor P.C. Mahalanobis. Today is 130th birth anniversary of Professor P.C. Mahalanobis. Today's speaker in this session is Professor T.J. Rao, retired professor from ISI, Calcutta. I am giving very brief introduction of Professor Rao. He MA Mathematics from Andhra University, MStat, PhD from ISI, and the position held, joined ISI in July 1967 and retired on the superannuation in 2005 from ISI, Calcutta. He was a visiting professor at several universities in UK, USA, Australia, Malaysia, etc. from last over 10 years. Adjunct Professor C.R. Rao, Advanced Institute of Mathematics, Statistics and Computer Science during 2009 to 19. Member Secretary, Board of Director, International Statistical Education Center, organized by International Statistical Institute, HOG, and in ISI Calcutta during 1972 to 74. He was head of the division of theoretical statistics and mathematics and member of ISI Governing Council during the year 1984 to 86. He is an elected member of International Statistical Institute, editorial board member in many well-known international journals, member of various university bodies in India, UPSC Chief Examiner for ISS, IFS and similar examination. His research interests are theory and practice of sample surveys, history of official statistics in developing countries. He has more than 125 papers and articles, mostly in sampling theory and some on official statistics in various international and national journals. He has several awards in his career. National Award in Statistics of India in 2016 in the memory of Professor P.V. Sukakme. Honorary Fellow of Andhra Pradesh Academy of Science. I invite Professor T.J. Rao to give a invited talk in the honor of Professor P.C. Malanobis. Thank you.
Thank you.
Welcome.
Namaskar. Am I audible?
Yeah, you're audible.
Okay. Yeah. So let us start.
Professor,
you are presenting?
Yeah, we can share from here. Okay.
Yeah.
Okay. It's okay, Professor.
Yeah. Good morning, everybody. I hope I am audible.
Yeah. Okay.
Today, to fit the day, I just titled it as Remembering Mahalanobis. An alternative title is Why Statistics Day? What is special about the Statistics Day 2023? Next one. Actually, what is the main purpose of Statistics Day? To create awareness in the public about the role of statistics towards human welfare. This year is the 17th Statistics Day and also the 130th birth anniversary of Professor Mahalanobis. Mahalanobis was the chief architect of post-independent statistical system in India. He's a pioneering statistician, founder of the ISI, Sankhya, a world-famous statistical journal, and is well known for his concept of Mahalanobis distance, etc., etc. Next one. What about Statistics Day? Statistics Day, why Statistics Day and who is doing this? It's already started in several other countries. Africa started in the 18th November since 1990, and Japan from 1973, and around 103 countries are celebrating the Statistics Day week or month to raise the profile of official statistics. World Statistics Day, devised by the United Nations Statistical Department on 2010, and it keeps on rotating periodic, as our friend said, every 5 years since then. Next one is 2025, 2010-2025. Why is not India in this list? What's happening? Next one. During the Platinum Jubilee celebration of ISI, former Prime Minister Dr. Manmohan Singh pronounced Maulana Bisi's birthday as Statistics Day to be celebrated at the national level. And hence we started having the Statistics Day. Next one. Let us go back and see what happened. Immediately after independence, we are now having we are following the British system, and we didn't have much of a statistics system of our own. There is a standing committee of Department of Statisticians appointed in 1948, as well as a National Income Committee with PCM, Maulana Bis, as chairman. 18th December 1949, Prime Minister Nehru wanted the sample survey covering the whole country should be organized on a large scale. And Maulana Bis came up with his large-scale sample survey called the National Sample Survey. It was approved by the government in 50, and the National Income Committee recommended the use of sampling techniques to fill the gaps in information. Next one. Excuse me, I think this is not the right one. The slides are something different. Satish Kumar ji. Not this.
Yeah,
is
yeah,
not
no,
it says what is special about Statistics Day? That's the one. Did I not send that? Can you check, please?
I have to check.
Can you check the mail, whatever? What is special about 2023? It seems to be some earlier one in their stock.
Yeah, okay, Professor.
Can you find out from the mail?
Yeah, just to
that will be nice.
Yeah, Professor.
Well, if it's not possible to show these slides, I can lecture, because after all, there is no mathematics in this. So let's try for a couple of minutes more, and let's not waste time. I can read through my slides and just give a lecture.
Just a minute, Professor.
Take your time, and if possible, that'll be nice. Oh, wonderful. Thank you.
Sorry, Professor. Sorry.
Thank you.
Just,
yeah. There is something special about this. That is what I wanted to say. Can it be enlarged a little bit? Okay, this is okay. This is not next one. This is my abstract. Anyway, about which I will be talking. That's it. That's it. Yeah. Why today? To honor and remember Professor Mahalanobis, whose birthday 130th, earlier said 129, that was the last year's, I suppose. Okay. It declared as National Statistic Day 17th. The first celebration was done 2007. Next one. PCM, as I already said, is the chief architect of the post-independent system and the founder of ISI, Sankhya, second five-year plan. His concept of Mahalanobis resistance is very well known, and it is very much used today in ML and AI, which are the buzzwords of today. As I already said, next slide, we already discussed that several countries are already doing that, but India declared a bit late in 2007. And the post-independent statistical system, a brief history tells us that the National Committee, PCM as the chairman, approached the Prime Minister, the then Prime Minister Nehru, who wanted something to be done to collect data. And he devised a technique called National Sample Survey in 1950 for collection of data on a scientific basis. That is important. The other people, economists, were saying that we should do stepwise from the states regarding regular official statistics, but PCM insisted that it should be done through a national sample survey using a scientific basis. That's the important thing. He also was the creator of Central Statistical Organization, and he prepared the second five-year plan, as we all know. It is next one. PCM's tenacity and wisdom that has given statistical world the 73-year-old well-acclaimed phenomenon called NSS, and its data is being used for promotion of better lives through policy decisions and research projects. Economics Nobel 2015, Keaton used NSS data. Welfare economics based on NSS data, Nobel for Amartya Sen, Nobel for Abhijit Banerjee poverty data. All these things are based on the well-known National Sample Survey data. Next one. The surveys greatly helped the government to introduce various reforms for the betterment of society and human welfare. Now fast forward to 2000. To review the statistical system, a report of Rangarajan Commission. Rangarajan Commission was appointed in 2001. They released a report which I call as a treatise on Indian official statistics, covers the modern era of Indian official statistics and offers a variety of suggestions. This was done in 2001, already 20 years old. Most of these recommendations have been implemented by the apex body. It's now still called National Statistical Commission. Now, today's events are something which I wanted to talk. The first event. India's huge footprint in global statistical arena, that is reported in several newspapers. And then some other paper said India has been elected to the highest statistical body, namely the United Nations Statistical Commission. I won't call it UNSC for the confusion that it will be in United Nations Security Council. So it is UNStatCom for a 4-year term beginning January 1 to 2024. All the papers, all the media, all the news situations, they all talked a lot about this, about the India's huge footprint. But what about this? Let's not forget Mahalanobis. Actually, my talk today is to give credits to those people who started a subject, who started a paper, who published a paper. So let us start by giving credit to P.C. Mahalanobis. Let's remember him today. Actually, P.C. Mahalanobis participated in many meetings of the UNSC, UNStatCom, from 1946 to 1970. And even acted as chairman twice, 8th in 1954 and 9th in 1956. So this is not something new. Only thing is that it just got repeated once more. It may be noted that the 19th session was held in New Delhi under the chairmanship of V.R. Rao. V.R. Rao was a classmate of C.R. Rao of Andhra University. He was the DT, Director General at that time, and they organized this 76 one. And later on in 77, we had the session of the ISI in New Delhi, as some of you remember. Now, second big event, I don't have to say anything. Everybody knows the whole of statistical fraternity is rejoicing about it. It's the International Prize in Statistics, ISP 2023, which has been awarded to Professor C.R. Rao. And this is the occasion which the statistical fraternity is rejoicing about and celebrating. Professor Rao's work over 75 years ago, which was published in Bulletin of Calcutta Mathematical Society, and there is no statistics at that time, Calcutta Math Society, 45 when he was 25 years old. it continues to exert a profound influence in statistics and science, as you all know. Next one. In awarding this prize, we celebrate the monumental work of C.R. Rao that not only revolutionized statistical thinking in time, but also continues to exert enormous influence on human understanding of science across the wide spectrum of disciplines. This is what Gay Nation, chair of the International Prize in Statistics Foundation, mentioned in the citation. Next one. 1945 paper includes what we now call as Kremer-Rao-Bound, Rao-Blackwellization, and information geometry. These are the three pillars which led to so much of development recently. Now, in this lecture, I shall concentrate on Rao-Blackwellization, which has application in several fields, such as, there is a big list of fields here in the next slide. I won't read all those things. It's a particle filtering, stadiology, data compression, smoothing, constellation tracker, or Rao-Blackwell as template sampling, quantum, even in quantum mechanics, quantum Rao-Blackwell theorem. And two important things which need our attention is that Rao-Blackwellization has been used in the basketball goals. If somebody is a basketball player, you will know how the goal is done. You have to push the ball and it has to drop in the goal. And Rao-Blackwellization has been applied to that to rank the players, not just rank them as we normally do, but using Rao-Blackwellization, a technique has been devised and its application in sports. And there is also a surprising Rao-Blackwellization WhatsApp, and I'll talk about it later, and a host of others in addition to the sampling theory. Now let me go back to sampling theory. Next one. Inspired by D. Basu's 1958 work on sampling with and without replacement, P.K. Pathak applied Rao-Blackwellization in sampling, especially for PPS without replacement selection. Now, PPS without replacement, probability proportional to size, there is a size measure, and you want to select the units not at random, but with probability proportional to the size, and it can be either with replacement or without replacement. As already it's done by Basu, you go for without replacement. Therefore, you take a probability proportional to size sampling without replacement, revising the size at each stage. The first paper, important one that we know, is made by A.C. Das, who was a research scholar in ISI. And in 1951, what happened was there is an International Statistical Institute session in Delhi. Maharanabi managed to get that done in Delhi. And he also brought a session of that to Calcutta for about 4 or 5 days. It has been arranged in Calcutta as well. And in 1951, that was arranged in Calcutta. A.C. Das, a research scholar, he gave a paper on two-phase sampling. And not only that, he had a small section in that paper on PPS without replacement, which he thought could be tried in national sample surveys. And his estimate at any draw, his estimated depended only on the Y value of that draw and not on the previous draws. Just let us have a look at that one. Next one. As I said, depended only on the Y value. In 1946, after 5 years, Deshraj, who was also in ISI, he gave his ordered estimators for population total Y, which depend not only on the draw selected, but also on the previous draws. Just to look at the example, Das's estimator is you don't find any YI there. Whereas in Deshraj's estimator below, if you can raise it a little bit up, it's just YI plus, etc. So there is a YI in the Deshraj estimator, but not in Das estimator. So if you keep on doing it for the nth draw, the same thing happens. Nth draw, Das estimator has only YN, whereas Deshraj estimator is Y1, Y2, YN, and so on. This Deshraj, I don't know why he missed the Das's reference. It's not at all quoted in that paper. As I said, I am also going to talk about credits, which are to be given to the right author, and what we are missing. Some of the sample survey in all statistics, and also especially in sampling, we tend to miss these credits which are to be given. So next one. Now the next story is that in 1952, a year after this 1951 paper, Horwitz and Thompson gave a general homogeneous estimator. By then, we have got the inclusion probabilities, Godam-based results, and all that thing. Therefore, they have this nice estimator called yi by pi I, where pi I is the inclusion probability of a unit. I don't want to go into the details of that. It's from the design, PS, the selection of a sample. That design, you can compute all those samples which contain the unit and add up, you get the pi I, which is the inclusion probability. So yi by pi I is the Hurwitz-Thompson estimator. With the summation there, summation missing because of my typing. Sigma yi by pi I is the estimate of Hurwitz and Thompson. Now let us follow the story carefully. One more year later, 1953, unaware of what HT obtained, Yates also obtained the same estimator. He estimated the estimator, he got the estimator, but he didn't know how to solve the variance estimation problem. Hurwitz and Thompson gave a variance estimation, which was not positive all the time. So Yates also was trying. And he then looks at his paper and then says that 1951 itself, now look at it, Hurwitz and Thompson gave it 52, but 51 itself, R.D. Narayan published the same result in Journal of Indian Society of Agricultural Statistics. These journals are not perhaps known at that time to others. And J.N.K. Rao rightly called it the NHT estimator, Narayan Hurwitz-Thompson estimator, rather than just HT estimator and so on. But most of us teachers and researchers keep on saying HT estimator, and so on. So credit should be given to NHT. But you look at Yates' paper carefully, it could as well be called as NYHT estimator, because Yates also contributed to this estimator of Hurwitz-Thompson in the next year, unaware of HT estimator. So let us call it NYHT estimator. Next one. Now to improve HT's variance estimator, there is another statistician, Grundy. He joined Yates and he added his variance estimator to Yates' draft. And it's now called, we all call it Yates-Grundy variance estimator 1953. But Yates-Grundy paper acknowledges A.R. Sen, another champion from Indian statisticians. He's published his work again in the Journal of Indian Statistical Society of Agricultural Statistics. He worked on the same estimators, and now some of us researchers, at least in India, we call it SYG, Sen Yates-Grundy variance estimator. Or because Yates did not want to take credit, we have to call it Sen-Grundy variance estimator. Next one. Now, what did Ebenmurthy do? He went back to Desiraj estimator, took the case of n equal to 2 only, sample size 2. It looks very simple. He combined it, and then you just half into this, divide to two ordered estimators. So T bar, based on the I first drawn and J next drawn, now Desiraj estimators gives me that expression there. But if you take the order J first and then I next, you get, instead of I, you start with J, and you get the same thing with the I replaced by J. So you have, Murthy had this T bar Ij based on the order Ij, T bar Ji based on the order Ji. Then he thought of improving the estimator, unordering the estimator. How should he unorder this estimator? Because Raoul is in the application. So he went on giving weights to the next one. So the sample selected Ij has the corresponding weight, and the sample selected Ji has the corresponding weight. So Murthy weighted that and got a weighted estimator, which is called the symmetric Desiraj estimator, given by that expression. Symmetric Ij doesn't matter, you can change it. And this is what we call as Murthy's 1957 estimator. And for the last 75 years, we have been calling it Murthy's estimator. Now let us look at the next one, which we all forgot. Let us see the next one. Everyone missed Murthy's footnote. In his own paper, Murthy had a footnote in page 384, which says, Lahiri is an expert in number theory as well as sampling. He was the champion in the National Sample Survey in the very early days. And he conjectured that Desiraj estimators can be improved by weighting the different ordered estimators by the respective probabilities. And in fact, suggested the estimator given by Murthy. Therefore, should we call it Lahiri-Murthy estimator or still continue to call it Murthy's estimator? So let us call it Lahiri-Murthy's estimator next time when we teach that. Next one. Now, further unorderings. I have discussed this in a recent paper of mine in 2021, how this unordering will help and Raoul correlation plays a very important role and so on. Why unordering? What does it do? Now, sometimes students don't understand this IJ, why should it be different and so on and so forth. And I give them this frivolous example, if you excuse me. Let me announce my example. Suppose you go to a restaurant. Waiter comes and asks, what's your order, sir? So my order is first bring some dahi. So he brings you dahi. Then you eat it, and then after a while he comes and brings some vada. Then after half an hour he comes again, what do you want now, sir? He says, bring vada first. That's the order. Then you say after some time, bring dahi. So the tastes are different. You eat dahi first and then vada next. And later you eat vada first and dahi next. That's a different story at all. But if you eat a dahi vada, which is an ordered thing, it's much better and it's more efficient. So that is essentially how I explain to the students how unordering helps and unordering gives a more efficient and nice estimator. Next one. Now, after these examples, let us look at some of the things that happen to how we collect the data and so on. Let us move to non-response. So far, as far as we have response, we can get the answers and then we can get y1, y2, yn. We can do lots of things about it, get estimates, variance estimates, and so on. But suppose there is people who are not at homes, or your question is sensitive, they don't want to answer. They're missing data. So what do we do? How do you do that? So in the olden days, the old statisticians at US Bureau and so on, they wanted to repeat the calls. You go again second time, you go again third time, and so on. But it's costly and time consuming. So you go to the other households and collect the data again and again. It's costly. It takes time and results won't be published in time. So in 1949, Politz and Simmons, they added a different question along with the regular collection of data. They went to a house and asked them, are you available? Are you at home at the same time during the preceding 5 weeknights? Forget Sunday, 6 days. So I go on Thursday and say, during the last 5 days, at the same time, were you at the house? Because at the same time, they were going every day to collect the data. Then depending on the answers, they wanted to weight it, and then based on that thing, they want to get an estimate. So based on this thing, you know the frequency of these people who are at home, and you inflate the factors so that takes care of they're not at homes. That's the idea which Politz and Simmons published in 1949 in JASA. Next one. But a good researcher will note that, however, in a discussion, if Yates gave a paper in RSS meeting, it's an RSS meeting, famous papers, and which is presented at the society with lots of discussions and so on. 1946, Yates gave a paper, and Hartley in that paper had a comment on Yates' discussion. He said that he proposed a method which is the same as PS technique, Politz Simmons in 1949, but Yates gave it, Hartley suggested it in 1946 itself, and Yates gives credit to Hartley, and he called it the ingenious and decidedly cheaper alternative to callbacks. It's the same thing, but then before Politz and Simmons, Hartley came up with this thing. Next one. In the next year, in the paper, Hartley, Politz and Simmons acknowledged Hartley, but then didn't give much credit to him. They just said that we understand that it is also done by him and so on. Now, let's go back to this Politz-Simmons technique. They're coming to your house and asking you, were you in the home, were you in the house at the same time during the last 5 days? Well, maybe in the 49s and 50s, people were answering that question. But today, if somebody comes to my house, I won't be able to give an answer. Why should anybody know whether my whereabouts? It could be somebody, thieves, trying to enter my house later if they know that I'm not in the house at the same time in the earlier days. Or maybe some divorce case and somebody wants to know where this fellow is going and so on, and that they want to do some detection. There are so many reasons why we don't want to give an answer to such questions. So this is a sensitive question now. So how do you give answers to sensitive questions? So there is, as you know, in 1950, there is known as RRT, 1965 RRT by Warner's randomized response technique, where they have a slight mechanism which gives the answer, randomizes the answer, and then you get the estimate of the corresponding people, proportion of people, etc., like proportion of people who are alcoholics, proportion of people who are black money, etc. There are lots of sensitive questions, and you can get the answers too by these Warner's RRT techniques and so on. And there is one special issue on RRT in 2016, which Professor C.R. Rao and others edited, and to celebrate the 50 years of Warner's RRT. Now, looking at this, what we call as the Hartley-Pollitt-Simmons technique. Next one. R. Sarkar and Bikash and myself, we produced what's known as revised or RRT Pollitt-Simmons technique. Now, what are the other RB applications, raw black validation application? Now, there is a new concept which you are trying to propose, and nowadays, whenever you open your WhatsApp in the morning, there are so many messages. Some of them say good morning, some of them say have a good day, some of them say the God's picture and so on. Today is such and such a day, and so on, and so on. So not many of us may have time to go through all those things and give response. If you are going to an office, or if you're a surgeon and you're going to go to a surgery, if you're a lawyer, you're going to the high court or court to take up a case and so on. If you're a businessman who has to go and start your business, you don't have time to do all these things. So why do you want to waste our time on these things? So one way is to ignore all those things and don't participate in WhatsApp at all. But rather than that, if you want to be in touch with your own people and so on, what we do is we have got the message clustering. So you cluster all the messages, and then there's something called spot response utility. You use the spot response to send the response based on that thing. So what we try to do is you have all the messages. They're all similar. Good morning and how are you, etc., etc. All similar. They all put together. There's a mechanism which is based on AI, and that AI will take care of that. And next one, please. That app, which is to be constructed, compresses the data and disregards repetitions. In that sense, it is raw black hole. There are no repetitions. It compresses the data, and it's so constructed. We'll have a mechanism which recognizes all the equivalents and then presents them in one set, and then you have to answer a simple answer to everyone with thank you very much or whatever you like. Or if you want to do some in a specialized way to some of your friends and so on, then just only answer those things. And there's another thing which happens, and now this conference, luckily Dr. Satish Kumar did not start that. As soon as a conference starts, you have a group to WhatsApp. There are 300 people in that, or 150 people in that, and you keep getting messages, or somebody says happy birthday to X to Y, and that's all not at all wasted. So you don't want to do that, and if there's such a thing happening and so on, instead of wasting one's time and wasting one's computer space and your battery space, it's better to use something like this. It's RB, raw black hole WhatsApp, which has to be constructed. Yes, some people are trying on these things, but I don't know how it comes up. Next one. Now, in view of the compression and reduction of the data and the ability to present sufficient information, we called it the raw black hole WhatsApp. In a strict sense, this concept is not like the research of Daly, Grafstein, and Born 2018. The 2018, I was talking about that sports, basketball throws and so on. They applied these things, and they came up with a very nice reordering of the ranks of the players. Somebody says so and so is the first rank, so it's the second rank, so on and so forth. They took some three variables and they what's known as they took that things, but based on those three variables, they did that got the new application of the rankings, and they are slightly different from the what we think of original. And this technique, if somebody is a good player in cricket or football or whatever, one can use their methodology, but one has to study their methodology in that paper of 2018 and try to understand the sport as well as the method that is used. They must know a bit of statistics as well as the corresponding sport. That new app so constructed reduces redundancy, saves time and effort. And if some company wants to make it premium, they can as well make it. So it's up to them to make that one. Now, my main theme, as I said, one of the main themes today is certain lapses in the literature and credits. Let's go to the lapses in the literature and the credits. Next one. What else to start other than raw equalization, which has suffered this credit problem? Now, most of us around here are familiar with this anecdote, but some of the youngsters here in the audience may not have known this. 1945, CRO published this. Around 1952, 47 CRO did, 45 did this, and in 1952, Sheffer and Laban called it Rao-Blackwell theorem. That's about after about 7 years. And there's a conference in 1953, which CRO attended. I think it is in Israel. Bergson was the speaker, and he called it Blackwellization. And CRO pointed out in the conference that he published it in 1945 itself. Then Bergson replied, Rawization is difficult to say. It's both the tongue twisting and so on. That's why he called it Blackwellization, which is simple to say. But later, of course, he called it raw Blackwellization. Next one. D.V. Lindley, on the other hand, is reviewing a book. Probability proportion to size. We'll come to that later. Now, similarly, in 1944 AMS, Maddow and Meadow gave systematic sampling selection, but when the not Uttar Pradesh, but United Provinces anthropometric survey was done in 1941, Mahalanobis D.N. Mazumdar and C.R. Rao are the three architects of that big anthropometric. Take every alternative individual. Similarly, analysis, Mahalanobis hinted small, and C.R. Rao also in the other Bengal anthropometric survey talks about complex surveys. He says that my sample is not really a random Statistical Association Bulletin. B. Ghosh has a similar idea. He got multivariate regression estimator in the 47 paper itself. Again, not many of us give credit to Ghosh. Murthy Sankhya 1964 has a product method of estimation. Most of the scholars now working on ratio product estimations call it Murthy's product estimator. But Robson, in Journal of American Statistical Association 1957, had the same product method of estimation. Surprisingly, Murthy doesn't refer to Robson in his paper. In JASA, it was different. It's known as Polycase method to get the product method of estimation. Murthy's estimator was something different. Now, as I said, Lahiri gave in 1955 the probability proportional size selection method, but Ikeda, a student of Mitsuno in 1951, Hayek in 1949, Lahiri, Mitsuno, Sen, all of them contributed to this selection. It's called the LMS scheme, nowadays popularly, Lahiri, Mitsuno, Sen scheme. Royal in the Biometrica started predictive theory, and Brewer in 1963 mentioned already about the idea of superpopulation in predictive theory. The next one. That will be the last one. Thank you very much for your attention. I would like to thank Satish Kumar for inviting me and his team for... there
may be a network issue or otherwise it's
okay.
Yeah, wrongly placed.
Okay, any other questions from audience? Okay, if there are no questions from the audience, let us thank the speaker, Professor Rao, for a very interesting and innovative talk. Thank you.
Thank you.
Thank you, Professor Rao, for your very interesting talk. And no doubt it is helpful to our even postgraduate level students are also interested, get several ideas, very interesting anecdotes. Stories, very sharing the session in a very nice way and concluded session in a timely way. Thank you, Professor. Thank you so much.
Yes.
Once again, thanking you, professors, on behalf of the organizers of this conference. Now, thank you, professors. Thank you so much. We expect your support in future also. Now let us move to the next session because I think this is scheduled at 12:05. There is some time. I have to check whether the Professor Carlos Coelho is here in the group. Yes, he's also in the group.
Yeah, he's there.
Yeah.
Yeah.
Yeah. Few minutes, 2-3 minutes, because otherwise some people will be waiting for hearing that talk. Otherwise we will start it a little bit earlier. How is the chair?
Myself.
Okay, Professor. Okay. So by the time, I hope Bhagilakshmi, you can introduce our chair and thereafter hand over the session to the
that is good.
Chair. So he has to say something, and thereafter and please support him for the.
Yes, sir. Hello, everyone. Now we are moving on to the fourth based on extreme rank set sampling published in the American Journal of Mathematics and Statistics. Dr. Biradar is also a member of the Indian Society for Probability and Statistics, International Indian Statistical Association, and Associate Editor of the International Journal of Agriculture and Statistical Science since 2020. We are indeed fortunate to have such an eminent person with us sharing the session today. So it is with great pleasure and honor that I invite you, sir, to chair the session today. Over to you, sir.
Thank you. Thank you, Dr. Bhagilakshmi, and thank you, Professor Satish Kumar. So on the behalf of the organizers, I welcome Professor Carlos Coelho. Is it correct? How to spell Coelho is right, sir?
Yes, it is.
Yeah, I don't know. Yeah, anyhow. So I welcome you on behalf of the organizers. The technical session number 4. I am fortunate to chair this the eminent person's lecture. Professor Carlos, so I would like to introduce briefly.
Carlos is a professor of statistics at the mathematics department, Nova University of Lisbon, Portugal. He holds his PhD in biostatistics by University of Michigan, and his main area of research are mathematical statistics and distribution theory, namely the study and development of exact and near distributions for likelihood ratio test statistics using multivariate analysis. In a 2004 paper published in the Journal of Multivariate Analysis, he laid the foundation for what he called near exact distributions. Since then, there have been almost more than 50 papers published alone on the same paper by the professor. Carlos, of course, he has published many papers, and he is also associate editor of many international, many journals. He is an elected member of International Institute of Statistical Institute and serves as associate editor in the editorial boards of Journal of Applied Statistics, Journal of Statistical Theory and Practice, Journal of Interdisciplinary Mathematics, American Journal of Mathematical and Management Sciences, and many. So his area of mainly, as I said, his area of interest are multivariate analysis, discipline theory, estimation, high dimensional machine learning, and many. I hope his lectures, the researchers will benefit very much from his lectures. Now I'd like to request Professor Carlos to present his paper on a likelihood ratio test of fit for the multivariate linear models in the high dimensional case, application to MANOVA in high dimensions. So over to Professor Carlos Coelho.
Thank you very much.
Sorry for that. You have 35 minutes of time. Now it is 40 minutes of 12:40, and you can present up to 35 minutes or 37 minutes and 3 minutes for a discussion. So is that okay, Professor Satish Kumar?
Yeah.
It's okay, Professor. It's okay.
Okay. Please go ahead, sir.
Okay, thank you very much. I'd like to thank, first of all, Professor Satish Kumar for inviting me, and also Professor Savan Kumar Biradar for chairing this session. So I'll try to start sharing my screen. Okay, let me see.
So,
okay, I'm not sure if you can see my screen now.
It is visible now. Yeah.
Okay. So I'll be presenting some results that I obtained quite recently, that are actually on a test of independence for two groups of variables in a situation where the sample size can be much smaller than the number of variables that are being used. And so actually 1 year ago I presented here a test for the one-way MANOVA, and the main aim of this other one, it is to really develop a test that can be applied in the multi-way MANOVA, and so that also is it possible to be applied to a test and to a model and a submodel, so that we can really end up having the tests for the factors and also for the interactions in the multi-way MANOVA. But in general, we can develop a much wider test that is really a test of independence between two groups of variables. And so the questions that I'll be answering, or at least some of them, are these: is it possible to really develop like a likelihood ratio test for the independence when the sample size is smaller than the number of variables? And if so, would such a test perform well? Will it have, for example, just like in SIGs, a good type 1 error control? It means under H null will the power of the test match or almost match the alpha level? Would it have non-inflated power values? It means power values will be what should be expected and not higher than that, and will it have or not a nice asymptotic distribution? And actually, the answer to all of these questions, it is really yes. We can develop such a test with such performance. Mainly also, if it is applied in the MANOVA setting, will it work with sample sizes that are really small? And the answer is yes. Actually, we can have in each cell just a sample size of 1, as long as in at least one cell sample size is 2 or more. It is able in this MANOVA setting to really outperform existing tests, and it also shows a very good control of the type 1 error. Besides, it may be used with very skewed distributions that are not normal anymore, really. So how can we really reach such a goal? The answer is, if we just set up a covariance matrix that is a common covariance matrix, a positive definite one, what happens is we'll be spending a lot of degrees of freedom estimating variances and covariances. And so the answer is, if I want to really have smaller samples, I should have as hypothesis from the beginning a covariance matrix that can be specified with fewer parameters. And so the solution is to really use what is actually called a circular covariance matrix, because a circular covariance matrix of dimensions p by p can be actually specified by 1 plus floor of p over 2 parameters, which is much fewer than the usual p times p plus 1 over 2 if the covariance matrix is only positive definite. So I just have actually more slides than those that I can handle for the time that I have, so I'll be kind of flying over a few of them, okay? And so the situation is the following one. Up front, I'll be assuming that my variables are normal, but actually then the testing can be applied to non-normal variables, as we will see next. But upfront, I'll be supposing that I'll be assuming that I have a random factor that is normal with some mean value mu and some covariance matrix sigma. The factor is split in 2 parts, x1 and x2. I'll be looking at x1 as being the set of the response variables and x2 as being the set of explanatory variables. And so we'll see that I can have a sample size, say n, that is much smaller than the number of variables in my response set, but it has to be actually larger than the number of variables in my explanatory set. So if I split x in this way, if I split the original random vector in this way, I'm actually splitting this sigma matrix in this way here, where sigma 1, 1 is the various covariance matrix of x1. And it will be this sigma 1, 1 that I'll be assuming as being a circular matrix, okay? So under the normal setting, actually testing for independence between x1 and x2, the 2 subvectors, it is equivalent to be testing the nullity of these sigma 1, 2 or these sigma 2, 1 matrices. So, as I said before, we'll be looking at a model of this type. X1 are my response variables and X2 my explanatory variables. And so I'll be actually carrying out a test of independence that is equivalent to a test between the 2 hypotheses here. H0 it is the empty model, and H1 is exactly this model here. And so if I carry a test between the 2 of them, it is equivalent to carry out a test of independence between X1 and X2. And so we'll be dealing with a situation where n, as I said before, n sample size may be much smaller than the number of my response variables. But anyway, it will have to be larger than the number of my explanatory variables plus 1. We'll see this better a little bit later on. Just only to specify a little bit better, more or less graphically, which is a circular covariance matrix. So as my sigma 1, 1, just let me go back a little bit. It will be this one that I'll be assuming to be a circular covariance matrix. And the circular covariance matrix has this kind of a setup. So the diagonal, all equal elements, and then by diagonals, they go like that. And so they go back sigma 1, sigma 2, sigma 3, sigma 3, sigma 2, sigma 1. And this sigma 1 is that sigma 1. As a mathematical specification, we can specify it like this, but it is easier to look at a graphical setup, and so we can see what is a circular matrix. It may seem it is a very restrictive specification, but actually, as we can see later on, it is not so, because actually this matrix is not that far away from a common positive definite matrix. What happens, it is likelihood ratio test, B matrix. This A and this B are running elements of my original matrix A and my original matrix B. It means I can fabricate, say, from my unstructured matrices, I can fabricate the elements of this A star and B star. The proof of this is a bit long, and it is done in a paper that I published some years ago, and it is not included here because I would not have enough time to show it. But we can estimate A star and B star in this way, and then we can show that determinant of A star and determinant of A star plus B star. Just let me go back, which are those over there. They can be actually obtained also in this way. Also, the proof of this relation is in that paper. It is a rather long one, where these A11 star and so on, these are the diagonal elements of my A double star matrix, and these C are the diagonal elements of my C double star matrix, where C double star is equal to A double star plus B double star, and where this A double star and B double star are these matrices obtained from the original A and B matrices, multiplied on left and on the right hand side by this U matrix. This U matrix is an orthogonal matrix with a running element defined like this. It was shown by Hawking and also by Hawking and Press in a 1969 paper that this U matrix is actually diagonalizing any circular matrix. And although this A and this B are not circular, if we just obtain this A double star and B double star matrices, then from the diagonal elements of A and C double star, we can obtain expressions for the determinants over there. With this result in hand, we can write lambda alternatively in this way, where Vj star and Vj double star are defined in this way. This is a much useful one, because then, since U is diagonalizing a circular matrix, and I'm assuming 6 sigma 1 1 to be a circular matrix, then this will be a diagonal matrix of delta J, say, with this relation between the delta J's. They are equal from the top and from the end. And then this implies that A double star and B double star are Wishart matrices with a diagonal parameter matrix, which in turn is giving us this result, which is a common result for Wishart matrices with a diagonal parameter matrix. And then this AJ and BJ double star, they are independent. The sum is also giving a chi-square. And so I can write, let me go back, this lambda as being actually a product. We can show that statistical or otherwise Stochastically, more precisely, the distribution of lambda is the same as the distribution of the product of these Y matrices, Y random variables. All of them are independent, and each one of them is a beta random variable. We can show that Y1 and Y2 are these beta random variables, and in turn Yj is this one. Are these with j from 2 to p1 minus m, where m is this floor of p1 over 2. And this is clear now from this expression here, that if I want to carry out the test, I only need n greater than p2 plus 1. And there is no relation between n and the number of variables in x1. There is only a relation between n and the number of variables in x2. But x1, it is a set of my response variables. I can have as many variables there as I want. And so I can have n's smaller than the number of variables in x1. I only need n to be larger than the number of variables in x2 plus 1. This is very good because it means if I have the response variables as being, it may be several hundred variables, and if in x2 I just have the indicator variables for my factors and my interactions, it means that I can model, for example, I can have a MANOVA model with many response variables, and I only need the sample size to be larger than the number of indicator variables for my factors and my interactions there. Okay, we can show that there is a very nice asymptotic distribution, a normal one, for this lambda, or rather for its negative logarithm. If I take minus log lambda, then I can standardize it, and we can show that as the number of variables in my response set goes to infinity, I get a normal 0, 1. And it is very interesting because this is really the asymptotic result is a function of the number of variables in my response set and not a function of sample size, which is very nice because it means I may have as small as a sample size as it is possible, and still the normal asymptotic distribution is holding because it is holding on the number of variables on my response set and not on sample size. The proof is not so long, but all this is actually based in logarithms of my y variables we just saw a while back, and so all these expressions are really coming out of the expected values and variances of these logarithms of my yj variables. And I don't have time to show the proof, although it is a rather simple one. It's here. I can send slides later if you may be interested in that. So, as I said a number of times, we'll be looking at x1 as being the response variables, at x2 as being the explanatory variables. And so, a nice setup for carrying out the test, it is a MANOVA model, which may be a one-way or a multi-way MANOVA with several factors and interactions, or even a Markova model. It means a multivariate analysis of covariance model, where x2 is a set of indicator variables for my factors, and also some continuous variables that are working as covariates in my model. It is shown in a number of situations. For example, Sager is really showing that we only need normality of one of x1 or x2. And so I can assume normality for x1, my response variables, and then x2 may be a set of indicator variables. And still the distribution of lambda is exactly the same. Okay? To just get some comparisons, and I'm sorry, I'm not sure how much time I still have. Can you tell me how much time I still have? I'm not sure I am reaching you there. I cannot hear you.
Yeah, Professor. We can hear you.
Yeah.
You can spend up to 12:40, Professor. So about 18 minutes remains.
Okay, thank you very much. I chose these 4 tests to compare with my test for just the one-way MANOVA. And the reason is all these are only applicable for the one-way MANOVA, and even some of them, they are only applicable for a situation where I just have a factor with only the 2 levels, and so I'll be using them in that situation. And so the tests are these. I don't have much time to go through, but the Fujikoshi et al. Test is using this kind of a statistic that is asymptotically a normal 0-1. Shot is using this one, and so on. Okay, for these tests, I used a set of 32 response variables. I used a sample size of 4 for each set. I'm only using 2 sets. It means I am using 1 factor with only the 2 levels. In each level, a sample size of 4, and I have 32 variables. And so under H1, what happens, it is every 4th variable of these, I just increment it by a bit that is stated in each case. So that we can see that we can use the test with variables that are not forcedly normal random variables. I used it with this uniform distribution from Cook and Johnson. This is a distribution that has marginal uniforms, but jointly they are not uniform random variables. They are very skewed actually. But so even for this, so this is the LRT that was developed there. These are the other tests. What happens, it is that under H0 for alpha equals 0.01, the optimal result would be we could get a power equal to alpha. What happens, it is if I use the exact distribution or the asymptotic distribution for the LRT, I get values that are really close to the nominal value of alpha, either for alpha 0.01 or alpha 0.05. But what happens, it is all the other tests are really giving very much inflated values or otherwise very much deflated values, okay? And so then under H1, I set up a shift of 0.35 in each variable, in every 4th variable. And then the LRT is giving these values of power. This is simulated, it means these are done for 50,000 repetitions for 50,000 simulations. And so what happens, it is I can assume 50,000 as being the true distribution of my statistic. And so I can, under H1, compute the power from the set of values that I obtained from H0. And that is what I called simulated. The optimal result will be that my distributions, either asymptotic or exact, would really match this value. And it happens that for the LRT, the exact distribution is very closely matching the results for the simulation, but not for the other tests. And so it means they should report something close to these values here, but they report these values for power. It means that systematically, 3 of them, they report very much inflated values for power, which is not good because we think we are getting this power, but actually the test is getting this power. We can also see that Fujikoshi et al. And Shot, the 2 tests are exactly the same because simulated power is exactly always the same. And some other cases, we just get a very much deflated value for power, almost 0, instead of getting the nominal power that we should get. This is a situation where the correlation is around 0.5. If the correlation is really increasing, the situation is much similar with a somewhat better result for the LRT. The powers increase a little bit, still quite close to the simulated power. And for the other tests, the power is really decreasing instead of increasing because they don't deal well with correlations that are a bit large. And what happens, it is still the values are very much inflated because they are much larger than the simulated values. This is a graphical representation. This is the histograms of 50,000 values of likelihood ratio test or other tests. And so this is the exact distribution. This is the asymptotic normal. And so we can see they closely match the histogram of the values, which is not the case with the other tests that show very much displaced asymptotic distribution in terms of the histogram of the values. And so this is for the first case, rho equal 0.5. For the other case, it is a much similar scenery with the likelihood ratio test distributions matching well the histograms, but not being the case for the other tests. One other example, it is a Burr distribution, a multivariate Burr. We just get a bivariate representation to see it is a very much skewed distribution. Even in this case, the LRT is reporting values that are a bit low for the power under H0 for the exact, but for the asymptotic, it is a quite good result, actually. The other, they report either very much inflated values or otherwise deflated values. And then under H1, we get a power for the likelihood ratio test that is rather close to simulated power. But for the other tests, the power is very much inflated because it is much larger than the simulated values, really. And so a similar situation with the distributions for the tests there. Okay, what happens it is, but we are actually interested in situations where I have a multi-way maneuver, for example. I mean in situations where my original model is something like this, the explanatory variables x2, the response in x1, and then I take away some of my explanatory variables. It means I take away some of the indicator variables for a factor or for an interaction, for example. And so I get my original model in H1, I get my submodel in H0 star, and I get my empty model in H0. And I want to carry out a test between the model in H1 and the model in H0 star. It means I want a test between my original and my submodel. In case I don't reject my submodel in H0 star, it means that the explanatory variables I took away were not significant. It means the two tests are more or less the same. Their fit is similar, and so it means that the factor or the interaction whose indicator variables were really taken away were not significant in my model. And so I can have a test of significance for factors or for interactions or for covariates by building a test between H1 and H0 star. I don't have much time to show it, but we can show that it is I can set up a likelihood ratio test, which is actually a ratio of several likelihoods, and it will have a similar structure to the original test. Of course, the matrices involved are different. These are blocks of my original V matrix defined in this way. Just let me go back one slide. It means that my V11, that is the MLE of sigma 11, is still the same, but I'm splitting these matrices here. The part 1, 2 is the part that is staying in my submodel. In my submodel, I have this part of variables and variances and covariances, and the whole thing is the whole thing for my original model, and the submodel is only taking this part here. Those other variables are going away in my submodel. And so the likelihood ratio statistic may be shown to be this one, and then just jumping this a little bit further ahead, we can show that it can be written alternatively in this way, where these are the Vj star are the Vj star on the original lambda I've shown a while ago, and these Vj 3 stars are these, where this matrix is the Cj 3 star. Sorry. Yeah, where I have these metrics that are involved there. The problem is in getting the distribution of this likelihood ratio statistic. We just have to make a few assumptions. One of them is that these metrics will be a circular matrix, which is the case in many situations, but not always the case. Or otherwise, we should assume independence of some other matrices, which is very interesting. It is that in either case, we just get the same distribution for lambda. And so we can see this as being relaxed assumptions. My C3 star back there was equal to A3 star plus B3 star, where this A3 star matrix is this one here. It means this is the same U orthogonal matrix I used a while ago, and this is V1, 1, 2, and so this is my B3 star matrix, this one here, and so they are once again Wishart matrices of dimension P1 by P1, and with a parameter matrix that is this delta matrix that is exactly the same as before. And so we can show that these are chi-squares, and so they are independent, and so the CJJ3 star, that is this one plus that one, it is this one here, this is the CJJ3 star, is also a chi-square, and so we just get, using a similar argument to the one used before, we can show that, likelihood ratio statistic has the same distribution as a product, once again, of independent beta random variables, where now the distribution is a bit similar to what it was a while ago, only that here I get the P22 instead of the P2. P2 is the number of overall explanatory variables in my original model. The P22 is the number of explanatory variables in my submodel. Okay, and so the distribution is only slightly different. This appears now where before I had the P2, but so I can get a similar result for an asymptotic distribution. These are other results, I don't have time to go through them. And so what happens is we can show that there is a similar result in terms of an asymptotic normal distribution, that once again it is asymptotic on the number of variables on my explanatory set, on my response set. It means there is no relation with sample size, there is no relation with the number of explanatory variables. It means that the quality of my asymptotic distribution, even for the test between the original and the submodel, it is only a function of the number of variables in my response set, and the more variables I have there, the better is the approximation of the asymptotic distribution. It would be good to just get some simulation results. Here I got a number of response variables equal to 55 to just make it a bit different. A model with two factors, factor one with two levels, and it was set up as having a non-significant effect, and factor two with three levels, and it was set up having a significant effect. This is run for 50,000 replications, okay, and I just have an overall number of 12 observations. It means my n is equal to 12 because I have 6 cells, and so in each cell I have a sample size of only 2. And so I have 6 cells, 2 observations in each cell. It means in the overall I have only 12 observations for 55 response variables. And so the results were like this. Okay, this is a situation under the situation for which the test was developed. It means X1 is normal and it has a circular covariance matrix. And so here what happens, this is the test for interaction. What happens is that interaction should not be significant, okay, because I did not say it, but factor 1 should be non-significant, factor 2 should be significant, but in all cases, I set up the interaction as being non-significant. And so the test for interaction is really giving exactly and asymptotic p-values very close to the nominal values of alpha as it should be. Because if it is not significant, the p-value should be equal to alpha, and it is really close both for the exact and the asymptotic distribution. For the test of independence, of course, I get rejection of my H0 because the interaction is not significant. Factor 1 is not significant, but factor 2 is significant. So I don't have independence between x1 and x2. Okay? The test for factor 1, the factor that was not significant, is also giving p-values very close to alpha as it should be, because the factor is not significant. And for factor 2, which was a significant factor, I get p-values that are quite larger than alpha, showing that there is some significance. Instead of 0.01 that has my alpha level, I get 0.059 for my exact and 0.081 for my asymptotic distribution. The asymptotic distribution is giving values a little bit away because P1 is only 55 and I have a number of variables in play and I get a few indicator variables. And so in that situation, the asymptotic distribution is working not so well because I need larger values of the number of response variables for the asymptotic distribution to be really close to the exact one. But anyway, this is working as it was expected. What happens if X1 is still normal, but with a positive definite covariance matrix? This is out of the original assumption for my model, because I was assuming that X1 had a circular covariance matrix. Okay, the situation is not so bad, although now I start getting a little bit inflated p-values. The interaction is not significant. I should have the p-values equal to my alpha values, and they are a little bit larger. It happens exactly the same with very similar values for my factor 1, which was also non-significant. And now for factor 2, that is the significant one, okay, I get somewhat larger values than my alpha value, indicating that factor 2 is really significant. But what happens is if I run away from the assumptions of my model, I start getting a little bit inflated values even under H0. But this is kind of normal, actually. What happens if X1 has a t-distribution with 5 degrees of freedom? This is not anymore normal, of course, and so the tails are getting a bit heavy because the number of degrees of freedom is a bit low. And moreover, I am using a positive definite matrix and not a circular one. What happens it is not so bad, because the situation is very similar to a normal distribution with a positive definite covariance matrix. It means the 5 degrees of freedom, the heavier tail is not damaging that much the test itself. And for factor 2, because these are not significant, it should be close to my alpha values. And for the significant factor, I get some significance now a little bit lower than for the normal case. But this is also normal because the tails are heavy now. So please tell me if I go over time. Sorry?
Yeah, please, you are telling something. Yeah.
How much time?
Yeah, actually, your time is over. You can take a couple of minutes.
Okay.
Your time is over now, but you can take a couple of minutes till you want to present.
Okay. I'll be finishing soon. And so for a very much skewed distribution, still it is not so bad. Now the p-values are a bit deflated under H0, but under H1 I get a very good significance. So as an overall comment, I can say that the likelihood ratio test works quite well for a large array of underlying distributions. It means skewed one, heavy tails one. It keeps a good control of the type 1 error, can be applied with very small samples. It has an exact distribution. It has an exact distribution which may be easily used, and it has a normal asymptotic distribution that is quite good and is not a function of sample size. So thank you very much.
Thank you. Okay, thank you, Professor, for a nice lectures, and you have covered various testing problems, likelihood test problems, but assuming the normality. Now I request the distinguished audience, if you have any questions, you can raise a couple of questions. So if there are no questions, then I have one question. Suppose instead of assuming the normality, so what happens if it is, for high dimensional data, I don't know about this field, but if it is not normal, then what would be the situations?
Yeah, I just show all these distributions that I have shown now. They are actually not normal because this one
data is from normal. Distribution of the test statistics is different. Yeah. But
this one is very skewed, and it is doing rather well, and also the T is not normal, and it is doing rather well. It means if they are not normal, if they are heavy-tailed, or otherwise if they are very skewed, the results are very similar to the results that are obtained for the normal distributions anyway.
Okay, fine. So is there any question? So yeah, please, Professor Dilip Ghosh has a question. Please go ahead, Professor.
I found that for any value of alpha, the value under exact is always less than asymptotic for all the factor 1 and factor 2. Is it always true?
Yeah, I think your question is why 2 was always significant. Is it?
No, sir. Under exact, the value for all alpha is always less than asymptotic. Either factor 1 or factor 2. So is it always true?
I think so. I cannot show it analytically, but it is true that in all cases, the power that was given by the asymptotic distribution, it was really higher. And I think it is because the asymptotic distribution is a bit off, because the number of variables was only 55 in X1, and I got a couple of factors with the interaction. I got a few, how can I say, I got a small confusion in X2 because I got more than one factor. And so the asymptotic distribution is a little bit offside. And so usually the power values were really larger always, yes.
Okay, thank you.
Yeah, any question? So if there are no questions, then I thank Professor Carlos Coelho for a nice lecture. And on behalf of the organizers, Professor Satish Kumar. So thank you, Professor, over the lecture of current interest and covered various problems. So thank you very much on behalf of the organizers. Thank you very much. I think Professor Satish Kumar will say a couple of words.
Thank you, Professor Carlos Coelho, for a very wonderful talk. In fact, very interesting. And we are very much grateful to you, Professor, for your deliberations in the conference.
Thank you.
Thank you so much.
Yeah, I also thank organizers for giving me an opportunity to chair such a, thankful to you. The distinguished professor's talk. Thank you, Professor Satish Kumar.
In fact, on behalf of the organizing committee, we extend our gratitude to you, Professor, for sharing the session.
Thank you.
And thank you, Professor.
Yeah, thank you. So this it will go to the next session. Okay,
yeah, we have time is little bit 1 or 2 minutes left. I think our beloved professors, Professor Harivaran sir and Professor Ghosh sir, here in the group, and everyone are waiting for the next talk. Anjana, please introduce the chair and please support him for the further proceedings.
Yes, sir. Warm greetings to everyone. We shall move on to the technical session 5 of WSTA 2023, which is a plenary session to be chaired by Professor G. Arivaratnan. Professor is a UGC Emeritus Fellow from the Department of Statistics, Manoanmaniam Sundarana University, Tirunelveli, India, with over 4 decades of teaching experience. He was the head to the Department of Applied Mathematics and Statistics, Madurai Kamaraj University, as well as a chairperson to the School of Mathematics, MKU. Professor Arivaratnan was granted the CSIR Emeritus Scientist from 2012 to 2017 and is an elected Fellow of the Academy of Sciences, Chennai, and a Fellow of the Royal Statistical Society, UK. He is deeply invested in the domains of stochastic modeling of inventory systems, applied statistics, optimization techniques, stochastic processes, as well as statistical computing. Professor Arivaratnan has about 100 research papers published in various international journals to his credit and has organized several international conferences, national seminars, and workshops. He is also a life member of IISA, IBS, IAPQR, Indian Society for Medical Statistics, and a member of the Operational Research Society of India. We feel really fortunate to have you, Professor, chairing the session today. So without further ado, over to you.
Welcome.
Yeah. Thanks to Professor Satish Kumar for inviting me to this conference. Good afternoon to everybody. I welcome Professor Ghosh. I am very happy to chair this session in which Dr. Ghosh is presenting his knowledge for the benefit of us. I take this as an honor. I have met Professor in various conferences and in some national level meetings. He's a very nice person and highly knowledgeable. I am very happy to introduce him, though he is well known in the academic circle. But I would like to say a few of many laurels about Dr. Ghosh. Dr. Ghosh did his BSc and MSc in statistics from Bhagalpur University, Bihar, and PhD in statistics with specialization in design of experiments from ISA Delhi Center under Professor M. Das. Dr. Ghosh was professor and head of the Department of Statistics, Saurashtra University, Rajkot since 1986. He was awarded UGC BSR Faculty Fellow after his retirement. His academic and administrative experiences span 44 years. He has got published research papers for more than 150. He has supervised 43 PhD theses, wrote 3 books. He has visited University of West Florida, University of Manitoba, University of Ohio, Chicago, and so on. There are many more universities. It's very difficult to list all of them. He has presented many papers in conferences abroad. He is a member of editor boards in 10 journals. He is a life member of 10 professional societies. He has carried out 2 major research projects. He acted as a selection committee member in many universities. With this short introduction, I invite Professor Ghosh to present his ideas on partial diagonal crosses using resolvable semi-regular group divisible design. Professor Ghosh, please.
Thank you, Dr. Arvindam. And we have a really very long association with him.
Yes.
Several places, several meetings we have made, we have worked. Good acknowledgement for me.
Yes,
and
yes.
we will meet sure again somewhere. Now I thanks to Professor Satish Kumar, who really tired some efforts. He is continuing this webinar since last many years, and he is giving a good opportunity to us to share our some work before a galaxy of the statistician in the world. Thing. But in the same time, I must thank to our ex-Prime Minister Dr. Manmohan Singh ji, by whom we are able to celebrate National Statistical Day, because many Prime Ministers came, but no one declared this as a Statistical Day. So he is a pioneer, and that we are able to gather together on one day, that is on the birthday of Professor renowned statistician Professor Mahalanobis, the founder of Indian statistician. And several people has told about him. I'm not going to him, but due to two persons, Professor Mahalanobis and Professor Manmohan Singh, we are here to share our activity with you. So my talk is it is not coming, sharing.
It is coming, but not. Yeah, not in the readable form. In fact,
You
it is
presented the whole screen desktop, sir. Better you present only that window.
And move to this side.
Yeah. You please come out and present a window, not the desktop. Please present only a window, not desktop. Please open your presentation in the window, then come over here.
Yeah.
It has come?
No, sir. No, sir. Please open and now start presenting it.
No share.
No.
To share. Share.
Please share a window.
Now it is coming. But now you have to move to that open slides.
Please. Yeah.
You
have got infinite windows.
Mm-hmm.
But
again,
you present not the desktop, Professor. You should present only a window. You open the presentation in a window. Then come over here.
No, a window.
Yeah, window.
And then
meet you must have already opened that.
Yeah,
window.
I opened.
Yeah, now come to the present now button. At the bottom, there is a present now button.
Yeah.
No. Yeah, presenting the desktop. Please try to select a window.
I'm starting again. I don't know why. What happened?
No. You opened your presentation in a window.
It has come?
No, not
after that. You come to this window. Click the present now button. You keep your presentation in a window first.
Not your entire screen?
No. Okay, if you do it, this screen will go out. That's the problem. You won't see yourself.
See what is happening.
This is called the infinity error.
I'm again closing, again starting.
Yeah, that's better. You go to your presentation, keep it in a Windows browser.
Whether you selected the entire screen, sir?
You should select only a window. Otherwise, infinite error will come.
In case of any difficulty, you can share to me, send to me, and we can present from here. Professor.
Yeah, that's good.
Now it is okay, but you have to move to the slides.
Yeah, bottom, you can go to the.
Yeah.
You go to your bottom.
Sorry, sir, his mic is not properly working because.
So unmute the mic, Professor.
Sir, please unmute your mic, sir. Sir, please unmute your mic, Dilip, sir.
Just let us wait. I think there is some network issue with him. Yeah, he joined.
Now he's joined, sir.
Can you guide me? I'll go to entire screen or window tab.
Yeah, Professor.
Tab or window?
That upward arrow.
Window.
Click on entire screen. Then click on that middle portion so that the share button will be active. Yeah, now we can move to the slides. Yeah, okay. Yeah, now it is fine.
It has come.
We can make it. Yeah, it is now reached. We can make it full screen if possible.
Okay, sir. Thank you.
Yeah. Okay, it is fine. Can make it full screen.
In this talk, we will discuss two main points. That is, actually, a dial cross experiment is used by plant breeder in the plant experiment and animal husbandry experiment. So they generally select the experiment with smaller lines. So my idea is to explain here, if you have a line, and with this line, you have several experiments under different blocks. Now, which experiment you should select so that they can get the better results? So first, I want to use some introduction of dial cross experiment. So dial cross play an important role in evaluating the breeding potential of genetic material in plant and animal breeding. A complete dial cross design involves equal number of occurrences of each of the p into p minus 1 by 2 distinct crosses, where p is the inbred lines. Let R denote the number of times that each cross occurs in a complete dial. Then such an experiment requires R times p into p minus 1 by 2 experimental units, or we can say crosses. But if p is very large, it becomes impractical to carry out a CDC plan even for a smaller number of replication, that is R is equal to 1. In such situation, we consider another type of dial crosses, which we generally call the partial dial cross or PDC designs. Here, I will give example of both CDC plan and PDC plan both with a fixed number of lines, and we can see which will be better for the researchers. In plant breeding experiment, the genetic properties of inbred lines are experimented by carrying out the diallel crosses plants. Here we will discuss the diallel crosses plant of Griffith system 4. There are 1, 2, 3, 4 system is there. So we are discussing only system 4, where the crosses are of I cross J, where I is always less than J. And I is not equal to J is equal to 1 to P, where P is the number of lines. And N denotes the total number of lines. In the literature, PDC design have been discussed for N is equal to total number of crosses is equal to PS by 2. So in the CDC plan, total number of crosses is P into P minus 1 by 2. But in case of PDC plan, it is PS by 2. And PS by 2 is always less than or equal to P into P minus 1 by 2. Where S is less than P minus 2. Now we have the total number of cross, we have the P, so we can find out S from this expression. And it is also a condition that S is equal to 2 by NP, and this must be an integer. Now these are the following person who has used and discussed the PDC plan, their properties, the analysis. So firstly, it was started by, in fact, we can say Camthorne and Carnot 61, and then it was followed by Carnot himself 63. But basic idea came from the Hinckelman and Camthorne 63 paper. However, Singh and Hinckelman, they discussed the efficiency criteria of partially diallel cross plan comparing to the CDC plan as well as the randomized block designs. So we will be using their criteria for finding the efficiency. Now, PDC design can themselves be quite large, and it is sometimes desirable to use a block design for experimental rather than completely randomized design. Here, I have used both the techniques, the PDC plan under completely randomized design as well as under incomplete block designs. And we will say what is the proofs for under both the criteria. Their resulting design have distinct cross appearing either R is greater than or equal to 2 times in the design. So here also I have taken R is equal to 1 times or R is equal to 2 times. These two types of I have taken in this our investigation. Now, actually, in our contracts, Agrawal Das was the first person, that was happened to be my guide, who constructed incomplete block design for partial diallel crosses. After there, several methods of obtaining PDC plan along with efficiency factor have been done by Camthorne, Carnot, Hinckelman, Camthorne, Fife and Gilbert, Arya, Singh and Hinckelman, etc. Now, Gupta et al. Described the single replicate orthogonal block design using circulant plan, and it was also followed by Singh et al. And then Varghese in 2005 discussed the use of partially balanced incomplete block design in partial diallel crosses plan. Das, Asif and Choi and myself, my one student, they discussed the various methods of obtaining partial diallel cross plan also. Plant and animal breeders use the complete diallel cross plan to investigate all possible single cross among a group of inbreds. Several researchers have focused on partial diallel cross, which are a subset of full diallel crosses throughout the last 3 decades. Now, this is the main idea here, that Camthorne Carnot cited the following advantage of using partial diallel among a large number of parents over making all possible crosses among a similar selected number of parents. Number one, the general combining ability of the parents can be estimated more accurately. Second, the selection can be made among crosses from a wider range of parents. And the last is the general combining abilities of a larger number of parents can be estimated. Although each parent will be assessed with a low degree of precision, the more severe selection that may be applied to the parents may result in a large genetic improvements. And we have discussed in the method of construction of partial layer cross with two associate class PBIB design. And then me and Divicha and my guide carried out construction of partial layer cross for incomplete block design. Here we are constructing using the partial balanced incomplete block design, but considering as a resolvable balance design. So this is some preliminary results which we must explain before starting the construction. We consider diagonal cross experiment involving P inbred lines, giving rise to a total number of NC is equal to P into P minus 1 by 2 possible distinct cross. And all the cross I is less than J. Let RDI denote the number of times the ith cross appears in a design, say Di, where I is equal to 1 to P into P minus by 2. And similarly, let SDJ denote the total number of times that jth line occurs among the crosses in the design D, where J is equal to 1 to P, P is number of lines. Again, you can define RD as a diagonal matrix of RD1 to RDNC, and similarly SD as a diagonal vector of the SD1 to SDP, and let N denote the number of crosses in the design. Then naturally we can find out a vector of 1 prime NC into RD will be always total number of crosses, or that is a vector of 1 P prime into SP. So this is giving the total number of cross, where 1T denotes a T-component column vector of all ones, and 1P prime denotes the transpose of the vector 1 with P component. Now let us have a model. So this is our model that Yij is equal to mu plus Gi plus Gj plus Eij. What is Yij? It denotes the response obtained from the cross I into J. Mu is the general mean. Gi is the general combining ability effects of the ith lines, and Gj is the general combined effect of the jth line, and Ei is the error which is distributed normally with mean 0 and variance sigma square. Now if I want to write it in the matrix notation, that can be written in this form, that Y is a vector is equal to mu times 1P, 1P is a vector of P components, plus delta 1G, delta 1 is a matrix, G is a vector, plus delta 2B plus E. That mu is the overall mean, 1P is a P component vector of ones, and G is equal to a vector of G1 to do of P general combining ability effects, and beta is equal to is the B block effect. And delta 1, delta 2 are the corresponding design matrix of N cross P incident matrix and N cross B incident matrix respectively. That is, that the ith element of delta 1 will be E if the ith observer is present in the jth line, otherwise 0. Similarly, for the delta 2, ith element of delta 2 is 1 if the ith observation is present in the jth block, otherwise 0. And E is a random vector of error component that takes care of a specific combining ability effect. But here one thing I want to say, we are not going to estimate the specific combining ability effect as we are pulling it in the error components. As usual, the analysis of PDC explained, it is assumed that the genetic effect of the cross Ij is represented sufficiently well by the general combining ability effect of two potential lines that is referred by Singh and Hinkle pen paper. Now let us have a design D where P is the number of line, B is the number of blocks, and K is the number of crosses per blocks. The class of all block design with P line, B block, and with K crosses. Now for a D block design, D belongs to always D PBK under the given model. In that case, the information matrix for the to estimate G is given by CD in the information matrix of design D is equal to GD minus ND prime by K. What is GD? GD is a matrix where the diagonal element will be number of line occurs and off diagonal element will be the number of crosses occurs from 1 to P. And that ND is a incident matrix of design D, and ND is a transpose of the matrix ND, and K is the number of crosses. And then it is happy to assume that and observe that product of delta 1 prime delta 1 always give the matrix G matrix of Dij. Similarly, delta 1 prime delta 2 gives the incident matrix of ND. This is already proved it. Now, after using these things, I can obtain a normal equation to obtain general combining algebraic effect, and the normal equation is defined as the CD times G estimate is equal to Q, where Q is a vector and defined as T vector minus ND K inverse B, and T is a vector of the totals and B is a vector block totals. Now, GD that can be also explained at the matrix of this is a sum matrix, WDA matrix, and this is also a matrix. Now we'll go to the construction side. So let us consider a resolvable semi-regular group design which parameter VBRK lambda N1, lambda 2, N2, M, and N. N is a number of groups, N is a number of treatment in each groups. Since it is one resolvable, hence it has R groups, and further each group contains each of the treatment only once because R is 1. Select one group that has 2 treatments. I have taken block size K is equal to 2 for this experiment. In each of the B by R blocks, now cross the 2 treatments of the first block and keep it in one block as first cross. Next, take another block in the group and cross it and keep them in the same block as second cross. Continue this process for all the B by Rth block and cross them and keep them in the same block as B by Rth cross. This way, one block will contain B by R crosses. Continue the same process for each block of the R groups. This will give a partial R cross with B, means R into B by R equals B crosses at total number of crosses. B by R crosses in each block, each line will occur R times. We can observe that the number of times cross like Ij will occur a lambda 1 times, and cross like 1j will occur lambda 2 times. This lambda 1 will be 0, 1, 2, and lambda 2 will be 0, 1, 2. Finally, we can construct a partial Jolly cross plan with B crosses arranged B by R blocks. This is an experiment design. So this I have taken V is equal to 6. V means number of line P also. But in design we call V, but in Jolly cross we call P. So you can say K is equal to 2. So when lambda 1, 0, it means with any line 1, all the line will not occur. So some line will occur 1 time and some line will occur 0 time. That's why lambda 1, 0, and lambda 2, 1. Now since I have R is equal to 3, so we have 3 groups, 1 group, 2 groups, and 3 groups. And it is one resolvable. So each group has all the treatments occurring only once, that you can see, all the groups. So 3 groups, all treatment occurs once and only once. Now I can take one block and cross them as a line. So this we got 1 cross 2, 1 cross 6, and 1 cross 4. And this we are keeping in one block. Similarly, 3 cross 4, And why not I'm taking 3 cross 2? Because we have already assumed that I is less than 2. So always it will be 2 into 3. 3, that is now 5, 4 means 4 cross 5, 1 cross 4, 3 cross 6, and this is 2 cross 5. So we got now 3, 3, 6, 9 crosses. Now what should happen if I have taken CDC plan? Should I P into P minus 1 by 2? Means 6 into 5 by 2 should have 15 cross. Instead of 15 cross, I have taken 9 cross as it is a PDC plan. So 9 is always less than the 15. Now, if I take the incident matrix, you have the 3 blocks, and each block we can say all the lines occurs. You can say all the lines occurs. 1, 2, 3, 4, 5, 6 line, 1, 2, 3, 4, 5, 1, 2, 3. So in all the 3 blocks, each line occurs. So this is our incident matrix for the process. And we can say that each block contains all the treatment. So we are arranging, and that is a CD matrix we can find out by using that techniques. GD minus n, we got this 3 is the number of crosses K. Now, after solving all these things, I want to find out the eigenvalues. Eigenvalue, I got 2 types. That one is 3 with multiplicity 4, and then it is 0 with multiplicity 1. Because this is a positive semi-different matrix. So B is 6. So naturally, there will be 5 eigenvalues. And that is the DCA effect defined as 1 by theta 1 qi. And since theta is 3, so 1 by 3 and then is 0, we got this. So we got the DCA effect. Now come to the variance of 2-line effect. That is 2 by theta 1 is 2 by 3 sigma square. And another eigenvalue 0. So that variance will be 0. So for those lines which occurs with the line 1 will be 2 by 3 times. And for those lines which is not occurring with a treatment, I will be 0. So because of this, since there are 2 types of variances, so I have to find out average variances. So average variance can be obtained by using techniques V1 N1 plus V2 N2 by N1 N2. N1 N2 are the multiplicity of the eigenvalues of the C matrices. So after using all this, for that example, I can find out that this is giving us 8 by 50. Now, I got, this is the main point to find out efficiency factor. Why? Because I told you if B is equal to a fixed number of lines, we can construct a number of PDC plan under different blocks. But which should be considered as a block? Here I'm not giving a importance of optimality criteria, because optimality criteria only say this is a optimal, A, D, E, or universal optimal, or so many 5 MS. But it doesn't give the which we can use it. So there are 4 PDC plans, all 4 are optimal, but which I can select. But efficiency factor can give a best idea which can be selected. So this is the effect. So Griffin gave efficiency criteria in this way, that the variance of the 2-line effects are always denoted by 1 by R times P minus 2, where R is the number of times each cross is repeated. Here I saw only 1 time it is repeated, so R is equal to 1. So variance of the line effect is equal to 1 by P minus 2 sigma square. And solving after all these things, I got efficiency factor as 0.46675. We have already told earlier also the efficiency factor of the PDC plan will be smaller compared to the efficiency factor of the CDC plan, because we are not considering all the crosses. Now, this is a CDC plan comparing the PDC. But now we want to compare this plan with the randomized block design. When we want to compare randomized block design, so that is use this techniques. And this techniques is nothing but the E star is equal to EP into P minus 1 by S, where S is the number of crosses. See, in the PDC plan, our number of crosses was, if you remember, NS by 2. So N was 18, total number of crosses 9. So 9 into by 2 is 9. Naturally, S is coming 3. So S is 3. So P is equal to 6. And 6 minus 1 is 5. S is 3. And EP we got earlier. So we got the 0.7%. So 80%. You can say when I compare this thing with the randomized block design, the efficiency of the PDC plan we got is 80%. Whereas comparing with the CDC, we got only the 40%. I just one example. This is the CDC plan I have taken for sale. Since we have time only 4 to 5 minutes, I will just go to one other idea only, which I want to explain. With this CDC plan, I got C efficiency 1. So for with same P is equal to 6, I constructed PDC plan and CDC plan. For PDC plan, I got efficiency at 80%, but for CDC plan 1. So this shows that if CDC plan is available, go for the CDC plan, otherwise go to the PDC plan. Again, I just want more example I want to take. I will take 3-4 minutes, not more. So this is I have taken another example of PDC. This is very interesting. Just morning only I just got this result. See what I have done. This is a natural odd number, 1, 3, 5, and this is a natural even number, 2, 4, 6. I have taken reverse. When I took it 2, 4, 6, I couldn't get the results. But when I took it 6, 4, 2, I got the exact result. This is just today morning I have solved this problem. So now I crossed this. After crossing, I got it this crosses. And there I found that each crosses occurs 2 times. And since it is each block contains all the lines, so it is organized in complete randomized block design. And here, just I want to this only, I will stop it. So when I got efficiency of this, I got 0.446, and when I got the efficiency compared to randomized block design, I am getting 40%, which is less than half of the efficiency factor with the same P is equal to 6 and same PDC plan. But what was the difference? In the earlier PDC plan, that each cross was replicated only 1 time or some were not. But in this case, some crosses are repeated 2 times and some crosses are not repeated. That's why the efficiency has been decreased. So my idea was that to suggest the plant breeders, so consider those PDC plan where you can find that efficiency factor is better than the take some 4 or 5 PDC plan with same lines P. Find out the efficiency factor. Don't go for the optimal criteria. Find the efficiency factor and see which efficiency is the minimum, and then select that PDC plan for your experiment. So these are the references. So thank you. I think I have completed within the time.
Thanks for finishing the talk within time allotted, Professor. You are a lifesaver. Now I invite questions or remarks, queries from the audience.
Hello, sir. Hello.
Yes.
Am I audible, sir?
Yes, you are. Yes, you are.
I am from Dr. Somir Bhandari, Bajkul Miloni Mahavidyalaya. You are presenting very nicely. I have some queries, sir. Please.
Yes, sir.
One query says, sir, you are explaining very example, giving so many examples very nicely. But I want to know if there is application, if any possible application, and also for any researcher. Suppose a researcher want to research on this field. What is your suggestion? It is my query.
Sir, application, I told you, sir, कि whenever you have a plant breeder or animal husbandry experiment, you want to conduct it for finding the promising variety of yield by crossing a gate to get the hybrid variety. So we have to cross the two seeds or two animals, etc., etc., and then you have the several crosses. And then after several crosses, we have to conduct the experiment, either conduct the complete dialect cross experiment or the partial dialect cross experiment. And considering all these things, then we find out both criteria, optimal criteria and efficiency criteria. But I will not go for the optimum criteria because this gives only the optimality, but doesn't suggest which cross we can, with design we can adapt. But in the efficiency factor, I found, sir, which have less efficiency, even more efficiency compared to the other PDC or CDC plant with the same line. Line have kept fixed. Line have not changing, sir. If you take that, then we will get the best results, and that is the application of the CDC plant, PDC plant, the plant and the cross experiment. Now, compared to the future plant, see, now I have taken just an example of p equal to 6. And I have taken only two, where one cross is repeated one time and another experiment, one cross is repeated two times. Now people may also try whether it is more than two times, what will happen to the efficiency of these percentages. But I found that if the number of times the same cross is repeated, naturally efficiency will decrease.
Okay, sir. Very good. Thank you.
And also, second thing for your answer, see, we have two questions. One is under the randomized block design, another is under incomplete block design. Better to go for under the incomplete block design.
Okay. Okay, sir. Thank you, sir. Thank you.
Thank you, sir.
Thanks for the nice deliberations, sir. We are very thankful to you. We appreciate your knowledge. And I think we all give a good appreciation to Professor Ghosh. You'll be joining with me. Now I hand over the session to the organizers. Sir, Satish Kumar, sir, please, we can take it.
Thank you, Professor. Thank you so much, Professor Ghosh, for your wonderful talk.
Thank you for your opportunity.
In fact, we are very much indebted to you, Professor. For even in this situation, you are trying to present very actively several things, and you are helpful to several young researchers in that respect. And also, we wish to extend our gratitude to you, Professor Arvind sir, for your support in chairing this session, and also concluded the session in a very nice way. Thank you so much, Professor.
Yes,
thank you.
By arranging the session very nicely, successfully, and timely, I am thankful to Professor Arvindam as chairman.
Thanks a lot. Thanks,
Professor. Thanks, Professor.
Now, I think let us next session will start at 2 p.m. Half an hour time is for our lunch break. So first you can go to lunch, and then please join before 2, 1:50 or 1:55, please. All are requested to join, rejoin the platform by 1:55 or 1:50 or 1:55. So you can take 20 or 25 minutes maximum for lunch break. Thank you, Professor. Thank you so much. Thank you. Bye.
Thank you, sir. Thank you.
So thank you, Samir Bhandari.
In the afternoon session, there Professor Samir Kumar Bhandari is there. Okay.
Hello, Professor Satish. Hello, sir.
Yes. Excuse me. Hi. Hello.
Yes, sir. I am joining. Already joined, sir. Professor Satish, sir.
Yes, Sadiq, I am also here.
Oh, okay, Professor. Okay. You can start at the right time itself. Now 1:54, sir.
Yeah, another 6 minutes here, I will start.
Yeah. Or we can within 5 minutes, 2-3 minutes, we can start the.
Yeah. Sadish?
Yes.
What about other two speakers? Amin Sahib and Shambasiva Shivarao?
Yes, sir. I'm here. I'm
Yes, okay. Oh, Shambasiva Rao is there. Okay. Nice to see you.
All are here, Professor.
Oh, okay. Very good.
Thanks.
Okay.
അത് 11:45 തൊട്ട് ഒരു 40 മുതലാക്കി. അല്ല 11:45 11:40 മുതലാക്കാം. പക്ഷെ 11:45 തൊട്ട് 12:15 നികേഷ് കുമാർ, 12:15 തൊട്ട് 12:45 തൊട്ട് 1:15
Sir, please mute your mic, sir.
Yeah, please mute your voice. Yes, mic.
Okay, let us, good afternoon, everybody. Let us, in fact, good afternoon, good evening, good morning. So, no
Good
problem.
afternoon. Okay.
Yeah, Neha is here in the group.
Yes, sir, I'm here.
Okay. Neha, please introduce the chair and let us start the session without any delay. Chair and the speakers are all there. So
Okay.
please introduce the chair and then support the chair for its further proceedings. Please.
Okay, sir. Good afternoon to all. We now move on to technical session number 6. This is an invited session to be chaired by Professor K. Muralidharan, Professor of Department of Statistics, Faculty of Science, the Maharaja Sayajirao University of Baroda, Vadodara. He has more than 30 years of teaching and research experience. Some of his major areas of research include statistical inference, stochastic point process modeling, quality and Six Sigma, etc. Dr. Muralidharan is a member of various professional bodies, including Journal of Indian Statistical Association, Journal of Indian Society for Probability and Statistics, etc. He has published more than 140 research publications in reputed national and international journals. We feel privileged to have you with us, sir, for chairing this session today. I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Thank you. Thank you very much.
Welcome, Professor.
Yeah. Satish Kumar, congratulations to you for getting elected to ISI in Netherlands. Okay. Good afternoon once again. I'm so happy to see all the 3 speakers in this session here. We have been given 1.5 hours. That means 30 minutes each for each party. Presenters. So what we will do is I will request the speakers to have their presentation for 25 minutes maximum, and then we will have some discussions, maybe question and answer, something like that. Is that clear, sir? The speakers? We have 3 speakers: Samir Kumar Bhandari from Bajkul Milani Mahavidyalaya, West Bengal, India. The second speaker is Amin Sahib Sheikh from Narsapur, Medak, Telangana. And we have the third speaker, Samba Shiva Rao from Pachunga University, Mizoram. Nice to see all of you. I request the speakers also to introduce yourself before you start your presentation. Just introduce for a couple of minutes. Don't take too much time. Just introduce yourself and then proceed. Okay, so I invite now the first speaker, Samir Kumar Bhandari.
Yes, sir. Yes.
Over to you, sir.
Yes, sir. Yes, sir. Thank you, sir. Good afternoon, everyone. First of all, I want to convey my heartiest thanks to organizing committee, especially Professor Satish, for giving me nice opportunity, this platform. Otherwise, I cannot talk. Last year, I also talk about here in this platform. Again, thank you, sir, for Satish Kumar, sir, and Muralidharan, sir.
Good.
Now,
thank you.
Okay, sir. Now, just a minute, I am sharing. Due to such technical problem, I am sharing with my cell phone. Due to technical
no problem. No problem.
Just 1 minute, sir. No, just a minute.
Okay. Good.
Now it is visible?
Visible. It's visible. Right. You can start.
Now.
Yes.
Okay. Thank you. Okay, sir. I am starting. My title of my talk is Some Approaches on Probabilistic Metric Space, simply which is known as PM space. It is very important nowadays. In this space, actual probabilistic metric spaces was introduced in 1942 Keminger. We all know that in 1906, Professor Fitchett introduced the metric space. All we school level, we all know the metric spaces. After that, in 1922, S. Banach established famous Banach contraction principle. And then so many researchers extended this theorem and established so many results on these spaces. They are like cone metric, B metric, and so on. But in 1942, after introducing the Keminger, Professor Minger introduced the probabilistic metric spaces. What is the probabilistic metric space? It is the probabilistic version of the metric spaces. In case of metric, we know that there is a distance function, d from x cross to r plus. But here, in case of probabilistic metric spaces, distribution function plays the role of metric. And here, distribution function has an important role for study many results. Okay. Next I'm giving what is the main points in my main features in my presentation. Here I am showing some important established result and new result also for opening problem. Such contraction we will see that it will be give the fixed points, and there is the use some different type genome. I'll discuss one by one. And also here is a control function. It is an important role in modern fixed point theory, especially probabilistic metric spaces. There is some corollaries. And lastly, I will discuss some open problem. What is for the new direction for the new researcher, newcomer in this field. Before that, I have the important definition. That is the distribution function. It is very, very important on this page. Distribution function is the here taken f is a distribution from R to R plus. It's called distribution when it is left continuous, infimum 0, supremum 1. And R is the set of real number, R plus set of non-negative real number. But here is your point. Why I take the left continuity? Because most theorem, especially still now, all researchers doing work on PM spaces with left continuity. But if any researcher or any which try to with right continuity, it's possible. And I think that it will be new direction for opening the new theorem. Examples. Heaviside function, one is the some standard example for the distribution function. HT1 for t greater than 0, less than equal to or t, less than equal to 0 is the 0, which is the standard example of the distribution function. Vital definition is PM space by probabilistic metric space. There is a connection between distribution function, there is a connection between a metric space and probabilistic metric space. In case of metric space, we know that it is a mapping from x crosses to R. There is a certain role. All college level students know that dxy equal to 0. There is some non-negativity condition, some symmetric property, triangular inequality, and after we get the metric space. Just like that, Professor Minger introduced using the distribution. Here is just like fx. Here x non-empty set, f is the function from x to distribution function. Here fxt actual meanings, fxt means probability of dxy less than t. That means dxy is the, if we consider the usual metric, that will be mod xy, distance between 2 points. If we consider the set x, 2 point xy, their distance, and we consider probability. And again, a question arises, when we take this, actually we take when we take the certain in our daily life example, we know that all not a distance is not a certainty. Always not we get the certainty result. Uncertainty arise also. In case of that, in case of uncertainty, we use the probability concept and probabilistic metric space also. There also, if xy t the distance between dxy less than t, that's probability is the fxy t. And comparison, if we compare with the metric space, just like fxy 0 equal to 0, fxy t 1, fxy t equal to fyxt, just like symmetry. When is the metric dxy equal to dyx, just like number 3 point, fxy t equal to fyxt. And all the property just establishing with the help of metric. And there is important books, Soiger Scalar, they discuss elaborately, and 2 important books. I suggest two important books for any researcher who want to research in this field. That is Hajikov, Soejaskar, very fundamental book, and very nicely they nicely explain the idea of the probabilistic metric spaces. An example: if we consider x equal to close 0, 1, and if xy equal to t by t plus mod xy, then xf is a probabilistic metric spaces. Then another important rule, there is when we know that in metric we consider the triangular regularity. That is very important for metric space. Just like that, probabilistic metric space, they are also triangular regularity very important. But although there is a recent researchers trying to avoid the triangular regularity, just recent some paper, Professor Gopal and so on, they are trying to establish showing to result without triangular regularity. That is non-triangular regularity. They are trying. That is other issue. But here the important role for triangular regularity, T-norm has a vital role. T-norm C and Etel, they introduce the concept of T-norm. Here T-norm means blocks 0, 1 to 0, 1 to 0, 1 to 0, 1 in its terms and on. That is the T-norm. We satisfy number 1, T 0, 0, 0 equal to 0, G 0, just like property 1, 2, and 3, all the properties satisfy, they only get the T-norm. But if we take the n equal to 2, actually in general, we use the binary T-norm or simply T-norm. That is, if we take the n equal to 2, that means T is a mapping from 0, 1 plus 0, 1 to 0, 1, that is the binary T-norm. Usually we use this T-norm. This T-norm, and there are just so many types of T-norm, just like minimum T-norm, leukocyte T-norm, product T-norm, tastic T-norm, so many T-norm. If we use the different type of T-norm, we can get different result. And especially myself and my with Professor Vinayak Chaudhary from IST Sipur, jointly we established so many papers using different types of T-norm. There is a difference, and minimum T-norm is a weak T-norm. Strong T-norm. Other T-norm is weak T-norm, but when we want to a strong result, we have to use the weak T-norm, such like product T-norm, continuous T-norm, and so on. There is a Menger space. It's a Menger space is a triplet. That is X, F, delta. X is a non-empty set. F is a function defined X goes to the all distribution function. Delta is a just already I've discussed T-norm. And satisfying this property, there is a similarity, just like definition of point 1, 2, 3, all are same, just like probabilistic metric. So what is the difference with Menger and probabilistic? The number 4 point. That means triangular inequality postulated with the help of T-norm in case of probabilistic metric, then we get the Menger space. That means vital point is 4 number point. And to establish fixed point, I will show soon. I will show that, discuss that. This triangularity very important role to establish the fixed point result in these spaces. Fxy u plus v greater than equal to delta, fz u, fz y v, for all u v greater than 0, xy z x, just like triangularity of metric space. Actually, I want to conclude that there is a similarity because space is different, but their property just like similarity. For uncertainty, we use that. And there is a combination, there is a relation between metric and probabilistic metric. That relation is fxy equal to h of t minus dxy. I already discussed that h the Heaviside function. And if we disconnect, we can connect by this relation is the from distribution function from probabilistic metric to distribution from metric spaces. And then important role, we all know that in case of function analysis, especially any analysis, probabilistic metric, metric space, fuzzy metric, very important 3 items: convergency, Cauchy sequence, and completeness. It's a pillar of analysis, not only functional, all analysis, and probabilistic metric also. So now I'm discussing convergency property. The sequence xn in a Menger space, except delta, is get to be convergence to the limit x. If we take the epsilon greater than 0 and 0 less than lambda, there exists a positive integer in epsilon depending on in epsilon lambda satisfying f x n x epsilon greater than equal to 1 minus lambda for all small n greater than, for all small n greater than n epsilon lambda. That is the definition of convergency. And another important Cauchy sequence, it is the pillar of analysis, Cauchy sequence. A sequence Xn is a main space except delta. Is said to be Cauchy if we consider again small epsilon and lambda lies between 0, 1. And if Xn, Xm, epsilon greater than equal to 1 minus lambda, then we get the Cauchy sequence. There is a point. If we take the, always you can take the greater than equal to in definition 1.1.2. That is point I indicate here that in greater than equal to in definition, we can replace by greater than 1.11. They are written actually in the convention already. We have presently given this for our proof. But if we take the convergence of greater than, then we can be Cauchy sequence to greater than. That may be possible also. Some my paper also establishing this using this definition according to our requirements. And there is a completeness. Completeness means we know that if a Cauchy sequence converges in that space, that is the completeness property and complete metric space. And recent time, another important role is control function. It is very, very important. Recent researchers taking their interest using control function, some admissibility condition also, just like phi function. Control function, actual Khan-Swale in 1984, they introduced first alternating decision function. And therefore, after that, so many researchers using this control function, alternative distance function. In 1980, actual 2008, my supervisor, Professor Vinayak Samadda Chaudhary, is a recently professor from IST Shibpur, and my friend Krishnapada Das jointly introduced the control function phi. It is and published there, Acta Mathematica Sinica Hungarica. It is a very cited paper. So many citation researchers are doing using this control function, many papers. We also jointly use this paper, many our paper also. It is the phi from R to R plus and phi t equal to 0. If L t equal to 0, phi t is taking strictly increasing and tending to infinity, phi is taking left continuity. Phi is continuity. There is also question. When they are taking left continuity, it's possible right continuity, the question arises. Yes, possible. Then new direction may be open, just like distribution function. It is an open problem also. And some example, phi t. If we take the phi t equal to t square, phi t equal to root t, phi t equal to t, then we can give some example. So question arises. So what is the important? Phi t, that is important because if you we can establish suppose a result with t. Some researcher doing with t square, some root 2. But if you take the phi t, they generalize all this. Because phi t equal to maybe t square or root 2. So phi t is a more generalization than taking general t square and root 2. It is a more give the more generalization in the researcher also. That is why researcher trying to apply this result also. And again, administrative condition also. There is a show administrative condition. That means alpha, beta admissible. Professor Samet possible. They introduced first this admissibility condition, and the same researcher are trying to working this well also. And at the recent time, very recent time, in the Asian, especially India, some researcher doing work in this. My guide, Professor Chaudhary, myself, my friend Nicholas Metia, Professor Dhananjay Gopal, and Professor Sandok from Kapar Institute. They are all doing research on this. Professor Sandok and Dhananjay, my collaborator also, we are some working in this field also jointly. And there is a Professor Sontu Barot, Thailand, Professor Mujahid Abbas from Pakistan, but especially from South Africa, is working field. And Sirik, Rhodes, Mihe, all are renowned person on this. Although Professor Sirik expired few years ago, they are all the renowned person in this field, researcher. They are used also some this admissibility condition also. And 2003, Professor Kirk, Srinivasan and Viramani, Professor C. Viramani is a Chennai Mathematics Institute, more possible, jointly established a paper. That is the new concept. All are trying to concept extending the result of Banach contraction. Already first, I discussed that is the main pillar, Banach contraction. And they introduced the cyclic concept here in metric spaces. After that, in 2011, myself, Professor Chaudhary, and Krishnapada jointly established a result, their probabilistic version, first time, and established this paper is cited more time because then opening new direction is probabilistic. They introduce actually metric, but we had the probabilistic version established there. That is the probabilistic version of the main. And also we are establishing two Menjar also. There is a two Menjar, two metric all, and we are working also two Menjar spaces field. I myself, Professor Sandok, all are doing working this field also now recent time. And that is the cyclic. Cyclic context actual, if we consider the non-empty set capital, if we consider non-empty set capital X, and there is some non-empty subset, that is AI, A1, A2, A3, there's so many subsets, non-empty subset. And then cyclic means we are taking the mapping from union I equal to 1 to P AI to union I equal to 1 to PI. That is the cell mapping. But cell mapping taken from the subset of X. There is a cell mapping and satisfy the condition Ti less than equal to AI, a subset of AI plus 1, 1 less than equal to I less than P, and TP less than a subset of A1. Very important. Why? If we take the A1, A2 mapping, that means T1 subset of A2, T2 subset of A1, just like 2. If we take A, B, C, TA, that means image of A belongs to B, image of B belongs to C, image of C belongs to A also. That means the cyclic way. That is the cyclic contection. It is very important. Cyclic contection. And parallelly, we can do orbital also, new concept, just like the similarity concept, orbit concept. T0, T1, T2, T3, T, that orbit concept, just like cyclic also. And recently, some researchers trying to co-cyclic concept, just like similarity. That's because in case of they are taking the two mapping. Here, in case of cyclic, we have to one mapping, single mapping, but they are taking cyclic concept of co-cyclic, taking the two mapping. It may be possible 3 mapping, 4 mapping, that is open problem also. And here, if we take the P, there are many papers. There is in recent time, all people are trying to establish this cyclic concept using this. They are established many fixed point result also. And there is a question. I taking the cell mapping. Is it possible non-cell mapping? Yes, it is possible. If we take the non-cell mapping, that means possible, but there cannot get the fixed point because fixed point is the Tx equal to X. But that is if two set are disjoint, there is no possibility image set and their pre-image set, image and pre-image point set. So that is why we cannot the fixed point. We can the proximity point, and that is the researcher taking their interest so much taking interest in the proximity points also. There is not only metric space, they are also taking probabilistic metric space, fuzzy metric also. Actual fuzzy is another direction. That is the Professor Jade, 1963, introduced this famous concept. And all researchers trying, they are doing work on this fuzzy concept. That is new direction. It is actual probabilistics, actually we can randomize them. And fuzzy is the membership function. In case of probabilistic, there is the distribution function. But randomized with the membership function. There is a parallelly, metric, probabilistic, fuzzy, there are 3 parallel directions doing. And researchers trying to establish result for metric. They try to convert into probabilistic. They try to another fuzzy. That means uncertainty arises. They are taking their interest on probabilistic. And they are now main results. Main results means here is the first taking the in case of any fixed point theory, it is a very important fixed point theory, recent, it is a very important optimization theory, control function, recent time researcher doing that, it may be possible, image processing, fractal, that can be applied also, this direction is possible. We have so many applications there. And here, the except delta be a Menjar space, delta is the continuous T-norm. There is a vital point, continuous T-norm. That means del A greater than equal to 0. And if we take the AI non-empty sets, that means A1, A2, A3, or non-empty sets taken. And taking mapping A from A1, union A2, A3 to A1, A2, A3. It is cycling mapping. That means cycle direction, satisfy the cycling. They are taking cycling. F1 to F2, F2 going to F3, F3 going to F4, and these way ultimately F3 going to F1 again. That is the cyclic direction. And then final number point 2 is a vital is a contraction. This contraction means if Tx Ty greater than equal to mean of Fxy T by T1 by A, Fxtx T2 by B, Fyts T3 by B, Fxty T4 by D, Fytx T by B. There is important. Because what is the important this? Important this means actual Banach contraction establish dTxty less than equal to alpha dxy. Their probabilistic version is f tx tyt greater than equal to fxy t by c. That is the Banach. The first point is the for the Banach. The next second point, xtx and yty, it is the canon. Next two item is the canon. An actual canon, Professor established his paper in Bulletin Mathematical Society. It is proud for her that he established new result simply in West Bengal Calcutta Mathematical Society. He established his famous work, canon.
Samir,
Yes, sir.
please conclude it in 5 minutes, please.
Okay. Sorry, sir. Okay, sorry.
Thank you. Yeah.
Okay, sir. And then there is a contraction, and this is my main results. The ftx to it greater than equal to this, combining this, and they give these fixed point there also. And now it is some example, and we take the corollary. If we take the phi equal to t, then we can give the results, same corollary, and phi equal to t. If we take the 2 or 3 sets, also another results, and some in a corollary. But due to short of time, I am speedily conclude myself that it is the some example. Now I conclude in giving some application. There is some application. Recent time, my guide supervisor, Professor Choudhury and Priyam Choudhury established a fractal chaos solution factor. They established result. It is possible. The probabilistic, they show actual metric probabilistic version, and we are trying to establish the fractal degenerative in the probabilistic metric, image processing, all our applications, and co-cycling, common fixed point, all the opening problem for all us. And so there is some references, there is some important references. Thank you, sir. Thank you for
That's wonderful. Sorry for the interruption. We have to go with the time. That's the reason. So, okay, thank you so much. It was really a wonderful presentation, sir. Pure theory-based probability metric space.
Yes,
okay,
yes.
Let me ask the audience if they wanted to ask any questions. Then we'll get back. Audience, any candidate, any audience wanted to ask something? Okay. Anyway, we don't have time to wait for. Anyway, let me ask you a very simple question, sir.
Yes, sir. Yes, sir.
The application part, the last you had mentioned something. So where exactly it is used? For example, in a very simple sense, can you talk about where is the application exactly?
Yes, sir. Yes, sir. It is actually applied. Already we have shown that integral solution. In case of integral solution, differential equation, also image processing. Some paper is coming.
Okay, image processing. Okay.
Yes, yes, some paper is coming now. We say image processing also. Any query?
Copula concept.
Yes, sir. Yes, sir.
How far it is connected with copula? Can you connect this particular theory with copula construction, where distribution functions are combined to form new distributions, etc.?
Yes, it is possible. We'll trying because it is. I am not doing on this direction. Trying.
Okay.
I will after your session. I will trying. Yes.
No
yes.
issue, sir. No problem, sir. Thank you very much. It was really a nice presentation, sir.
Yes, sir. Yes,
okay.
Sir.
Thank you very much once again. We'll definitely meet in person also in future, sir. Thank you.
Thank you, sir. Thank you, sir.
Now I invite Amin Sahib Sheikh for his presentation.
Yes, sir.
Amin, yes.
Yes, sir. Yes, sir. Good afternoon, sir.
Please put the camera on, please.
Yes, sir.
Camera as well. Yes, please. Please introduce yourself for a couple of minutes and then start the presentation. Amin. Okay.
So, good afternoon.
Amin, over to you. Yes, over to you.
Yes. First of all, I thank to Professor C. Satish Kumar sir and Muralidharan sir for giving this wonderful opportunity to explore my research work. Sir, I am Dr. Amin. I am working as assistant professor in BYRT Engineering College, Hyderabad, sir.
Hyderabad, yeah.
My research work on mainly my research area design and analysis of experiments. So, particularly dimensionality reduction in response surface design, sir. Our research work is on basically dimensionality reduction techniques.
Okay.
So, today I am presenting how to reduce the number of factors in response surface design. Is it visible, sir?
It's coming. Yes, it is visible.
Yes, sir.
Okay. It's now.
Sir, my topic of presentation is
Put it in slideshow mode. Put it in the slideshow mode.
Yes. Yes, sir. So, my topic of presentation is response surface design model reduction using Sobal indices. So, the logical construction of an experiment is known as design and analysis of experiments. We have different types of designs like completely randomized design, randomized black design, Latin square design, factorial experiments, and black designs. And similarly, response surface methodology. So, response surface methodology is also one important branch of design and analysis of experiment. The main goal of response surface design is to optimize the response when we have several independent variables. So in this case, it is used to find how the levels of application of independent variables and changes in response variable also. But the problem is when we have more number of variables in response surface design, so it is very difficult to analyze the data, analyze the design, and it is important to identify the important factors out of the given n number of observations with the minimum number of minimum loss of information. So what is response?
Yes, sir. Please put it in the slideshow mode. Please put your presentation on the slideshow mode.
Yes.
The presentation is seen. You have to put it in the slideshow.
Yes.
Maybe you can share the desktop and then start presenting.
Yes, sir. I'm sharing this.
Nothing to worry. No,
don't worry. Share it once again. Now your presentation disappeared. So please share it once again.
Is it visible now, sir?
It will come. It will come. I think if you have started the sharing, then definitely it will come. So far, not. Okay. Okay, it's coming. Yeah.
Yes.
Okay. Maybe if you are comfortable with this one, okay, fine. You go on. Go ahead.
Yes.
Go ahead.
So let there are V factors x1, x2, and so on xn. Each factor is S level for experimentation, and here D is a design matrix. Now the functional relationship between factors and response, nothing but response surface, and the designs are used for fitting response surface model is known as response surface design. Generally, we are using first order and second order, etc. So here, this is the general response surface model y equals to x beta plus epsilon, where y is the vector of observations and epsilon vector of random errors, and x is a design matrix, beta is the vector of parameters. Now, there are many authors' attempts on dimensional reduction in response surface model, but these authors' attempts on only application point of view. We know well-known methods like principal component analysis, factor analysis, multidimensional scaling, stepwise correlation approach, and so on. But the principal component analysis is not suitable for nonlinear structures. And factor analysis is also not applicable for the interaction effects in the model and estimation of main effects of individual factors. So these authors attempts particularly on response surface model. So these authors studied only application point of view. There is no theoretical work on the dimensional reduction of response surface model. That is our we are focusing on response surface design theoretically, how to identify the important factors. So this is our motivation of work. Here, 1988 Venter taken a problem, mechanical problem, and they want to they are trying to reduce number of factors from 9 to 7 by using element analysis approach. And MCK 99 reduced the fitted model to some specific experimental data by using correlation ratios. And Laysen still 2006 studied the finite element method for an engineering problem to reduce the number of factors from n to n minus k. So this is our basic idea. What is Sobal indices here? So let y equals to f of x is a response surface model model of order k, and here x1, x2, and so on xp are independent variables, and y1, y2, and so on yn are response variables, and the model in y is expressed as this one, and here we are calculating variance for each input vector, each independent variable, and we are dividing with variance of response. So variance of each beta and divided with variance of each response vector. So that is the basic idea of snowball indices. Now, how to apply this snowball indices for response surface model? One minute. So here, derivation of snowball indices for first order. So how to calculate snowball indices for first order response surface design model? So this is our first order response surface model, and here this is the estimated response y hat equals to beta naught hat plus beta 1 hat xun plus and so on. So this is the variance covariance matrix of beta for a first order response surface model. So this is the X transpose.
I mean, we are unable to see anything about this kind of surface design model. You click that surface design, nothing is appearing. Maybe you will be able to see, but we are not able to see anything.
Yes.
The derivation part we can't see.
Sorry, sir. Again, I will.
Maybe you open that file separately and then show it.
Okay.
You just move the slides. That's it.
Yes, sir. I'm changing slides, sir. But
now share it once again and do it.
Is it okay now, sir?
Okay. It's visible now.
Yes, sir. This is perfect. This is variance of predicted response at the youth point, and so this is movement matrix of X. Now we are calculating snowball indices for first order response surface model. So this is S naught. So this is variance of beta naught hat by variance of estimated response. Similarly, Si is the variance of beta I, so and by variance of response. Similarly, we are calculating snowball indices for Ij term. So these are the snowball indices for a first order response surface model, but theoretically it is not compressed form. That's why we are imposing some conditions towards the orthogonality. After imposing these conditions, so our X transpose X becomes like this, and variance of response. And for after imposing these conditions, our snowball indices becomes S naught equals to n inverse and Si equals to xi square by n into lambda to sigma square, where sum of snowball indices must be equals to 1. So the proportion of variance indices are used to obtain indices, snowball indices in case of orthogonal, non-orthogonal presented in this example. So here we considered a numerical example for orthogonal in case orthogonal case. So where our betas are beta naught equals to 328.3 and so on, beta 4 minus 51.07. So these are the snowball indices for the given experimental data. Now, based upon these snowball indices, we are giving ranks to eliminate the unimportant factors from the model. So this is another numerical example we taken for in orthogonal case. These are the snowball indices for this data set, and based upon this, we are giving ranking. After that, we identify the important factors and fit the model with these important factors only. Similarly, we calculated second order response snowball indices for second order response surface model. So this is our second order response surface model. For this, estimated response is this one, and variance covariance matrix is variance of beta hat equals to x dash x whole inverse into sigma square. For second order response surface model, our movement matrix X transpose X is this one, and these are the snowball indices for second order response surface model after imposing the conditions, and these are the variances for individual parameters. So these are our snowball indices for second order response surface models, sir, S0 and SI, SIJ, SIA. So after imposing these conditions, we got these Sobol indices. Based upon these Sobol indices, we are giving ranks, and based on that, we are identifying the important factors. So these are the comparisons between Sobol indices in second order response surface design. So when C n lambda 4 equals summation x power 4 and n lambda 2 equals summation x square, then 1 by the ratio of SI and SIA are 1 by lambda 2 and 1 by lambda 4. So these are the comparisons between the given derived Sobol indices. For this, we taken some experimental data and fitted second order model. For this, we calculated Sobol indices. Based upon these Sobol indices, we are identifying the important factors from the model, and we removed unimportant factors and fit the model with important factors only. So this is for non-orthogonal data. So for this also, in this case also, we calculated Sobol indices. So our goal is to find the Sobol indices for first order and second order model response surface models.
Is it over? I mean,
1 minute.
Okay.
So yes, sir. So there is a future scope for dimensional reduction by using Bayesian approach and artificial neural networks. So these are our references, sir.
Okay, good. Any questions from the audience, please? Questions are invited from the audience. Amin,
sir,
how does your design compare with the partially balanced incomplete designs, PBIBD, etc., or usual regular designs, maybe factorial designs of 3 raised to n kind of experiments?
Yes, sir. We taken only response surface design, sir. We constructed supercharged designs from partially balanced incomplete black design, sir. We not calculated Sobol indices for PIBD.
Okay, you have not done so far.
Yes, sir.
I think you need a kind of comparison.
Yes, sir.
The existing designs.
Yes, sir.
Because what is the gain in terms of efficiency?
Sir.
In terms of any performance you could talk about.
Yes, sir. But there is no much theoretical work in response surface design to reduce the number of factors. Sir. This is the first step. So we are trying to do in applying a Bayesian approach or artificial neural networks. We are trying for that.
Okay. Who is your guide?
Professor Bhattacharya, sir, from Usmani University.
Usmani University. Okay.
Yes.
Okay. Oh, that was really good. Any questions, any suggestions from the audience, please? Otherwise, we will close this session here, this presentation. We'll have one more presentation to go now. Okay, thank you, Sami. Amin.
Thank you, sir. Thank you very much.
Presentation. See you. Thank you very much. Right. Sambas Rao. Yes.
Yes, sir. Namaste, sir.
Yeah. I believe we met each other somewhere in some conferences, sir. Sambasiva Rao.
Last chance, sir. I don't know, sir, because I rarely attend any conference.
Okay, even I do. I'm not very sure about, but still,
Yes.
maybe somewhere you might have seen. Okay, please introduce yourself and go ahead.
Yes, sir. So I'm Dr. Samba Shivarao Paspuleti. I'm assistant professor in the Department of Statistics, Pachinga University College campus of Mizoram University. I joined here in 2019. Before joining here, I worked for 1 year, 4 months in the Institute of Liver and Biliary Sciences, New Delhi during 2018 to 2019. I obtained my PhD degree from Population Studies Unit of Indian Statistical Institute. I did my work there and obtained degree in statistics from Calcutta University in the year 2012. I did my postdoctoral research in demography for 2.5 years in Deakin University, Australia. I work in the areas of demography, public health, epidemiology, and biostatistics lines. This is all about me. And before I go with my talk, I sincerely would like to thank the organizers of this conference, in particular Professor C. Satish Kumar sir, for giving me this wonderful opportunity to share my work with the learned audience. Let me share my entire screen. So is my screen visible?
It will come. It will come. If you're shared, then it will come. Even I am also experiencing some problem with the network. We have heavy rain outside.
It is visible, but you can make it full screen if it is not difficult for you.
Okay.
Yes, sir, definitely.
Okay, it is seen. It is visible now. Please start presenting. Okay, it is seen.
Yes.
Fine. Perfect.
So this, the title of my paper is Estimation of Health and Economic Burden Due to Alcohol-Related Liver Diseases in India and its states and regions, with a special focus on southern states of India. SOU, just here is a spelling mistake, sorry. A multi-state Markov modeling approach. This work is a part of my UGC-sponsored major research project entitled Estimation of Health and Economic Burden Due to Alcohol-Related Liver Diseases in India and its states, a multi-state Markov modeling approach. Before I go ahead, I just want to briefly tell about this entire work. As we all know, alcohol has a detrimental effect on health. One of the major effects that it had on health is through liver also. In fact, worldwide, around 50% of deaths due to liver cirrhosis are due to alcohol. And in the context of India, over the last 2-3 decades, the consumption of alcohol has greatly increased, both in terms of magnitude.
Dr. Rao,
yes,
please.
sir.
Your slides are not moving, I suppose.
Yes, sir. I didn't move it. I just
move it.
briefly
Okay.
telling about.
Okay.
Yes,
please
sir.
see.
Yes.
Okay.
Yeah. So, as a result, the number of cases with liver diseases attributable to alcohol has greatly increased. In fact, with the decrease of communicable diseases like this variety of viral hepatitis, now alcohol, the share of alcohol in liver diseases, it has increased by more than or about 50%. But there are no studies, not only in the context of India, even in the context of world, that assess the health and economic burden due to alcohol-related liver diseases. So this is the first of such study, not only in the context of India, but in the context of world also. And these similar kind of approaches can be taken to study in the other contexts and even some other problems also. Now, with that brief background about this work, now I would like to go little more detail. Alcohol is a psychoactive substance with the dependence-producing properties. In fact, alcohol is a liquid that is formed through the process of fermentation of yeast with sugars in fruits and then starches, grains. Depending upon which kind of fruit or which kind of grain is used for producing alcohol, we are having variety of forms of alcohol, and they are available in different forms and in different brands. And these are few such things that I showed here. Studies from around the world, they showed that alcohol has detrimental effect on health. It can influence various body organs, including the cerebral system, so-called brain, the circulatory system, hepatic system. Hepatic system is what is liver system, liver, gallbladder, and pancreas all together. This is called the hepatic system. It can influence renal system, so-called kidney system, reproductive system. From these, at least 40 diseases. For 40 diseases, alcohol is the sole cause for those diseases. Of the 3 million deaths in the world, about 636,000 deaths are digestive diseases. Digestive diseases do mean any disease that is related to all these parts, either liver or to the stomach or to big intestine or small intestine, so anything related to this. Now, majority of the burden out of this also falls on liver itself. In fact, because of alcohol, a range of liver diseases are possible and they are progressive in nature. If a person with normal liver, I mean, of course, basically everyone will be having normal liver. Now, with heavy drinking and persistently heavy drinking, 90% of the people with normal liver, they will develop a disease called fatty liver disease, or called hepatic steatosis. Basically, it is forming of some form of fat in the liver. And with persistent drinking, suppose if the person stops drinking, then it is irreversible. It will go to normal liver stage. But if the person keep drinking, then of these people, 20 to 40% of the people will develop steatohepatitis. This is heavy, it is presence of heavy fat in the liver. And of these people with sustained heavy drinking, 8 to 20% of the people will develop cirrhosis. Now, why I'm telling about all these things? Because these stages are important, and the Markov model bases on the progression of these stages in this study. Now, as I said, in the context of India, over the past 2 decades, alcohol use has increased to a level that is posing big public health threat to the country. In fact, between 2006 to 2016, the quantity of alcohol consumed per person has doubled in the country. This is the prevalence of alcohol in India and its states during 2019 to 2021. In India, on the whole, 9.91% of the people aged 15 and above, they drink alcohol. The percent drinking alcohol is highest in the northeastern part. In Arunachal Pradesh, 38.42% of the people, they drank alcohol in 1 year before National Family Health Survey 5. In case of South India, Telangana is the state with highest with highest percent of drinking people alcohol. 24.61% of the people aged 15 and above drink alcohol in Telangana. Same in Andhra Pradesh, it is 11.55%. In Tamil Nadu, it is 12.27%. Yes, in Kerala, it is, I'm unable to see, it is, yeah. Is my screen still visible, sir?
Yeah, the screen is visible. Yes. No issue, no problem.
Yeah. Now, with heavy drinking in different parts, the burden due to alcohol-related liver diseases is also expected to be more in those states or regions where alcohol use is high. And the burden, the economic burden in particular, it not only depends upon the prevalence, it also depends upon some other factors. Now, all those factors were taken into consideration in modeling approach, and health and economic burden has been estimated. Now, the objectives of the study is to estimate health and economic burden due to alcohol-related liver diseases for India and its different states and regions for the period 1st March 2021 to 28 February 2022. It means what I'm really focusing about is the recent burden, that to annual burden. So there are 4 objectives, minor objectives, not main, the 4 objectives. First, how much is the health burden at all India level? Second, how that burden is varying from state to state. Third, how much is the economic burden at all India level? The fourth one, how that burden is changing from state to state. Here, economic burden I have assessed in 3 different situations. Before talking about that, health burden has been assessed in 2 terms. One, how many deaths are happening because of alcohol-related liver diseases? Second, how many disability-adjusted life years are lost due to alcohol-related liver diseases? These disability-adjusted life years, it takes into account both the quantity and quality of life lost. I skip this part, assuming it is known. I mean, dailies are known to the people working in public health line and in biostatistics line. I'm skipping this. Now, this is the methodology that is proposed in this study. The central idea is I will be finding number of people in different liver disease states based on the total population aged greater than or equal to 15 years, proportion aged greater than or equal to 15, based on that I will be finding this. And by multiplying that number with percent of the people drinking alcohol, I can find the number of drinkers. And by multiplying that with prevalence of various liver diseases, I can get prevalence estimates. They are not basically from India. Those estimates are from at global level. And then after finding expected number of people in different liver disease states, then a Markov model approach could be used to find person years spent in various liver disease states, and then using utility in various liver disease states, then total years of life lost due to reduced utility can be obtained. And applying this Markov model, I can also find number of deaths due to ARLD, and using these information, I can find total disability adjusted life years. This is the Markov model that is considered. I mean, the different transition of liver disease states, transition of individuals between these states is what is being considered. And for your better idea, I have provided some parameters, all these for the context, to show the calculation in the context of Mizoram. And this is a point estimate calculation I'm showing, but interval estimation is there, and for different states, different regions, it is there. The idea the calculations goes like this. In Mizoram, there are 12,16,000 people are there. Of them, 76.4% of the people are aged above 15 years. So by multiplying this 0.764 with this, I will be getting number of people aged above 15 years. Now, of these people who are aged 15 and above, now from the National Family Health Survey 5, I have the information that 12.24% of the people in Mizoram aged 15 and above are consumers of alcohol. So I can find the expected number of alcohol drinkers in Mizoram by multiplying this with this number. So I find 1,13,341 are the expected number of alcohol users in Mizoram. Now, what literature says is, if there are 100 drinkers, alcohol users, 82 of them will have normal liver, 10 of them will be having fatty liver disease or hepatic steatosis, 5 of them will be having alcoholic steatohepatitis, and 3 of them will be having cirrhosis. If that is for 100, and for these many people, how many number of people I can expect in normal disease state, alcoholic hepatic steatosis state, alcoholic steatohepatitis state, and cirrhosis state, I can find. And from the literature, I found if there are 100 people, 100 with normal disease, and if they drink alcohol for 1 year, what is the transition? What will happen? 73% of the people will remain, 73. If there are 100 people, 73 people will remain in the normal state even after drinking for 1 year. Some 17 people, they will develop fatty liver disease, so-called alcoholic hepatic steatosis. 10 people will be developing alcoholic steatohepatitis, and within 1 year, no cirrhosis will develop. Similarly, if there are 100 people with alcoholic hepatic steatosis, with 1 year continuous drinking, 71 people will remain in the same state, but 26 people, despite drinking, they may go back to normal state, and about 2 people will develop to the next level, alcoholic steatohepatitis, and out of 1,000, only 1 person may develop cirrhosis. Similarly, the other parameters could be understood. Now, applying these with certain assumptions that the transition of liver diseases over the year are uniform. What I mean is, if there are 12 people who moved from normal state to alcoholic hepatic steatosis state, every month there is 1 person is moving out of the 12 people, so that on an average they are moving to the other stage 6 months. And even there may be some deaths due to natural causes. So those deaths are also assumed to be uniform throughout the year. Now, after applying with those assumptions and after the calculations, relevant calculations, these are the expected number of people, expected person years in different liver disease states during 1st March 2021 to 28 February 2022. And similarly, these are the expected number of deaths. Now, what literature says is whoever died due to liver diseases, they die on an average at the age of 47.19 years. So now in Mizoram, life expectancy at birth is 69.7 years, the current one. So therefore, whoever died due to alcohol-related liver diseases, they are dying on an average 22 years. They are before they actually supposed to die if there is no alcohol in the population. So by these people, how many years are lost? This multiplied by the 22 years. That is what is 3,710 deaths. Now, these people who survived but with the disease. Now, a person in cirrhosis state, his utility is not like a normal person. Because of the disease, their activities of daily living will be restricted to a level of, a person with cirrhosis is only 74% efficient as a normal person. It means 26% utility is lost due to cirrhosis. Now, because now these many people, these many person years are there, and each one losing 0.26 years. So that this multiplied by 0.26, these multiplied by 0.24, these multiplied by 0.02 will give me the total utility years lost due to alcohol-related liver diseases. Now, when I add these two things, I'll be getting DALYs, disability adjusted life years. Sir, my screen visible and am I audible?
Yes, yes, yes. Continue.
Yes, sir. Now, this is how economic burden is estimated. Now, there are two kinds of losses. Those who died in Mizoram due to alcohol-related liver diseases, they are dying 22 years before they are supposed to die. But however, assuming that productive life is up to 62 years only. In India, the average age at retirement is 62 years. Therefore, those people who died in Mizoram, they are dying at the age of 47, and then 62 minus 47, it is 15 years. So those each one is losing 15 years. Per capita income of Mizoram is say 1,48,000. So multiplying that number of people and per person losing years multiplied by per capita income, we will be getting the amount of money that is lost due to premature productivity. Rather, it is productivity lost due to premature mortality from ARLD. Similarly, the utility years lost multiplied by per capita income, that it will be giving the productivity that is lost due to disability from the disease. Now, combining these will be getting productivity losses. Now, there is not only productivity losses, there will be cost to the system for treating alcohol-related liver diseases, and there will be out-of-pocket expenditure to the people in the form for getting treatment. Suppose if the person, alcohol-related liver disease person, if the person goes to a private hospital, then totally it will be out-of-pocket expenditure only. On the other hand, if the person go to a public healthcare facility, public hospital, government hospital, then there will be some cost for treatment to the government, and there will be some cost, there may be some cost to the person also. If the government hospital provides every treatment and even provide medicine, which is generally not the case, but they will some cases they may give some medicine, but still the person has to purchase some other medicine. So there will be cost to the system, there will be cost to the individual. There are three levels of government care, government hospitals at India: primary healthcare centers, community healthcare centers, tertiary cares in the government setup, and of course, there is a private in the government hospitals. Everywhere at the three different levels, there will be cost to the system, there will be out-of-pocket expenditure to the individual. And all these how much it is going to cost for each of these problems, that is there collected by someone, Professor Shankar Prinjar, in his sequence of works. So those works are being utilized in this particular study for cost estimation. Now, before I go with my findings, I just want to, sir, how much time I can use? How much time I have?
Yes, you have 5 to 6 minutes. 5 to 6 minutes you have to complete.
Then I will skip a couple of things. I just briefly, across the states in South India, Tamil Nadu is having the highest population, and percent of the people aged 15 and above is also high in Tamil Nadu. In Telangana, 24.8% of the people aged 15 and above, they drink alcohol. In case of Lakshadweep, the Lakshadweep is a union territory in South India. Person drinking alcohol, people aged 15 and above who drink alcohol is just 0.3%. Per capita income is highest in Lakshadweep. And in the states, Telangana, per capita income is high. it is in fact Karnataka. Karnataka, it is high, and then it is followed by Telangana. Now, life expectancy at birth is highest in Tamil Nadu, and person preferring government hospitals is highest in the Union Territory of Andaman Nicobar Islands, and it is the least in Telangana. I skip these different regions. They differ in terms of these characteristics mentioned, and this is at all India level. This is the burden, health burden measured in terms of number of deaths. At all India level, due to alcohol-related liver diseases, there are 218,169 deaths are expected by the used model. The 95% confidence interval for it suggests these deaths could be as low as 1,47,990 deaths, or as high as 2,95,000. Now, these estimates were compared, cross-checked with the WHO reports, and they are very close. Total dailies lost, productivity lost, and the confidence interval. Total economic burden. The economic burden has been estimated in 3 different circumstances. One, if a portion of ARLD patients, alcohol-related liver disease patients, only take treatment. Other cases, now this is what is reality. In reality, only a fraction of people with the liver diseases, they go for treatment because liver is something different from other organs, and many of the people, they never know they have liver disease. And it will never show symptoms unless the health problem becomes very serious. Now, that is only this estimate that if only a fraction of people go for treatment, this is close to reality, but that is not the true burden. If all people who have liver disease, if they are to be treated, then how much is going to cost? That is what is the true burden. And the true burden has been assessed in 2 situations. One, respecting individual choice for taking treatment from private and public hospitals as per their choice, as per their usual choice. The other is, if all people are to be treated in healthcare facility. If all people are to be treated in the public healthcare facilities at all India level, it's going to cost 2 lakh, the total economic burden, which is sum of burden to the healthcare system, to the individuals, and productivity losses. There will be 2,729 billions of dollars will be lost if all people are to be treated in the public healthcare facilities. The total burden due to alcohol-related liver diseases, if people are to be treated as per their choice in the public and private hospitals, is 3,807 billions of Indian rupees. And the burden is estimated number of deaths in different regions. In southern region, 59,764 deaths are expected, and is followed by eastern region, central region, north, west, northeast. But as we know, different regions have different population sizes. Similarly, different states have different population sizes, and it is obvious the state or the region with high population will have expected to have more number of deaths despite lower prevalence of alcohol. So for a sensitive and for a sensible comparison, deaths per 1 million population has to be compared. And if we compare deaths per 1 million population across the states, this is still the total deaths only. As far as total deaths are concerned across the states, Uttar Pradesh, it has highest number of deaths, followed by Tamil Nadu, West Bengal, Telangana, Maharashtra, and so on. As I said, if we compare deaths for 1 million population, then it is not south, rather it is northeast that have the highest burden and is followed by south. In terms of now, the same if you across the states, what would happen? Now, Uttar Pradesh that have highest number of deaths. Now, if you see per million population, it is just the deaths due to alcohol-related liver diseases is just 111. It is from the bottom. It is the fifth, the least being Lakshadweep. But in this case, if you see at all India level, there are 160 deaths per million population, and all the southern states are above the all India level except Karnataka.
Dr. Rao, Dr. Rao, your 30 minutes is over.
Yes.
So please complete in 2 minutes. Another 2 minutes.
Yes, sir. This is the regional pattern, and this is years of life lost, and years of life lost due to disability, and hence total dailies lost across the regions. As usual, South had high dailies lost, followed by East, Central, and this is across the states, and this is disability adjusted life years lost due to ARLD across the regions. That's for 1 million population. This is productivity losses. Productivity losses are very high, substantially higher in southern region, because southern regions per capita income is very high compared to the other regions. The burden, the economic burden in southern region is sum of the central, east, and the north together. And this is the burden in 3 different scenarios. So on the whole, I'm just speaking all these. On the whole, the conclusion is the health burden per 1 million population due to ARLD is expected to be the highest in Northeast India and is followed by Southern India. But the economic burden per 1 million population is high in Southern India than Northeast. This is because of high per capita income in this region. Now, all the eastern states and all the southern states except Karnataka and the Union Territory Lakshadweep, they have high health and economic burden, and they disproportionately, the deaths and economic burden is high in this region. To bring down the health and economic burden in this region through the policies on alcohol control will also bring down the overall burden at all India levels. Thank you so much for giving me this wonderful opportunity.
Thank you very much. Is this your study completed? This is based on your UGC project, right?
Yes, sir.
Did you compare your estimates with the official estimates of Indian government?
Sir, there are no official estimates from Indian government, but I compared my estimates with whatever is existing, like WHO estimates or some indirect estimates. Yes, I got close to them.
Okay.
Because there is no economic burden estimates so far. This is my first. My study estimates are the first one, but health burden estimates were indirectly there from some sources, and I compared, and these are in line with those, absolutely in line.
Okay. Okay, now you have constructed a Markov chain with transitions from various states of diseases.
Yes, sir.
So that's really good. Now, did you study any kind of properties like ergodicity, periodicity, or anything like that?
I haven't tried also that particular thing as
I think you should study that. Yes, you should study the complete properties, and even the stationary distribution. You should see what is going to be the limiting distributions.
Yes, sir.
You have a beautiful Markov chain. That's really good.
Thank you, sir. Thank you, sir. And I also want to tell one thing. Through taxes on alcohol, various state governments are getting huge money to their exchequers, and at all India level it is about 2 lakh crore, more than 2 lakh crore, but burden due to alcohol related liver disease itself is more than 3.7 lakh crore. So it itself is outweighing the gains to the government. But anyway, the government botheration is their expenditure on these public hospitals, and productivity losses and out-of-pocket expenditure are out of their concern. As a result, the burden is heavily falling on people.
Yeah, it's really a very big concern for all stakeholders in India. So anyway, we have already exceeded the time, so I am not inviting any audience to ask any doubts or this thing. So I would like to thank you, the speaker, Shamba Singh Rao. Okay.
Thank you so much, sir.
Thank you very much for joining. Thank you.
Thank you, sir.
Thanks to Satish Kumar as well for inviting me as the chair. Thank you.
Thank you, Professor. Thank you, Professor Muralidharan, for your nice arrangement, nicely chaired the session. In fact, the time is not over.
It's not over because I have given 30 minutes because the second speaker completed early.
Okay.
So I can give more time for the other speakers. First speaker was in time. Second speaker completed early. The third speaker I have given full 30 minutes presentation and plus some few minutes discussion. So you have buffer time for 10-15 minutes.
Yeah, it's 10 minutes. Yeah. We have 10 minutes. So anyway, we have. Let us give a big clap to all the three speakers of the session.
Thank you.
And we are grateful to you, sir, for chairing the session.
Thank you very much.
Supporting us. Your sincere support and that, and we are always grateful to you, boss.
Thank you very much. Thank
you. Before going to the session, in fact, next session at 3:35. In fact, it begins at 3:35. We have 15 minutes more. So by the time we can take, I think 10 minutes we can take, and thereafter we can start the session. After 10 minutes, it's better. By the time anyone can share if you want, or this time can utilize for some collaborations or some interactions that way.
Yeah, that's right. You can have some interaction or discussion. You can even have Andakshari.
Yeah. Okay.
Good. Anyway, today is National Statistics Day. Wishing all of you the very best of National Statistics Day. Enjoy, promote, prosper statistics.
Also, we can give some inputs for the youngsters.
Yeah. That's right. See, I was just, surprised to see the map shown by the third speaker, Rao. The map, if you can recall, the map of India. Where Kerala, the maximum drinkers are there in. We believe that drinkers are more in Kerala, but his estimate and the shade. If you see the map, the shade was so gray. Means very few people are drinking. Something like that is coming out from that map.
Yes, sir. This is combining men and women.
Men and women.
If you just talk about men, then it will be.
Because it will be, the story will be different. Yes.
Yes, sir.
Good. You should promote, you should publish this study in some government, journals, or you should even discuss this report with the government officials in Mizoram.
Yes, sir. Definitely, sir.
Mizoram is the most severely affected state in terms of consumption of alcohol.
Yes, so it is. And in fact, alcohol is banned in Mizoram, but still about 12% of the people, they are drinking alcohol.
Correct. But the population is also very small. In that case, if you see, population is very small and the population is very high. So there is complete imbalance.
Yes, sir.
No doubt, population of Kerala is also very less, roughly 3 point something, 3 point plus something, some crore, something like that. So
yes, sir. Yes.
If you look at the alcohol consumption is very high there. Yes, combine both women and men. If you combine, then definitely it is going to be great.
Yes.
Good study.
Thank you, sir.
Sadish, I will also leave for some time.
Oh, okay, sir. Okay, sir.
Okay. So I have some emergency.
Yeah.
Thank you very much. I will join maybe tomorrow also. I will join. Tomorrow I have another presentation at some other place on behalf of Statistics Day.
Okay.
Today being a holiday, everyone has shifted to the next day.
Okay.
So tomorrow I am busy. So day after tomorrow is my presentation early morning. That is 9:40 or so. So I will join there.
Yes.
Thank you. Thank you very much.
Okay. Thank you, sir. Thank you so much. Rakis? Hello? Raki is there in the group? Raki?
Hello, sir. Can you hear me?
Raki, you please adjust with your microphone, and I think let us start the. Will you please introduce the chair and invite the chair if chair is there in the group? Dr. Sindhumol is the teacher.
Hello.
Okay.
Yes, sir.
Hello, Raki, can you hear me?
Yes, sir. Can you hear me, sir?
Yeah.
Okay, sir.
There is
Good afternoon, one and all.
Just a minute. There is some sound problem with you. Please.
Okay, sir. Okay, sir. Let me check.
You can switch off the another system. Two systems having the same audio is working. That's why. One of the
Sir, okay, sorry, sir. Extremely sorry. Good afternoon, one and all. Next is the special invited session in the honor of Professor Eliama Josh. The session is chaired by Dr. M.R. Sindhumol. Professor M.R. Sindhumol is the Associate Professor and Head of the Department of Statistics, University of Madras. She has published more than 10 publications in several national and international journals, and she has participated and conducted more than 21 workshops and seminars. Her areas of specialization are statistical quality control, applied statistics and outlier inference, and distribution theory. It is with great pleasure and honor that I invite you, Madam, for chairing the session. Over to you, Mom. Thank you. Thank you, Ma'am.
Or 1 minute, 1 minute.
Okay. Well, let us wait. There is a network issue. We shall wait 1 minute. Okay. Don't worry.
Professor.
Okay, teacher, please. Yeah.
Am I audible? Am I audible?
Yeah. Now it is audible. Yeah, we can hear you.
Okay.
Yes. Audible. Yeah.
Good afternoon to everybody. I'm really thankful to Professor Satish sir for me also to take part this brand event, and that too on the day of Statistics Day. And I also feel proud to introduce our Professor Kalyan Krishnamurthy sir. He is a retired professor of the Kerala University, and he is in fact the gurus of all gurus, we can say. And even now he is his enthusiasm and interest to take part in academic events is he is like a role model to all the teachers like us. He even handle classes even now, and he is a good researcher also. And he has apart from this teaching, he has done so many administrative work also. And for the South India, especially for the computer related introduction to the education, okay, I think we should be thankful to Professor. And another interesting thing I think I want to say today is he is fond of music also. And today we are lucky to have Professor with us for this National Day celebration, which is a part of this conference, international conference. And with this my few words, okay, because if we want to talk about him, okay, there are so many, okay, when I browse, okay, so many things are there. Okay, due to the time constraint, I am just concluding. Professor, really good namaskaram to you, and please forward your presentation. This people behind this conference is allowing you to talk only 45 minutes. Okay, probably we are missing that. Okay, your lectures. Okay, you please try to constrain on 45 minutes so that this will be on, the event will be on time. Thank you, Professor. Please have your slide and go ahead.
Welcome, sir. Please.
Thank you, Professor Sindhu, for
thank you, Professor.
Nice words. And beyond that, you also note that I am an alumni of Madras University.
Still, you are here and there part of the Madras University. That is what I heard. Thank you, Professor. You must visit to our department.
Okay, way back in late 1950s and 1960s, early 1960s. So with Raja Lakshmana's at our department.
Okay.
Very good. Nice that I am getting a chance to be back in a function organized by the Department of Statistics, University of Kerala, where I had been working for about 35 years. And further to that, I am very happy that I am able to present some ideas which occurred to my mind while Dr. Satish called me. And very rightly, he has placed me with a session in honor of Professor Eliama George. As far as I am concerned, if at all I call one as a professor, it is only Eliama George. Wherever we say professor is there, it means Eliama George is there. So that's it. Beyond her academic achievements, she was a great educationist, and she had contacts at international level and very well associated with Population Council in the early 70s and later 60s. She was JRS. I'm sorry, what is that? fellow FRS, that is a fellow of Royal Statistical Society. Name was proposed by Kendall himself. So that is the greatness, and she was an educationist rather than very big achiever in academic area. She brought the subject demography to India. Now why India? Even the Asian countries for the first time in the department. Actually, Department of Demography was associated, was along with the Department of Statistics, we were working together. Only later, Department of Demography was bifurcated. And apart from that, she had a wide contact by which Population Council considered her as one of the major centers. And all computing devices were available, and the first generation computer, Arithma machine, was there in the year 1966. It became out of, it went out of order, and now one can see that machine being kept in scientific museum that is available near the PMG office in Trivandrum. So those who would like to see that, you can go and see the entire history of statistical computation gadgets. So when Dr. Satish called me, I was just thinking about the current happenings with the area of computing, and I'm not going to have any slides and all that. This is only sharing my feeling of computation and statistics with you. Why I say this is, way back in the year 1959, when I started attending classes on statistics, the first lecture was by Professor Swaminathan on numerical mathematics. I remember the first words, let y be a function of x, divided difference of y1 and y2 is equal to y2 minus y1 divided by x2 minus x1. These were the first words I heard in my statistical journey. And right from there, we started computation as part of statistics initially. We belong to the area where we had only Dr. Rao's first book as our textbook, and other books were not available. Linear statistical inference was not available at that time. So we had to be satisfied with the first book. And other major, Harold Kramer was another book which he was used by the Madras University for MSc. So the classes started with computation, and the computations were all by manual computations only. Manual computation means not like this. Even if you go back to that particular time and take the question papers, you can see divided difference, use the divided difference formula and find out a value of f for x is equal to a 7 decimal number. And the answer is expected to be correct up to 19 decimal, 21 decimals. All these things we had to calculate by manual computations. And that was the situation in those days, and we had to be concerned about computing expertise. As far as statistics is concerned, that's one of the main requirements in those days, because statistics used to be number crunchy. Then all gadgets for computation were introduced as part of the course in those days. That is, after manual computation, they started using Clark table, and we never used Clark table because while computing, there may be some, say what you call some adjustments will be done in the logarithm table. We are not very quite sure whether the answer will be exactly correct. So we used to calculate everything manually, even though we were allowed to use Clark tables. And after that, we were introduced to what you call as slide rule. That is one of the major calculating tools in those days. And apart from that, we had a special course on nomography. Nomography was a subject which has gone away from the syllabus at all. I think many of you might not even have heard that particular name. Nomography, by nomography, what we can do is, if you have a function, you can evaluate the value of the function at any point. You can use it for finding out differential coefficients, etc. So, this kind of computations were there in those days. And as soon as we reach third year in the BSc course, we were introduced to manual computation using calculators. Those days, we had two calculators, one Marchand calculator, the other one being what you call as facet calculator, which many of you might have seen or at least heard about it. And in the postgraduate classes, we were introduced to computation using what we call as the electrical computers, calculators. Electrical calculators were the same as manual calculator. The only thing is the operations will be by electricity. But it will take time. In order to multiply 9 by 8, you put 9 in the slide and it will rotate for 8 times. So it will take time. Before that, manual calculator will take less time. So we used to do it in this aspect. So with this expertise, I joined the Department of Statistics, University of Kerala, and by Professor Eliama George had a lot of projects. Some 4 major projects were there. One of the projects was nutrition project, a project associated with Sukhatami. Sukhatami used to come quite often, frequently to the department and give instructions. And I was one who was assigned the job of computing the required computations for this particular work, by Sukhatami nutrition work. So we were doing this using, at that particular point of time, department had the first generation machines, computing machines. That is a punch card. Apart from that, you have a collator, you have a printer, kind of things. They're all valve-based machines. So you put the machine on and you go for a coffee and come back. By the time the machine will come to life. So this was the situation in those days. And all that you have to do is, you have to make computations by serially connecting 4. That is, there will be a board available with holes, and there will be connectors. These holes are to be connected to prepare tables and put it in the collator and get it. It's a very, very difficult process, and which was done very efficiently in the department in those days. At that time, somewhere around 1972, the University of Kerala borrowed a computer from the ISRO, which was kept idle, IBM model 1620, installed it in the Palayam campus, and the computer, not like this, what you see nowadays, the computer will be there, you have to go to the computer, and 2 persons from the ISRO were manning that particular computer center. So this was the situation. Now see here, I was working on the project on nutrition, where a lot of computations were involved. I used to do it with hand computing, hand operators. And there is a computer sitting in the Palayam campus, no one uses it because nobody knew what to do with the computer. There was no course available, no book available, nothing was available. Only the 2 personalities from the ISRO will come and operate the computers. They won't even tell you what to do. So actually, the computer was sitting idle, no one was using it. Professor one day gave her peace of mind. You people are all very big mathematicians and statisticians. You people are unable to work with the computer. Then, I don't know how I took the challenge. I told professor, okay professor, I will do this project work with the computer. Give me permission to go to the computer whenever I feel like going. Then she said, okay. Then I went into the computer center with no idea of what computer is, and somehow or other, with God's grace, by trial and error, I learned computer programming in just 1 week. Oh, it's a big story, and I don't want to spend more time on this. And somehow or other, I came to do programs, and I wrote the program in Fortran for the entire project and got the results on the 24th day, as I promised. Professor did not believe that I did it. The next day she called me and asked me to write a program for another problem sitting in her room. I did it, and the program went through very well, and she started providing me all facilities to improve my ability on this. And this is how I come into the computer as such, as you see, the second generation computer. The language was Fortran 4 that we started using. And at that time, Population Council sent a letter to Professor with a request that using the data, they try to fit a mixture of normal and gamma distribution for the data. A mixture means, it's alpha 1 F1 plus alpha 2 F2, where alpha 1 alpha 2 adds up to 1. So this is the condition. So Professor called me, can you do it with the computer? Because without computer you cannot do it. Then I said, I tried my ideas on the forming of tables for the project work, but I do not know whether I will be able to. Let me try it. Then I sat down. That was a real learning experience that I had. University Department of Statistics, University of Kerala, is to be taken on the head in the sense that whatever you want to learn about statistics or computing, you can go to the library and you will have an answer to that. That excellent ambience and available literature made me no problem at all. It was great. And there is a big collection of tracts for computing. Because if you take a mixture of normal and gamma distribution, you will see that you have to operate with gamma functions and log gamma function and double log gamma functions. So these are all how to compute them. Actually, the department had all the required materials for that, and I used sit and study and develop the methods for getting that parameters, estimates. Actually, that you call nowadays as EM algorithm. As far as the machine language is going, you call it as EM algorithm. Without naming it as a EM algorithm, I developed a program for that in those days, 1972 itself. So it's a very funny thing. The computer was a very slow computer. It takes a lot of time for computing. I gave the program after every verification, morning 8 o'clock. And evening 5 o'clock, I go to the computer center. Still, the person says that, sir, the program is running. Only 3 cards is put out. That is, the output will be in the form of punch cards. Then I said, what do we do? Then we'll wait for some time, sir. Then we waited until 8 o'clock. One more card came, 4. And that is where practical and theory are two things you have to understand. See, in the theory, we say it's a convergence process. That is the estimation of parameters for the mixture of the two distributions is a convergence process. In the theory, we say convergence means if it converges to the 7th decimal, you stop it. But with the computer, if you put 0.0000001 as a stopping rule, it has to go on doing it for hours together. So the 4 cards came out, and I didn't know that is the result that is wanted. So I brought the 4 cards, expecting that professor is going to give her peace of mind. But she was very happy because the result started converging at the second iteration itself. And she said that this is enough. So that is how the first statistical computing for estimating a parameter of a mixture of 2 distributions I did as the first program in my academic career. So this is the achievement. And so I was very happy about it. And after that, professor retired. I was the one who could program a computer right from 1972 to 1986 when the personal computers started coming in these areas. So, taking that as a possibility, the World Bank approached me for a computing because it happened that there was a common survey of determinants of fertility in India, in Kerala, Karnataka, and Sri Lanka. So the principle was whatever data is collected, the data should be operated there itself, manipulated there itself. So they approached ISRO, but ISRO said they won't take this external work. So they directed, because they know that I will be able to do it, so they directed the World Bank towards me. It's a big work, 9 different schedules, and 8 different sets of programs you have to generate. That is, the data has to be verified and it should be put in a particular order and it has to be used for specific purposes and results are to be produced. In that case, I am really thrilled. That is what I'm saying. I was just thinking about it and Professor Satish called me and I thought that I should share this excitement. That is excitement that I have. Here, people are talking about artificial intelligence nowadays. And artificial intelligence means you create an agent who will be able to do certain things by ordering them. Similarly, here what I do is, in the World Bank project, there was a particular requirement that the data should be checked for consistency. What do you mean by check for consistency? Suppose you ask the question, how many children are there? No children. And what is the name of the first child? You answer that means it is inconsistent. So no child means there should not be a name in that particular column. This has to be checked. You won't believe it. I also won't believe it. I created a program which will automatically check for these inconsistencies and will provide answers that will help the manual operators to find out the exact place where the mistake has taken place and do it. So this was one of the major things. That is what you people call as artificial intelligence. I did it in the year 1980 itself with this, if you want to call it like that. Based on that, I was offered a job also by World Bank, but due to my father's condition, I did not take it up. So this is the major work that happened in my academic life. And after that, everything started moving in a totally different dimension. 1986 or 87 somewhere, we went for academic program in Madurai Kamaraj University. In Madurai Kamaraj University, I had to give lectures on 4 days. So I stayed there. And I visited the botany department that's there. And there were few computers, there were few, on table certain thing is available, something is covered. I asked them, what are they? They are personal computers, sir. We don't know what to do with that. Then we sat in the night and started trial and error and finally found out the way how to operate that. And I executed a program in BASIC as the first program and make it workable. Once you come back in the Department of Statistics, we had our computers brought in somewhere around 1989 or so, 89, 88, 90 places. At that time, Dr. Aran Pullai was doing his research in his area and students were doing the research in the associated topics. One of the major work was Mittag-Leffler distributions and also alpha-Laplace distributions. Very high sophisticated distributions, and we started to work with them, and the entire probability tables were generated using the simulated exercise for Mittag-Leffler and alpha-Laplace distributions. So this was one of the major work that we did with the computer at a higher level of computing. By that time, the entire scenario was changed because of networking, and the internet started coming in. and people started talking in different tones, which we could understand as a statistician, because statistics was more concerned with number crunching work only. Then Management Institute was started in the University of Kerala, and we had to take classes for them with respect to statistics, and I did it mainly. And for them, concept of decision was in different dimensions. Initially, they did it with data using statistical software, and in between, I would like to say that there was a software for statistics called SPSS, which was before 1995. All computations were disk-operated systems, the DOS system as we call it. That means you have to remember every place where the data is residing. This GUI, graphic user interface, came only in 1995, and so it was a situation where this SPSS was made usable. Because I sat one day without any instructions, nothing. Some doctor brought SPSS disk, and we made it work in that. Similarly, this text also was available by it was brought by one of the professors, that was also made workable without any instructions. By trial and error, we did all of them to work. And at that time, the management system started using computers in a different level, and the concepts of management information system came in. Management information system consisted of data supported decisions, and the development was in a totally different dimension, and data was used, and we are moving towards automation at that time. By looking at this, what I remember is data started flowing in like anything, and data use, you have to be at pace with this. You have to run along with the development data storage facilities. That ended with a concept of data mining. That is, data is available in large quantities and kept somewhere, and you have to use the data to take decisions. That also we had to tell them how to do it. So these are all parts of computations, and we are doing it like that, in that manner. And this started moving, and finally the data availability is so big that manual use of data was not possible. So they started thinking of the computer himself finding out a way to look at the data and answer. That gave birth to what you call as machine learning. So this machine learning also was started at a particular stage, and it came like this. And why I choose to share my views on computing is because very recently I came at, many of you might know this ChatGPT is something that is the AI tool that has come in, and this AI tool is mind-blowing, unable to expect, unable to think that these things can happen, because it is not like you people. I have been working with this kind of computation right from manual computation to this level. So that means to work with this ChatGPT, what is the difference, sir? See, I took at least 10 days to write a program for estimating the parameter of a mixture of two distributions, one normal, another one gamma. Here, you tell him to write a program for that ChatGPT fellow does it. You ask him to write a program, he does it. And you ask any question in statistics, he answers. And I was just trying, because I have a lot of time now available, the computer is there, ChatGPT is free, so I go on checking with whatever that I taught. I just ask the question, how do I put the students to linear estimation? You won't believe it. The way in which I taught in the classroom, that fellow says that you have to go in this way. So these are the things that is happening, and I am unable to believe. But of course, there are a lot of confusion with respect to identifiable problems. That is, you ask him to write a story, about your Madras. He will write a story about Madras, but unless you know the story of Madras, you cannot say whether it is correct or not. The story will come. So that kind of change has happened, and I was trying to make a PPT at that time. It said it was not possible, but now there are methods by which you provide the information, the PPT is automatically generated by ChatGPT and given to you. This is also possible now. So I don't know where we are going to end with. However, things are going to be very happy for you people in the future, and I think that you will be able to understand. Because why I am taking this topic is, imagine the problems that we face and think about the facilities that are available for you, which are not available for us, and try to make yourself adapt to what is available and try to put more directives towards understanding these concepts. Anyhow, this is the work which I wanted to share. I am very happy that I am able to complete it. I will stop at this stage. Thank you. Yes. If you wanted to ask any question, ask me to stop.
Thank you, Professor. You are one time. Okay, another 2-3 minutes. Okay, if anybody having interruption from the professor,
the elders will go on talking unless you control it. Don't end. Yes. Thank you. Thank you.
Thank you, sir. Thank you. You have given a brief history also. This is time to interact. Just 1 or 2 minutes. Okay, those who are want to interact with the professor, then please raise your questions or.
I'm ready to answer. I don't think that what I told you is only sharing my experience. That's all. So any questions are there? I'm ready to answer. No problem.
Hello, ma'am.
Yes, sir. Yeah.
Yes.
I just don't want to ask any questions, but just thank him profusely for what he has given us, the information. It was really marvelous information he has given. The history, that how the things have started. Now we have come to that level that we are using computers frequently. But it was really very interesting to see the journey he has shared. Thanks a lot, sir.
Thank you.
Thank you, Professor, for coming and encouraging us. You just shared that how you faced all the challenges and then how the computer history get along with your life experience. Thanks, Professor. On behalf of this conference committee and on behalf of myself also, I am really feel thanks, sir. Thank you for sharing your experience. The next speaker is Professor Sudip Kumar Kattamanin. Professor, Professor, are you ready? May I know, Professor Sudish Kumar sir is ready. I request the organizers to please contact him.
The speaker is there. Thank you, Kalyanam sir. Thank you so much for sharing the experience and motivating the students in that. Thank you, sir.
We will wait just a few seconds for Professor Sudeep to join with us.
Trying to join. I think he has some emergency.
Let us wait for 1 or 2 minutes.
Yeah, let us wait 1 or 2 minutes. The time we can.
Meanwhile, if anybody having an experience with the Eliama ma'am, okay, you can share. Yeah. Because this is an exclusive session in honor of Madam.
In fact, we have, even though the talk is up to 4:10, we have time, no problem, because the next speaker at 4:15 scheduled. Why? Because there may be discussion with the talk of our Kalyanam sir. That's why. So that that is 5 minutes devoted there.
Yes. Yeah, we have time.
Probably several ask some questions. That is why some discussions. Maybe there is some scope for discussion after the talk of our Professor Kalyan sir. That's why. Thank you. Sir, you are muted. Please unmute if you are talking in the.
Professor, please unmute. Professor, please unmute.
Yes. So this is an occasion where there is some time available. So naturally we can spend it for better purposes. So I have around 55 years of experience with statistics, learning and teaching, and which may be useful for anyone who is interested in this area. I am only happy to share my experiences with anybody. Of course, these people know how I used to be in the department when I was there. So there is absolutely no restriction, nothing. You can ask any question. You can call me by name, no, even not at all worried about it. So lot of things are happening. Actually, all these things happened just because very recently I came across a student who wanted to estimate the distribution, parameter of the distribution, having 6 parameters. I said that you can go with maximum likelihood estimate, and the student said how to do it, sir. Now I am heard that these are all available in Python by simple just giving 1 or 2 lines of commands, you will be able to achieve it. And then finally, the student found someone who could do with these things and got the estimator within just 1 day. That was the case. So that made me to think the kind of effort that I put for estimating the 4 parameters of the gamma normal mixture way back in 1972 and compared it with this. So that is what the reason why I started giving this particular topic as a situation, so that people may ask questions towards that and we can go. Anyhow, I think that the speaker has arrived and you can go with the next stop.
Yes.
Yes.
Thank you, Professor. Thank you, Professor. I invite Professor Sudhir Kumar Kattamannin to on your mic and video. Yes. Yes.
Thank you.
Professor, are you ready?
Yeah.
Okay, thank you.
Shall I start it?
Yeah, I'm going to start. Good afternoon to one and all once again. And this is a special session in honor of LMM, and our next speaker is Professor Sudhir Kumar Kattamannin. He's an associate professor in Indian Statistical Institute, Chennai. So I'm really happy to see you. One more person from Chennai. Okay. And his work experience is okay. He is working in ISI, and he even did his postdoctoral also from ISI. And his academic qualification, if you look at, we can see so many postdoctoral fellowship he got. And he is a postdoctoral fellow from the University of Hong Kong. And he got Indo-US Fellowship of the Michigan State University. And I told you that he is the postdoctoral fellow from ISI also. And he got his PhD from Cochin University. And he did his PG also from Cochin University and UG from Calicut University. He got award of Dr. C.R. Rao Gold Medal in Statistics. And in fact, he has so many awards he got, including U.S. Nair Memorial Young Statistician Award and Indo-US Research Fellowship. And he is a very good researcher. He published more than 42 papers, and even one book also published. And he's currently supervising PhD students. And he is a member of an editorial committee also. On behalf of this organization, I'm welcoming you, sir, and I'm really thankful for coming on time, and you are asked to present your findings within half an hour only, sir. Please go ahead. Thank you once again.
Thank you, Sindhu, for kind words. Today, Professor Srinivasan was in our institute. He delivered a talk on Mahal of this distance.
You were celebrating ISI was celebrating, right? Okay.
Yeah. So anyway, I choose this topic because I know there are several research scholars in the department was working in this extropy, which is somewhat a new area. I can see that about 20-30% of the papers published in this area is from Department of Statistics, Kerala University. So that is why I thought of presenting this. And this is actually based on my some of my recent works. And in this talk, actually, we exploit entropy, extropy, and its relationship with some reliability measures, then we will see that all these measures can be bring into the platform of probability weighted movements, so that the inference associated with these measures become very easy. So this is the idea. So this is the basic concept. Then generalized entropy measures. Then we talk about relationship between entropy and extropy. Then we talk about relationship between extropy and GMT. Then we talk about this how we can bring all these measures in the framework of probability weighted movement. So this talk, as I mentioned, is based on these 3 papers published with Sridevi and Professor N. Balakrishnan in McMaster University. So all this talk is actually based on these 3 papers. These are the 3 authors in these papers. So you can say that this work is associated with Sridevi UP, Wsta, Cochin University, and Professor Balakrishnan, McMaster University. So before going to the details, I will just give some notations. This is 2-3 notations only we need. So this is the we know we have a survival function, which is very important in reliability analysis, and then hazard rate. Then if this is a very simple result, and if you have a positive random variable, you can write this expectation as integral 0 to infinity f bar x dx. So this result, if you know, then you can do a lot of things. Simple results only, but you can. And then another 2 results we used frequently is the expectation of maximum of x1, x2 and minimum of x1, x2. That also you can write this way. If you have a minimum, you have f bar square x is the survival function. So you can write the expectation as that way. So we have integral 0 to infinity f bar square x dx is the expectation of minimum of x1, x2. And the same way you can express the expectation of maximum of x1 and x2. So this is what. So everybody is working there. So in many practical situations, measuring the uncertainty associated with a random variable is quite important, and many measures have been introduced for this purpose. So the famous one is, we have the Shannon entropy is given by this definition, expectation of minus log f of x. And then we have different kind of modification and alternative definitions have been proposed in the literature. And so this is the some of the highly cited work is in this direction is the cumulative residual entropy introduced by Rao and others, which is given by this form. And then we have a weighted version of that one, which is the x into f bar x into log f bar x. And then we have cumulative past entropy, and then we have a weighted version of this. So these 4 measures have been discussed extensively in the literature. And there are some other extension also is there. So several extensions of Shannon entropy are available in the literature, obtained by introducing additional parameters so that these measures become sensitive to different characteristics and shape of probability distribution. So this one important generalization of Shannon entropy is due to Tallis, and this Tallis entropy is defined this way. So there are recent work which generalize this Tallis entropy, and some of them are also from Cochin University, and you can see that this is the work by Rajesh and Sunoch. They actually defined the cumulative residual Tallis entropy and given by this form. And then they have a weighted version introduced by Chakrabarti and Pratha. And then there are several other versions also available. And then you can see that this is the cumulative Tallis past entropy, and then we have a weighted version of that. So I'm going very fast because this is the existing things. So now you can see that there are several modification and extension of these measures. Then when I talked to Professor Bala, he told Sudhesh, people are working on these things you think about one measure which you can bring all these things to our measures. So that is why we thought of these measures. You can see that this is the equation number 1. So we defined a generalized cumulative residual entropy of X, which is defined by this equation number 1. And you can see that for different choice of this W and pi, one can get most of the entropy measures. And I will show you one thing. You can see this actually table. We have discussed this cumulative residual entropy and cumulative residual Salis entropy and other things. You can see that this is the special case of that generalized measure defined. So for the particular choice of this W and phi u, you will get this all these measures. So now this is the residual past entropy. This is the definition, and you can see that very simple way. You can see that you actually getting from our generalized measure, you can deduce this expression. So it's not difficult, very easy. So that is what. So you can see that we have this cumulative residual entropy of Rao and others. So now you can have a generalized cumulative entropy. Here earlier we have a generalized residual entropy, and here we have a cumulative entropy. Somewhat similar. You are in one case you are considering the X is greater than u, and here you are considering X is less than u. Again, if you see that for particular choice of W and phi u, you will get several measures which is available in the literature. So these are some of, you can see that you can reduce from this weighted version. So then this is another measure which is called the Sharma-Taneja meter entropy, and here you can see that this is defined equation number 3, and there is you can generalize this to residual entropy and past entropy. This is actually, we generalize these things because whenever we talk about this generalized measure, then some of the referee asked us to compare with these measures also. So that is why we show that if you can define this cumulative residual entropy of you can see that this also a special case of our generalized measure. So you can, so in brief, if you think about these two generalized measure of entropy, most of the what's available in literature can provide this general framework. That is what the idea. So now we can use this, in fact, to obtain some relations between extropy and other measures. So this is what another important work. So apart from entropy, extropy and its properties have also been studied for quantifying the uncertainty associated with the random variables. I will spend some time only here because most of the people are working on in this extropy. Using these new entropy measures discussed here, we established some relationship between entropy and extropy measures. I know there are some discussion by Professor Sattar and his student on these topics. So for a non-negative random variable x, extropy is defined as Jx is equal to half into 0 to infinity f square x dx. And then we have several extension and modifications are done in recent time. And unfortunately, I can see that people just see, if you wanted to modifying, be careful. I want to say that, see, you know, in the earlier case, you replace f by f bar, you replace f by capital F of x. Here we have a small f of x. But you see, if you are replacing the small f by capital F, then the measure is not actually this integral is not convergent, it's a divergent. So you cannot measure, you cannot define a measure which is divergent. So be careful while there are some literature is there. So I don't know, referee may not be looking at the technicality of this detail, but be careful while modifying the measures. Just you cannot blatantly put f small f by f bar. Then you can see that some measures we have cumulative residual extropy, which is defined these things. And you can see that one another interesting point I would like to mention that some of these measures actually are already available in the reliability literature. So unknowingly they introduce these things. So you can see this, then we have a cumulative entropy is defined as this way. Now, in the beginning, I mentioned that if you have a positive random variable, you can express the expectation as the integral of the survival function. So here you can see that what is f bar square x is the survival function of the minimum, and in the 1 minus f square x is the survival function of the maximum. So then if you can identify that, then the inference problem becomes very easy. Actually, we use that idea and then propose some, discuss the non-parametric estimation of these measures under right-censored cases. So as I mentioned, there are several papers from the department. Sadar and Nair introduced this cumulative residual extropy, and then they introduced a weighted version of the cumulative extropy. And then we have, they also defined that dynamic survival extropy like this. And one can see that this dynamic survival extropy is actually some reliability characteristic. You can see that they express this as half into expectation of minimum of x1, x2 minus t given minimum. What is this? You can see that this is the mean residual life of a system. What is that? Mean residual life of a system which is connected in series. If you have a series system, you know minimum of x1, x2 is the lifetime. So this is actually, you can see that the dynamic survival extropy is nothing but some reliability measures associated with the series system. So then, this is actually, Kundu introduced a dynamic cumulative extropy instead of a residual. So you can see that here you have 1 by 2 into f square t into 0 to t f square. If you are actually truncating the variable, you can use the f. You can use f. But if you are integrating 0 to infinity, you cannot use f. So that is you have to be careful. And here also you can see that this measures also is the mean past life of a system which has two identical components which is connected in parallel. So this is what we have. So and this is the actually connection between entropy and reliability measures. And now you can see we have a connection between entropy and extropy. So this is what you can see that we have. You can write the relationship between extropy and entropy. If somebody is interested, I can share. I can send to them my slides. So this is again we have for an open derivative. You can see that there are several relations are there. So maybe I can skip some of these things and so there are several. This is what the problem with my slide is. Actually, I made a very bullet point, so I have to. Yeah, this is the connection between extropy and entropy. So you can see that GCX is equal to 2CJ into the expectation of X. So you can have this type of relations, and then connection again between entropy and extropy. You can see if you have Z is equal to minimum of X1, X2, again, you know, this is the lifetime of a series system having two identical components. And if you have a parallel system, you know the lifetime is the maximum of X1, X2. Here we have a series system. So then we can define the generalized residual entropy associated with the Z as this way. This is the actually the generalization, maybe the exact definition using our generalized measure. Now, if you have these things, you can see that for the choice of W is equal to 1/4 and phi Z equal to Z, you can write this way. No, so now you can see that this is also something related to thus the generalized residual entropy associated with Z is the weighted average of dynamic survival extropy. So you can see that the relation between residual entropy and dynamic survival extropy. So the same way as I mentioned, you have this result when you consider a parallel system. So we have, you can see that this is the how actually we are defining. We are using the same generalized measure, and for us, what is the density function associated with the maximum of X1 and X2. So use that. That is why we have a 2 here. Then you have f of u into d of f of u. So 2 into f of u, d of f of u is the density function associated with the means density function of a maximum of X1, X2. So this is what we have. So again, for the choice of w equal to minus 1/4 and phi z is equal to z, one can see that we can again write this generalized cumulative entropy associated with Z as the weighted average of the dynamic cumulative entropy. So there are a lot of connections between. And then this is the, again, we have a connection between entropy and GMD, and this GMD also has a very good relation with the Department of Statistics, and Professor Mutadu has done a lot of work on Gini index. Unfortunately, he passed away last month. So he had a lot of work on this Gini mean difference and associated measures, and highly cited. Something happened. Can you see my slide?
Yeah, but
yes.
Now it is minimized.
Now it is minimized.
Now it's fine?
Yes.
Yeah, fine.
Yeah. So this is, and you can see that Gini index can be written as in terms of GMD. And in fact, Gini index means two definitions, one based on Lorentz curve and one based on Gini mean difference. So Gini mean difference is the actually expectation of mode x1 minus x2. And then you can write, this is also a very simple expression. You can see that we have a mode x1 minus x2 can be written as maximum of x1, x2 minus minimum of x2. So that is why you can express this GMD in this way. So some of the simple identities may be very useful to infer something. So you recall the definition which is given, then you can see that from that, if you put f bar w equal to f bar u and phi x is equal to 2x, you can equate this entropy and GMT. And then generalized to cumulative entropy and GMT, this is what we have, both. So you can see that. Now, this is about 2-3 minutes are there. If anybody is having some question, I hope I can answer.
Sure, Professor, sure. As Professor said, okay, please feel free to interact with him.
Anyway, thank you for Sadiq sir for inviting me for this program.
Thank you. Please, thank you.
Is anybody wanted to ask anything related to his presentation?
Yeah, you can write to me. If somebody is interested in this presentation, they can write to me.
Can I ask something? Yeah, because you were talking of the relationship between Gini mean difference as well as the entropy. So I think I had seen some slide where you were also mentioning the Lorentz curve, etc. Also, is there any
actually,
between these and
yeah, please ask.
Is there any relationship which you are talking of this entropy measures as well as the Gini mean difference in vis-a-vis the Lorentz curve also? Is there any work in this direction along with this entropy? Because entropy is generally used in the inequality concepts.
Yeah. Actually, as I mentioned, we can define Gini index in two ways. One is based on Lorentz curve.
Yeah.
One is based on Gini mean difference. So I consider the Gini mean difference setup, not the Lorentz curve.
Mean difference is also related with the Gini coefficient also.
Gini, that's what I'm saying. So that is what that setup is I use.
On 2 mu, because I think in that direction also one can associate its significance with the, you can just say the diagrammatical representation of the Lorentz curve.
Maybe, yeah.
Okay, thank you.
Yeah, welcome.
Thank you, ma'am. Thank you, Professor.
Yeah, welcome.
Yes. I personally thank you as a chair of this
Actually, sorry, I have to leave. Actually, I am in Hyderabad. I am going to Chennai. So sorry, otherwise I should continue here. At least for this
time only, Professor.
You can, yeah, please. Okay, for the time being, you can leave, and tomorrow onwards, please. Yeah.
Thank you.
Thank you.
Yeah.
Thank you. Thank you, Professor.
Yeah.
Yes. Then the next speaker is Professor Sangeeta Arora. Professor, she is a professor of statistics in Punjab University, and
Please unmute your mic.
Sorry for the interruption. She, Professor Sangeeta Arora is a professor in statistics of Punjab University. She did her MSc, MPhil, PhD, everything in the same university, and that is actually, in fact, really fantastic. And she has teaching experience, more than 39 years of teaching experience, both teaching as well as in research. And she has supervised 8 students, awarded PhD for 8 students, that is now also supervising 2 more students. And she published a book on Bayesian estimation and related inference for Pareto distribution. And she's one of the authors of that particular book. And she received the 8th Venus International Women Award for her lifetime achievements in statistics in science discipline in this year. So I think just like our Ailia Mama, she is also one of the pioneering faculty, women faculty.
Women statisticians.
Yeah, women statistician. We must congratulate her because this year she received it. and she has published more than 50 research articles, and she is in an editorial board of many. She's in the editorial board of many journals, and apart from that, she has administrative skills also. We can see so many administrative positions she adore in her university as well as in some other institutions also. We are happy to have Professor Sangeeta Arora here. Professor, on behalf of this organizing committee, we thank you for accepting our invitation and come for a presentation. Please go ahead with your presentation. You are requested to present within half an hour for the maintaining of the time. Thank you. Please go ahead.
Thank you, ma'am. Thank you. Thanks a lot for giving the brief introduction, nice introduction. I also like to thank Professor Satish for giving me this opportunity for the last so many years for interacting with all the great statisticians on this platform. So I am just now going to present. So let me first share. Just 1 minute. Is it coming or not? This is not coming. Let me just again try.
No issues.
I will just see.
Yes, it is.
Yeah, it is fine.
Is it okay? Yeah.
Yes, ma'am.
Okay, I start with it. So I will be talking about the Bayesian estimators of the process capability indices in case of non-normal distributions using Gini mean difference. So this will be my roadmap. So I will be first giving the brief introduction about that.
Madam, please maximize.
Maximize.
Oh.
This is already my PDF is there.
It is okay.
I think if I will just maximize it, maybe
No.
go to
view and full screen.
That's
full screen only. Is it okay now? Is it okay? Yeah.
It's okay. It's okay, ma'am.
Okay, right. So I will be talking about the case, what is the case of the normality in case of PCIs, and then estimators of PCIs for both the distributions, and then some simulation studies being done, and the real life data sets and references are there. Okay, I start with the introduction. So what is the process capability and what is the process capability indices? The most popular statistical measure of process capabilities, which is used to measure the ability of the process to produce output within customer specification limits, is the use of process capability indices, or we call it PCIs, or the process capability ratios. So these are the references. So generally, once we just talk of the statistical quality control, we talk about the processes under control. At the same time, it is important to know whether the process is capable or not, because process may be under control, it may not be capable. So capability is seen vis-a-vis its specification. What are the specifications? So there are so many methods in which we measure it, and generally they are being done with the help of the PCIs. Process capability indices, and once we apply the process capability indices to see whether the process is under capable or not, so in that case there are three basic assumptions which we have to follow. First is the quality characteristics must be normally distributed, and the process must be under statistical control, and in case of two-sided specification, the process mean is centered between lower and upper specification limits. It means there is a centered, mean is centered between the two specification limits, and process must be under control normally. If any of these assumption is violated, our usual PCIs which we generally apply, they may not be true, they may give us the false picture. So in simple words, what is the role of the PCI? It measures process capability to produce the product within customer's tolerance range. in every process there exists a certain, and how this is being done. So we know that there is a certain amount of variation in every production. So variation in a process cannot be eliminated, but however it can be monitored, reduced, controlled. So you can take a simple example. For example, we are making cup of coffee, right? So there may be so many inputs and outputs. What are the inputs? So coffee maker, turning on the coffee maker, measuring and adding the coffee and water, and output is a pot or the cup of coffee. The variation can occur in the amount of the coffee, of the water introduced, and the performance of the coffee maker itself. Now, every cup of coffee is not exactly the same, but in most cases, the measurements are controlled and reasonably consistent, and it stays the same. So it means you can just say variations. If we just maintain the variation, it's almost the same. So once we look at the process capability also, so what is the main important thing? It is you control the variations. You control the variations and bring it according to the specifications. So that is a basic idea. And by utilizing process controls, taking measurements and using reliable, well-maintained equipment, variation in a process can have less effect on the quality of the output. So that is a basic idea. And the process can be capable of producing acceptable product on a consistent basis. And so determine how our process is operating, we can calculate process capability indices depending upon the state of the process and the method of determining the standard deviation or the sigma value. So the four well-known or most famous process capability ratios which are given in the literature, they are the CP, CPK, CPM, and CPKM. So they are briefly defined here. CP, so you can just say USL minus SLL over 6 sigma. This is actually basically the difference between the upper specification limit, lower specification limits, and this is your natural tolerance. This is known as a specification band. This is known as a tolerance band. So if they both coincide, this is equal to 1. Otherwise, this is greater than 1 or less than 1. What is the meaning of being less than, greater than 1? That is important. It means if it is equal to 1 and the distribution is normal, then we can say some non-conformities, NCs, will be produced, and they are, we just say parts per million defective item 2700, even if it is equal to 1. So generally, we just say if it is greater than 1, in this case, we can just say the specification limits and the tolerance limits both are coinciding. Still, this, how many non-conformities? They are 2700 parts per million. So that is not acceptable in the industrial setup. What is there? Generally, it is desirable that this must be greater than 1. If it is greater than 1, then you can say non-conformities, they are less than 2700 parts per million and otherwise. And in case the distribution, the specification limits, but the problem with the CP is it may not always, it is actually it is the potential, you can say, the capability of the process. But sometimes what happens, one of this assumption which I have mentioned earlier may be violated. What happens in that case? Maybe the mean is not centered between the two specification limits. So in that case, you are not getting the true picture of the process capability. In that case, in the literature, CPK, CPM, and CPMK, these are being suggested, where the idea is that you bring into picture the concept of mean also, because in this case, mean is nowhere in the picture. Here, mean is brought into the picture, and then these values have been evaluated. So because I'm not getting into this assumption in detail, so I will just skip further this, and this, in this case, the denominator is so chosen so that in case they are centered, this coincide with 6 sigma. Otherwise, you can just use into this expression. And these are, and sometimes here we can have also used we can also use the concept of D. So D is generally taken as a halfway with the length of the specification interval. And in all the assumption, PCRs are set. If all the 3 assumptions of PCRs are satisfied, CP should be used. But if any of the 3 assumptions is violated, we should use rest of these measures. In case the process is off-centered, use of CPK, and this is recommended. Right? But in case of non-normal data, one may use different set of PCRs for measuring process capability. So this was the assumption of one assumption is violated. So okay, options are there. So what happens in case of non-normality? Suppose that distribution data is not normal. It may not always be normal. Still, we are going ahead with our quality control charts basics. They are also 3 sigma limits we are using, but we are also assuming that data sometimes can be non-normal also. So what happens? What should we do in case of PCRs? So if underlying distribution is non-normal, then a number of approaches can be used. One approach is to transform the data such that the new transformed data has normal appearance. This is one approach. So you transform it to this one. Other approach is given by Luceno, who has given a new index known as CPC. The CPC is also upper specification, lower specification, 6 into pi of 2, expected value of x minus 2. T is the target value, which is halfway between the two. So this is another approach. It has also got its drawbacks and some results are available, but still there are so many other approaches. One is idea is to use the appropriate quantiles of the process distributions. So x 0.0015 and x 0.9985 to get a quantile weight PCR CPQ, which is given as such. And where the idea is in case normal distribution, what happens in case of normal distribution? This value is mu minus 3 man, and in this case, it should be mu plus 3 sigma. So if we just put them there, it again becomes the 6 sigma. So it says in the normal distribution, what are the values which are giving you this range 6 sigma, which is the natural tolerance region of natural tolerance range of the distribution. So you work accordingly in the other distribution also. So this approach is also being used in the literature, and claimants also propose a method for determining the quantiles based on the Pearson families of distribution. Sorry, this is some superfluous. And now the index on which we are going to work, that is another process capability ratio suggested using CP theta, that is given by the Cots and the Johnson. This is USL minus LSL upon theta sigma. Instead of 6 sigma, it is theta sigma. It is being suggested where theta is so chosen that the proportion of conforming item is not greatly affected by the shape of the distribution. It means non-conforming articles, they are not coming up. It means you can fix the level 1%, 0.1%, whatever it is appropriate. You choose theta accordingly for the various distributions where it is not normal. Right. So these are the various, you can say, the PCIs which are available in literature. Sometimes we also call them PCRs. Now, what is there? You can see that somewhere here sigma is involved, that is the parameter. Somewhere here you can see the mu is involved, that is also parameter. So once we estimate them from the data, we take the data and then take their estimates. For example, replace sigma by its estimate sigma hat. Now you can see in literature, there is not one estimate of sigma, and in quality control, generally, we know that we prefer range over to the standard deviation. But still, there are so many options available. So in general, estimates of the probability capability indices are obtained from data, and capability of the process is measured by these estimates. Process capability indices are studied and analyzed using, now we can estimate once the estimation is coming up. So we can estimate them, replace sigma by any of the suitable estimates. Then the next thing is, nowadays, it is not only the estimation. Now, there is another concept. Bayesian concept has also come into the estimation. Bayesian approach is also being used while we are talking about the PCIs. So several researchers recently preferred the Bayesian framework over the classical approach. And there are some of the references which I am giving you. Saxena and Singh carried out the Bayesian estimation of CP for the normal distribution, and Matty and Saha addresses the Bayesian estimation of generalized PCI for normal and non-normal distribution. And there are some other references which you can just see, they are there. Some recent paper also, we have not even included each and every paper, but we were concentrating on this. So this PCI Cots and Johnson approach, we are using it, taking into the account the non-normal distribution of the quality characteristics. We propose to introduce a new PCI taking into account the Gini mean difference and modifying the index CP theta suggested by the Cots et al. The Bayesian estimation of the new proposed index will also be carried out using two different priors and two different functions. So once we come into the Bayesian realm, naturally, so concept of priors and loss function, that will also. So first of all, how I just propose how we are doing it, proposed process capability indices using Gini mean difference for some non-normal distribution, that is exponential and uniform. We have taken only two distributions, others can also be taken depending upon which type of information you have got. So we call it CPG theta and CP sigma G theta. By the assumption of normality is violated, new indices are proposed using Gini mean difference, and which is supposed to be an efficient estimator of variability. That is the main thing. We have also worked in one paper where we have taken the case of normal only, and there we have replaced sigma by the Gini mean difference, and we have seen that the efficiency of those estimators that is much higher than the regular estimator, which is based on the range or the standard deviation. So Gini mean difference in case of sample observations can be defined as such. Already, I think the previous speaker has already given you this information. So in case of order statistics, this G can be written as such, where Xi is ith order observation from the sample. This is ith order statistics. And similarly, in case of normal distribution, it has been seen this Gini mean difference. This has got the value as equal to 2 sigma upon under root pi, and its variance is given by this expression. And why we are insisting on the Gini? Because there are certain properties which cannot be ignored. So David proved that this under root 2 pi G is an unbiased estimate of sigma in case of normality. That is, expected value of this is equal to sigma. And Gini had shown that even under the condition of non-normality, Gini mean difference as an estimate of sigma is more superior over range in terms of efficiency and its robustness. And Wsta also compared the properties of Gini mean difference and variance, and thereby discussed the use of Gini mean difference as a measure of variability. He spotted the situations where data departs from normality. The use of Gini mean difference comes into existence. And David and Nagaraja in their book compare efficiency of some well-known estimators of sigma and point out that Gini mean difference is almost as efficient as best linear unbiased estimate of sigma, even for the small sample sizes less than 10. So these are sufficient to use to say that this is an efficient estimator of sigma. So instead of using simple standard deviation, we can use this as an estimator. So using Johnson-Cots-Pearson method, the proposed process capability indices using Gini mean difference when sigma is unknown. This is given by CPG theta, the USL minus this upon theta G. And second is CP sigma G theta, the USL minus LSL theta into sigma G, where theta is so chosen that the process capability, namely the proportion of conforming items, is not greatly affected by the shape of the distribution. Also, G is unbiased estimate of sigma and can be considered as a measure of dispersions. And we can note that in case of non-normal distribution, the choice of theta is equal to 5.15. This will give approximately 1% of non-conforming product. This is the reference of my paper with one of my colleagues, Professor Mahajan. So it means if we choose theta is equal to 5.1, and we have taken this to be this criteria, in case distribution is non-normal, so then we can say, okay, we can just allow 1% non-conforming products, and in this was lambda comes out to be the Gini mean difference, and using the concept of this D, so you can just say D is equal to this much. This is the one first index which we propose, and this is the, in case of exponential distribution, sigma G comes out to be equal to this much, and this is another which we propose as so one is this, another is this. So now, similarly, in case of uniform distribution, we can call it CPGU and CP sigma GU. So this is the uniform distribution, and this is the corresponding. You can just say the index CPGU theta, USL minus LSL 5.15. So, and K upon this is using Johnson-Cots approach, and in this case, the sigma g is equal to this much, k upon this much. K is the parameter of this, 1 upon k, the uniform distribution. So in that case, we can just say CP0 in this case is given by equal to this much. So these two just appear to be very simple indices, but in this, I have not brought it here, but we have also derived their distribution, sampling distributions also in another paper. So in this case, now I am just looking at, suppose the distribution is non-normal, then how can we look at their Bayesian estimation? That is the problem which we want to deal. So naturally, first I look at the prior and posterior distribution. Once we come to the Bayesian setup, we need to have the prior and posterior distribution. So posterior distribution in case of exponential distribution using gamma prior. So this is actually a conjugate prior. So those who are working in the Bayesian, they understand that there are some informative priors, non-informative priors, and some conjugate priors also. So conjugate priors also can be the informative priors. So if this is an exponential distribution with scale parameter lambda, and then informative prior for the lambda, that is for the parameter lambda, this is a gamma prior with parameters alpha beta, where alpha beta, they are known as a hyperparameters, and this is H1 lambda, which is known as a prior for the lambda. So posterior distribution of lambda, gamma prior, this is being posterior distribution of lambda using the gamma prior. This is given by pi 1 lambda x. So this is a likelihood function. This is a general setup with the general likelihood function into this much. This is the marginal distribution which we get. So this is the posterior distribution which we obtain in case of the gamma. And after simplifying this, we can just see this posterior distribution follows gamma distribution with parameters this as well as this. And similarly, posterior distribution in case of exponential distribution using uniform prior, non-informative prior. So we have taken this as to be uniform prior. Uniform prior is just simply, this is proportional to 1. This is an improper prior also, but generally this gives us a very good improper priors. It is, I mean, you can just say we are not using any information in non-informative, but still it is going to give us a very good posterior information. So posterior distribution in this case using the same formulation, this is pi 2. And this is the posterior distribution, which again follows the gamma distribution with parameter this. So this was the case of exponential. We have obtained the posterior. Similarly, we obtained the posterior distribution in case of uniform distribution using Pareto prior. Pareto in this case comes out to be the conjugate prior. So there is a particular list of the conjugate priors given in the literature, and we have used into that. So these are the information, these are the observations from uniform distribution. This is a PDF of the likelihood function for the uniform distribution. And posterior Pareto prior, this is being given as such, where this is the indicator function, delta is less than equal to k. So we can just say the delta is nothing but the shape parameter, the Pareto distribution, and this we can just use this t is greater than 0, and hence the posterior distribution of k using Pareto prior, this is given by pi 3k. And this also follow the posterior distribution, again follows the Pareto distribution, right? And posterior distribution in case of uniform using the uniform prior only, which is a non-informative, and this comes out to be equal to pi 4. I'm just skipping these results because they are just the derivations. So I have just reduced the derivations, still one has to do it. So next thing is, what are the Bayes estimators of PCIs for both the distributions? Bayes estimators of PCIs of CPGE and CPGU for exponential and uniform distribution under two different loss functions using different priors. So once we just take the Bayes estimators, we have to take the loss functions. So there are two types of loss functions given in literature. The easiest one, the simplest one is the self. So squared error loss function, which is defined as, I mean, you can just define the theta hat is the estimate. So theta minus theta square, where this is the expected value of theta given x. This is the Bayes estimate of theta into this. And asymmetric loss function, they are more realistic because in practical situations, one asymmetrical loss function, because sometimes what happens, overestimation and underestimations, both can be dangerous. So if you want to consider this, so there are different types of asymmetric loss function. One such loss function is the GELF, or the generalized entropy loss function, which is given by this expression, where you can just see this is the where b is not equal to 0. B can be greater than 1, b is also can be less than 1. It is equal to 1, then this it is equal to -1, then this GELF coincides with the Bayes estimate given by the self. And Bayes estimate of this under this, so using these expressions, now we can drive our Bayes estimates. Bayes estimate of CPG under squared error loss function, this is given by expected value of this. Using it means with nothing but the expectation of the posterior density. So posterior density already we had obtained, and this, if we integrate it, this comes out to be equal to this expression. So they are not in a proper, very particular form, but using simulation, we can always compare their efficiency. Similarly, the Bayes estimate of CPGE under generalized entropy loss function, this is also being obtained with equal to this much. And for exponential distribution, using uniform distribution also we have obtained. And similarly, using this Pareto distribution, we have also obtained. Ma'am, I have got 5 minutes or not?
Actually, almost time.
Okay, right. Thank you. So Bayes estimate of PCRs for the uniform distribution using uniform prior. Similarly, that means I'll just take the CPGU with for both the distribution using two different priors and two different, you can just say the loss functions. We can always get their values. We can just get the estimates of these. So these are the various estimates, and this is a table in which the loss function prior and the Bayes estimates CPGE for the exponential distribution. This is being shown as we have tried. So this is for the gamma as well as the prior gamma and uniform, and this is under the self, this is under the GELF, gamma and uniform. So these are the expressions. And so Bayes estimate of CPGU, this is the second in case of uniform distribution. These are the Pareto as well as using the prior Pareto, uniform, Pareto and uniform. And these are the corresponding Bayes estimates which we have obtained. And these are the notations which already we have. Now there is a simulation study. A simulation study is conducted to assess the statistical performance of the Bayes estimators for process capability indices in case of exponential and uniform distributions. Right? The simulation study is performed in R software and the process is replicated 10,000 times, and the average of the results have been presented in the following tables, which I am just going to show. The estimated losses are computed for both squared error loss function and the generalized entropy loss function using generated random samples for exponential and uniform distribution, and by considering 3 sample sizes: small sample sizes, moderate sample sizes, and 25, 50, and n is equal to 100. And also 2 choices of the specification limits we have taken. L is equal to this and upper specification this much, because many times we have got the lower specification limit as 0, and depending upon our simulated data, we have taken these. We can vary them also. Considered in case of this exponential, and this estimated losses are repeated using different configurations of the scale parameter, as well as for the exponential, as well as for the uniform distribution, and hyperparameters are also chosen specifically. This is as sample size increases for all configurations of various parameters. And also the estimated loss using GELF loss function is smaller as compared with squared error loss function under informative. Which means the results which we get in one suggested CPI, they are almost true in the second case as well. And just we have also included, because we have used 2 distribution, exponential and uniform. So we have taken some real life data from the which follows, first of all, the exponential as well as the uniform. The 2 sets of data are being taken, and then also we have computed our CP and seen what is the simulation exercises, are they in accordance with this or not. So illustration of this purpose, the real life data was our survival times for 116 breast cancer patients treated over the period itne to itne quoted in wo times are in months. So these are the in months, and by using easy fit software, it is seen the data fits well to the exponential distribution, and p-values for the Kolmogorov-Smirnov test is given at this, which is significant at 5% level of significance. It means the value of the shape parameter of the exponential distribution comes out to be equal to this. Using again easy fit software, the Bayes estimator of PCI are obtained for the exponential distribution using informative as well as non-informative prior, and the results are given below. So you can again here see that in case of GELF, this is smaller than in case of the self, and you can say that in case of the gamma informative prior, this is smaller than it means they are in accordance with what we have already obtained. And the second set of data, which is related to the uniform distribution, the data Deshpande and Prohit we have taken of 35 units are subjected to fatigue test, and their lifetime in weeks are given by this much. Using this, it is seen that the data fits well to the uniform distribution, and p-value of the Kolmogorov-Smirnov is this much, and the value of parameters of uniform distribution comes out to equal to this, and the Bayes estimator of PCIs are obtained for the uniform distribution using informative and non-informative trials, and they are again reported here. And the findings from both the real-life examples are in accordance with those of the simulation study, and we can see that both the cases of real data sets, informative priors, result in the smaller estimated loss in comparison with uniform prior for both the distribution. The estimated loss is also smaller in case of GELF than SELF, irrespective of the prior being used. The findings from the real-life examples are in accordance with those of the simulation study, and these are the references, ma'am. And then again, thanks.
Thank you, ma'am. Thank you for the wonderful presentation. On behalf of
Very
the
insightful presentation, ma'am. Very insightful, very thorough. I'm Gopa Chattopadhyay. Thank you.
Thank you. Thank you.
Okay, yeah, one or two questions are allowed. Okay, if anybody is having. Please feel free to interact. If no questions are there, okay, we will congratulate the speaker.
I will also like to thank the chair as well as the Professor Satish for giving me this opportunity to interact with you. Thank you so much. Thank you so much.
Thank you, madam. Thank you so much.
Thank you. Thank you. Thank you.
Nice.
Thank you, ma'am. Next speaker is Dr. Shili Lin of Ohio State University. Madam, are you ready? Ma'am,
Yes.
Okay, that's echoing. Is it okay now? Okay. So let me just, that's echoing here. I don't understand why. Let me see.
Ma'am, please tell me when you are ready. Because it's echoing. Your sound is echoing here.
Yes. Can you hear me?
But yes, it's audible, but with an echo. Echo is there. Sound is echoing.
Now it is okay, I think so, isn't it?
Unmute, please. Unmute, ma'am. Unmute, please. Unmute, please. Ma'am, please unmute and talk. Ma'am, please unmute and talk.
Yes. Can you hear me?
Yeah. Yeah. Now
It's
it is
echoing.
clear. Now it is clear.
Now, can you hear me now?
Yeah, we can. We can. Yeah, then.
Can you hear me now?
Yeah, it's clear. It's clear.
Is it clear now?
Yeah, perfectly all right, ma'am. Good
I'm
evening.
sorry?
Perfectly all right, ma'am.
Yes, I'm ready.
Yes. Thank you. Thank you. Good evening to one and all present here. We have the last speaker of this section, Dr. Shili Lin. She is a professor of statistics at Ohio State University. Her research interests are statistical genomics, genetic epidemiology, and bioinformatics. In addition to this methodological research, Dr. Lin is also working in collaborative projects with researchers at Ohio State University and other countries also. She has co-authored one book, co-edited another book, and authored and co-authored more than 165 referred book chapters and journal articles. Dr. Lin currently serves as an associate editor of biometrics and statistical applications in genetics and molecular biology. She is also an editorial board member of Genetic Epidemiology. Dr. Lin is a fellow of the American Statistical Association, a fellow of American Association for Advancement Sciences, and an elected member of International Statistical Institute, ISI. Ma'am, we are happy to have you in this floor today. And I'm really okay, we are just seeing one more women researcher and achiever in this section. And I must say thank to Professor Satish Kumar for arranging all these women achievers under in honor of Professor Elia ma'am. Ma'am, please go ahead with your presentation. The organizers are allowing half an hour for the presentation. Please go ahead.
Okay, well, I would like to thank Professor Kumar for the invitation and Professor Maria Gatu for the very kind introduction. It's just special for me to be presenting in the session in honor of Professor George. I had never met Professor Aliyama George before, but her career and her work are truly inspirational. So I got to tell you a story. In preparation for the International Biometric Society's meeting, which is the International Biometric Conference, called the IBC, in Barcelona, Spain in 2018, the organizing committee decided to honor women in statistics from different continents. I was charged with finding a women statistician from Asia to honor. Countries like China, India, Japan, Korea, etc. Literally 70 emails later, through contact with Professor Bala Biswat and his former student, which happened to be also a student of Professor Aliyama George, Professor Thomas and Mathai, and colleagues from other Asian countries, I was able to identify Professor George as our honoree and put together a poster in her honor, which was displayed prominently at the IBC main hall in July 2018. Her story, together with those from 5 other women from the other 5 continents, were extremely inspiring and the topic of many conversations among the IBC participants. However, you can see here that her photo was missing. Instead, it was replaced by University of Kerala logo. And also her birth year was missing because I could not find the information, which was really a pity. Interestingly, the 5 days prior to the start of the conference on Sunday, Professor Bala sent me a photo of her, but it was too late to be included in the poster by that time. Later, biometrics decided to have a cover image of the 6 women honorees in one of its issues. And I have to seek approval from using Professor George's image. That was when I learned from Professor Bala that this photograph was actually a photograph of a painting hanging in the Department of Statistics at Kerala University. And the student took the photograph for us for the poster. So I hope that I will have a chance, maybe perhaps one day, to visit Kerala University to see the actual painting instead of just the photograph. So sorry for the long story, but my journey of finding Professor George to honor as a role model for women statisticians, especially those from Asia, was extremely fulfilling. And I thought I should share the story since this is the session in honor of her. And again, I'm extremely honored to have the opportunity to actually speak here. So today, I will be talking about sparse estimation in finite mixture of varying coefficient models. And this is joint work with colleagues from the US and Canada. So the motivating example or problem for this work is a data set collected from Fangchenggang, which is a coastal city at Guangxi province in China, which is bordering Vietnam. So researchers at Guangxi Medical University was interested in identifying factors, genetic and non-genetic. For genetic, these are the single nucleotide polymorphisms. For non-genetic, is something like BMI, folic acid. They may influence osteocalcium or OCN in short. So it's known that OCN plays a role in metabolic regulation, and it has been established that a higher osteocalcium level associated with an increase in bone mineral density during drug treatment for osteoporosis. So you would think that one's gene may play a role, and indeed a number of variants. Let me just hide this. Okay, sorry, there's something blocking my screen. I need to hide it. Okay, it's good now. So it has been found that a number of genetic variants in chromosome 7 have been indeed linked to bone morphogenetic protein. And it turned out that the underlying features of these data sets are quite complex. First, the relationship between OCN and some of the factors may not be the same across the entire population. In other words, there is population heterogeneity. So one would need to use mixture to model this. But the complication don't just stop here. The effect of genetic factors, and for that matter, even non-genetic factors, may influence the outcome unevenly over one's lifetime. So in other words, the effect is age-dependent. So if you would do a regression model, the coefficient is not constant, rather it is varying according to age, so it's really a function of age. And not only that the effect can vary according to age, the missing probability may also vary according to age. So for example, the probability of a component representing, say, high OCN may change over time. And so the goal here of this work is to revise divided method that can accommodate all these complications. Sorry, my mic is off. Oops. Oops. Can you hear me?
Yes, we can hear you. There may be some network issues. She joined.
Yes.
Sorry, someone said my mic was off. Is it on now?
Yeah.
That's fine.
Yeah.
That's fine.
No, it's fine for
So, have you heard everything that I have said, or
yeah,
the mic was off?
Yeah.
Yes.
Okay.
You have to share your slides once again.
Yeah. So let me share my slide. Sorry that okay. So then is it okay now?
Yeah, okay.
All right. Okay, so then the goal of this work is really to devise a method that can accommodate all these complications. And so then to get started, okay, so let me make it full screen. Okay, so just a sec. Let me try to make this full screen first. Sorry for the technical issues. I'm having trouble making the full screen. Okay, this is a new. I could not share screen on the other computer, so I borrow a computer here, and I'm having trouble making that full screen. Just bear with me.
We can share from here if it is.
Oh,
okay,
no, that's okay. Okay, I think it's fine now. Okay, I think it's full screen now.
Just one minute. Yeah.
Yes. Sorry.
That's fine.
Yeah, I think it's full. Hopefully that's full screen now. It's still not. Okay, you know what? I think this is fine. Okay, so I just do this. So to get started, I need to fix some notations here. And I also need to state the formulation. And so within each of the numbers of subpopulations here, we formulate the problem within each subpopulation as a regression, where Y is the response variable, in this case is OCN, and we use X to denote the covariates, and in this case is genetic and non-genetic factors, and D is the dimension of the covariates. The missing proportion and the coefficients of the effects of X on Y may change as function of age, which is denoted as U. So U is the index variable that the effect and the probability of the mixing proportion may change according to. So with the notation and basic formulation out of the way, we are ready to describe the model. So we're using pi to denote the mixing probability for subpopulation J. So this is indexed by J, which may be dependent on age. Again, as I said, this is the index variable U. We assume that the conditional distribution of the response variable given the covariates and age is belong to a non-parametric family, which is characterized by two parameter functions, where theta is the mean, so the link function G to the non-linear predictor functions here, and the other parameter function is also dependent on age. These unknown non-parametric functions are collectively denoted as psi here. So putting these two things together, our finite mixture variance coefficient model can be written in this mixture form, which look like your usual finite mixture regression model. However, I need to caution you that everything here are in terms of a function of U, the index variable, rather than constant. So in the finite mixture of regression model literature, we know that the numbers of parameters can get large very quickly, especially if your model has many components. The problem with finite mixture of variance coefficient regression model is even worse, as these are not just parameters, they are actually functions. So in our OCN example, even with just 43 covariates, the numbers of non-parametric functions that need to be estimated can get up to more than 200 very quickly. However, the point here is that not all covariates have significant effect on the response. That is, the model is sparse, and that is the typical thing with high-dimensional problem. So to be precise, mathematically, what we mean by sparsity is that we assume that it's a subset of the covariates for which the expected values of the norm of the non-parametric function is exactly 0. So in this situation, the number of regression coefficients that need to be estimated is likely much smaller than the full set. So our design of having this finding a sparse arithmetic model really adds a level of complexity to the inference of the finite mixture of varying coefficient model. And there has been no existing method that can plug in for both varying coefficient estimation and variable selection. Because on the one hand, there is considerable amount of work on FMVCR model recently, but they don't consider sparsity. Sorry that the references didn't show up here. On the other hand, there has been a lot of work on variable selection in finite mixture regression models, but they don't deal with varying coefficients. So there is a need to develop a new method that can perform simultaneous estimation and variable selection. So suppose if we have an observation of the triplets, the index variable, the covariates, and the response, then we can write down the log likelihood function of the FMVCR model. Just a reminder, again, the sign here contain all unknown non-parametric functions, including the model parameters and the mixing probability. So these are functions, not constants. There are several common techniques used to estimate non-parametric functions, including local kernel, spline, and local polynomials. In our situation, we opted to use the local kernel method, which is easier to implement when fitting an FMVCR. It boils down to locally estimate each unknown function by a constant. So back to the finite mixture regression model scenario, which is much has a lot more research and much easier to handle. So specifically for each of the index in our index space, we consider the local kernel likelihood, where K here denotes the kernel. So essentially, our model is locally approximated by a standard finite mixture regression model. So the set of parameters now become finite locally, as we only consider a finite mixture model values within the range of the data. And it's now finite dimensional as well, instead of being infinite dimensional. So for each of the U considered, we find the maximum likelihood estimator, like in finite mixture regression model, and we decided to consider only the U's that are the observed index values. So just like finite mixture regression model, the estimator is consistent, but it doesn't lead to sparsity, which is the problem that we try to solve. So in order to induce sparsity, we need to add a penalty, which is what we added here, where the Pn is the penalty function. And the lambda here are tuning parameters controlling the level of penalization on the regression coefficients. And we're using a good penalty, treating each covariate in each subpopulation as a group, which lead to uniform sparsity, as I'm going to discuss next. And so, to talk about the property of our finite, our maximum penalized local likelihood estimator, for convenience, we're going to assume that the parameter space is partitioned into two parts, with the second part being uniformly 0 for all the indices, and that these factors in the second part has no effect on the outcome uniformly across the entire index space. If this set is non-empty, then we have a sparsity model here. We are arranging our estimation, our parameter set to correspond to the same partitioning. And then we show that under a number of regularity conditions, we have uniform sparsity, which is exactly what we like, because you want it to be uniformly zero. There's no effect across the entire parameter or index parameter space. And this particular property was obtained because we assumed a good penalty. And further, we have asymptotic normality for our estimator as well. So with the local kernel likelihood approach, by adding this good penalty term, we have a modified EM algorithm that is amenable for this problem. So we brought a really complex problem into a much simpler situation. We can estimate the non-parametric function at the observed points and perform variable selection while estimating the regression coefficient through the good penalty. So it's a simultaneous estimation and model selection. So I will now show you some results from a comprehensive simulation study. Here I only show you one result. The other results are available in the paper that I'm going to give you the reference at the end. So in this simulation, we assume a model with two components. We consider several dimensions of the covariates from 5 to 50. 50 is the same order as in our real data. For the first component, the first, second, and fourth covariates are assumed to be non-zero. For the second component, it's only the first and third are non-zero. The rest of the coefficients are assumed to be zero in the model. So it's a very sparse model. And here are the results for dimension being 10 and 20, and with sample size either 200 or 400, and several penalty functions that we consider here. Oracle here is the situation where you have the known model. MMLE is the one without, is a maximum log likelihood estimation without the assuming sparsity. We see that specificity is high for both components and the combination of the settings, but sensitivity is reasonable with the sample size of 400, but a bit low with the sample size of 200 for component 1. And there isn't a lot of difference between the different penalties, but we did multiple runs and indicate that scat was a bit more consistent compared to the other penalty functions. In terms of estimation procedure, all penalties for the most part led to better estimation than the one without inducing sparsity. And finally, I'm going to turn to our motivation application, the OCN data set. Recall that we have 43 covariates, including 36 SNPs. These are single nucleotide polymorphisms, a type of genetic markers that is most commonly used in today's genomic applications. There are also 7 other non-genetic factors, which include the BMI and the folic acid. In our analysis, as I said already, we use age as our index variable. So the effect of each of these 43 covariates may vary according to age. We apply all the penalties to this problem. And it turns out, again, just like the simulation study, scat penalty gave us the most consistent results for different runs. So therefore, I'm just going to present the result using scat. We FIDIC model with 1 to 4 components, and BIC selected 2 components as the best model. And here are the results of the densities of the 2 components of the FIDIC sparse finite mixture of varying coefficient model. The first component, which is this orange or red one, has higher OCN, and I'm going to refer to the HOCN component. And the figure in B here shows the mixing proportion for these components. And as one can see here, it's actually changed over time. So in particular, we see that the probability of being in the high OCN component is starting at 60% at age 20, but then it goes to about only 40% at age 60, which is biologically interpretable. BMI also has a non-constant effect for those in the high OCN population. It has a negative impact on OCN, especially at the young age. The most significant one, and the one that we're most interested in, is the effect of a particular SNP, the genetic markers, that has been implicated in the literature. The effect of this SNP is deleterious, meaning that people who have the SNP, especially at the young age, is going to negatively impact their osteocalcium level. But the effect lessens as one ages and become more or less neutral after the age of 50. And so the additional evidence that we have explored to show that the non-constant effect of this SNP is real. Okay, so the first evidence is that there is literature support. Although the literature never explored age-dependent effect, nonetheless, this SNP has been implicated in the literature, showing that it indeed has an effect on osteocalcium. The second evidence is that we also fitted a finite meter regression model without allowing for varying coefficients, and it indicates that actually the one with allowing for varying coefficient fits the data much better according to a diagnostic workup. The third evidence is that we have constructed confidence intervals or confidence band over the entire age space, and that shows the upper bound is below 0 for the younger age group, which provide additional evidence that the negative effect for young people is real. The fourth evidence is that the non-constant effect is really substantiated because we look at the derivatives and they are likely to be 0 in the entire range of age. And so, in summary, we have developed a penalized local kernel likelihood method for finite meter varying coefficient models. And we have established the consistency in estimation and variable selection, as well as asymptotic normality. We have looked at the finite sample performance through a comprehensive suite of simulation studies. And I have shown you the result from just one of the simulations. And it appeared that the method performed reasonably well for the setting considered. This one is really important as a guidance for practical applications. For our real data analysis, we have chosen to use SCAT because we actually explored varied penalty functions, and this was the most stable. And so therefore, in practice, what we would suggest is sort of following the recipe that we have tried out, that is using all penalties with multiple rounds and choose the final model that appear to be stable with multiple runs and compare well using a model selection criterion. And we have been just using BIC, and that appear to be satisfactory. And finally, I just want to say that our OCN real data analysis has demonstrated the utility of our proposed method for analyzing data with complex features. It's not only substantiating early findings, which is supporting our finding, was supported by the literature, but we also have providing new insights into the results that not only this particular SNP and some other SNP that I didn't find you had an effect on OCN, the OCN calcium level, but the effect is not even over the entire age lifespan of a person. It impacts the younger people more. When one turns age 50, it doesn't really matter anymore. So these are the additional biological insight that we have gained. And finally, I would like to acknowledge Professor Zhengnang Mo at Guangxi Medical University for generously sharing the OCN data with us that motivated this work. And I would like to also to acknowledge the funding agencies. So the method and the application paper has just been published online on biometrics, and it's open access. So if anybody interested in, it's available. And I would welcome your comments. And thank you.
Thank you, Professor, for the wonderful presentation. Now the platform is for the interaction session. If anybody is having any queries or clarification, please feel free to interact.
I'll be happy to answer question if you just want to do it offline. Well, yes.
If there is no interactions, okay, let us congratulate the speaker.
Thank you.
Thank you, Professor, for being with us and giving the presentation. On behalf of this organizing committee, I thank you, Madam.
Thank you.
Now over to organizers. I'm because all the 4 speakers presented, and the time is on time.
On time. Yeah.
I conclude the session. Now it's over to organizers.
Yeah. Thank you, Professor Sindhu, for nicely managing the session and concluded in time. And we are grateful to you for supporting the Wsta 2023. We extend, on behalf of the organizing committee, we extend our gratitude to you. Thank you so much. Also, I would like to extend our gratitude to the speakers of the session, especially all the speakers, in fact, Professor Kalyan Raman sir, then Dr. Sudesh Katumanan, then Professor Arora, Sangeeta Arora, and Professor Shili Lin. We are very much grateful to each one of the professors who have given wonderful talks. In fact, your support, and we are really grateful to each one of the professors. Thank you so much. Thank you. Now we have the time. We can't able to waste time. With this next session is starting at I think 6:05. By the time I hope the introducing the chair and other things can taken care of. Bhagyalakshmi?
Yes, sir.
Yes, Bhagyalakshmi, please introduce the chair and
please
support. Yeah.
May I leave, Professor? I have to travel. That is very sorry.
Okay, man. Yeah, you have already mentioned that you are in between. Okay.
Thank you, Professor.
Thank you. Bhagyalakshmi, please introduce the chair and support the chair for running the next session in a smooth way, please.
Hello, everyone. Now we are moving on to the 8th technical session of WSTA 2023, which is a special session in honor of Professor T.K. Ghosh that shall be chaired by Professor Kanjan Jain. Professor Kanjan Jain is a professor and former head to the Department of Statistics, Punjab University. Her areas of interest include reliability, survival analysis, actuarial statistics, distribution theory, stochastic process, inference, and measurement error models. She has collaborated with academic experts from various universities across and outside India for research. She has several administrative experience, including as an advisor to the Union Public Service Commission, She is an elected member of International Statistical Institute Netherlands and the National Academy of Sciences India, life member of Kolkata Statistical Association, International Indian Statistical Association, Indian Society for Probability and Statistics, Indian Association for Productivity, Quality and Reliability, also a member of several national and international agencies. She has a lot of research publications and has been coordinator and member for so many training programs and conferences. Also, she is a member of UGC Experts Committee in Statistics and has been a speaker for various national and international conferences. An excellent academician with experience over 4 decades, we feel privileged to have you with us, ma'am, chairing the session today. So, without further ado, over to you, ma'am.
Thank you, Ms. Bhagyalakshmi, for a nice introduction. You see, it's an on good evening, everyone, and a very happy Statistics Day to all the statisticians. It's an honor to welcome Professor Malay Ghosh, a renowned statistician. I'll just like to give a brief introduction to Professor Malay Ghosh, though he doesn't need any. He did his PhD in statistics from University of North Carolina at Chapel Hill after completing his BSc and MSc from University of Calcutta. He moved to USA for pursuing higher academic studies and was a faculty member at ISI in the 1970s. Professor Ghosh is well known for his research in non-parametric inference, sequential analysis, decision theory, Bayesian statistics, and small area estimation. Professor Ghosh served from 1996 to 2001 in the United States Census Advisory Committee. He is an elected fellow of the American Statistical Association and Institute of Mathematical Statistics. He is a recipient of Samuel Wilkes Memorial Award by American Statistical Association and Lukács Distinguished Professor during 93 to 94. Professor Ghosh has been serving continuously on the editorial board of several national and international journals such as Sequential Analysis, Sankhya, American Statistician for more than 2 decades, and he has co-authored 2 books, more than 25 research publications to his credit, and has been the advisor of over 40 PhD students. Notable among them is Professor Nitish Mukhopadhyay. So I welcome you, Professor Malay Ghosh, for your talk on high-dimensional posterior consistency in multi-response regression models for error covariance matrix. So I invite you, Professor Ghosh, for your talk.
Thank you very much. Can you all hear me?
Yeah.
Yes, sir.
Yeah.
Thank you very much, Dr. Jain, for such a nice introduction. The thing is, as I said, it is not possible for me to flash the slides here, so someone has to help me by putting the slides. So can I have the first slide, please?
Yeah, Professor.
Next slide.
Yeah. That's fine.
Because of the Google Meet thing. Okay. Thank you. Can you make it one slide at a time? Is it possible? Because, yeah, very good. Thank you very much. Okay, this is a different kind of talk. What I will be talking today is estimation of the error covariance matrix for a matrix normal distribution. Now, the precision matrix, the inverse of the error covariance matrix, has been addressed a lot, but here we are talking about the covariance matrix itself. Now, there are a couple of things. When the paper was first written, it was just concentrated on estimation of the covariance matrix. But then recently we moved to a regression setup And as we will see, we'll talk about not only posterior consistency for estimating the error covariance matrix, but also the regression matrix. The second thing is, it is not an ultra high dimensional setup or even a setup with sparsity. In fact, within this setup, the so-called large p small n thing will not work, as we shall see. As we shall see that if the sample size gets bigger than the number of covariates, you will have posterior inconsistency. This is a joint work with my student, co-advised by my colleague, Professor Shatish Khare. Next slide, please. Thank you. I'll spend a lot of time with the introduction. Then I will go for the model and the prior. As I said, I will talk about both posterior consistency and posterior inconsistency, which will be revealed in the simulations as well. Make some final remarks. Next slide. Now, estimation of the error covariance matrix, the standard thing is the inverse Wishart distribution. It's a popular choice and attractive properties because of the conjugacy. But there is a problem. The problem is that the first one, and that is the one we'll harp on today, uncertainty for all variance parameters controlled by a single degree of freedom parameter. But then there is no flexibility, because if the different components of the variance have different degrees of prior knowledge, that is not incorporated in the standard inverse Wishart prior. Of course, they're not suitable when there is sparsity, but the sparsity is not something which we are talking today. Next slide, please. Now, first of all, just I'm giving the formula for the inverse Wishart distribution. So a random matrix sigma of dimension, whatever, Q, fixed dimension, has an inverse Wishart. With the parameters I'm using nu and psi, nu corresponding to the degrees of freedom and psi for the scale. So it is of the given form, determinant of sigma raised to the power, as I have given, nu plus q plus 1 over 2, and exponential minus trace psi sigma inverse. It is available in many books. The notable one, of course, Anderson, all the time, the second edition, first edition, second edition, and also in the books by Jim Press and many others. Now, the point is, if you use even a default inverse Wishart, so for nu, you just put q plus 1, so, and psi is in identity, what do you get? Determinant of sigma to the power minus q plus 1 and exponential minus trace of sigma inverse. And it is a simple exercise. I'll give you a hint how to get it. You get an inverse gamma 1 comma half. Shape is 1, scale is half, depending on scale or I think the rate, can't quite remember. Marginal prior for the variances. And what will happen then? In a region near 0 with extremely low density, a bias toward larger variances even when the true variance is small. The way to prove this kind of result, component-wise result, is a very simple one. An exercise even given in Professor Rao's remarkable linear statistical inference book. Take the quadratic form, A transpose sigma A. If sigma has the inverse Wishart, A transpose sigma A will take an inverse gamma kind of form, inverse chi-square actually, kind of form. And then if you put for the A, the unit vectors, you will get those component-wise distribution. for the variance components. Very nice way of looking at this kind of result. So in the one-dimensional case, of course, Gelman argued very strongly against the use of vague inverse gamma priors, primarily on this ground. He suggested instead half-T priors for standard deviations, which we'll talk again later. Next slide, please. Now, there is an interesting way. Half-T prior you can do in many different ways. You can think about a normal, actually, and then you put a distribution, a gamma, on the scale, or the actually on the reciprocal of the variance, the precision. You can get a T, and half-T is just the positive part of the T. But there are other ways. The other ways are, for the variance, you take an inverse gamma, and for the precision, you take the gamma in that way. Then marginally, for variance, you get that particular distributions, sigma squared to the power minus half, this one. And then pi sigma is becoming the half T distribution. Of course, it has to be on the positive side, so that's why the half T is coming. And special case is the horseshoe for sigma squared. If the nu is 1, what do you get? Sigma squared to the power minus half, 1 plus sigma squared over u minus 1. And this is, you can call it horseshoe. It's a special case of what people call type 2 beta distributions, or nowadays people have given a whole bunch of other names, beta prime, beta min, whatever it is, but that's what it is. Now we'll talk about a hierarchical model. Matt Wand and Huang, his student, proposed a scale mixed inverse Wishart distribution. But here comes the interesting thing. The degrees of freedom is nu plus q minus 1, but instead of using an arbitrary Chi matrix, they're using a diagonal matrix to reflect the importance of the difference variance components. That's what it is. And it is hierarchical because for the components of the matrix diagonal A1 to AQ, they're putting a gamma prior, independent gamma prior. And that is the proposal of Huang and Wand. Next slide, please. But there are other choices. The choices are given, for example, even before Huang and Wand, O'Malley and Jaslovsky, they propose log normal and positively truncated normal priors for these diagonal elements. I'm still having that particular formulation, that diagonal version of that matrix Chi, but I can have different priors. A very different one is by Milder and Perici. We'll talk about that also. A matrix F distribution for the covariance matrix, which is a robust version of the inverse Wishart. A scale mixed inverse Wishart, but in a different way. Not that particular diagonal structure, but a more general structure. Their scale mixed inverse Wishart for the scale mix matrix of the inverse Wishart also has a reciprocity property. That's interesting. Covariance matrix has a matrix F distribution inverse. The precision matrix also belongs to this family. It is almost like an F. F or reciprocal of F, they're both F. Next slide, please. In the univariate case, the F distribution is interesting. Is an inverse gamma scale mixed by a gamma. So you take sigma squared by R inverse gamma, you take R as gamma in a certain way, pi of sigma is now becoming sigma to the power nu minus 1, that particular structure. And the multivariate setup, sigma given delta is inverse V-shot with those parameters which I have given. If you take a delta as a V-shot with degrees of freedom D and scale B, then pi of sigma has that particular form, almost looks like a matrix version of the ridge, but not quite that as yet. But there are other ways to think about it. Even in the univariate case, actually we can talk about different way to get that half T. In the multivariate case, the matrix F can be also represented as a V-shot mixture of V-shots, V-shot mixture of inverse V-shots, etc., etc., etc. Is there any question up to this point before I get into more technical aspects? This is all preliminary. Any questions?
Sir, I don't think.
Yeah, please.
You can go ahead, sir.
Thank you. Okay, next slide, please. So now it is a hierarchical model. As I said, originally we did not think about the regression framework, but now we have. So we'll start with a multivariate, multi-response linear regression model, Y as XB plus E. Y is the vector of matrix, actually, where each component is a vector. So Y is an n by q response matrix, n samples, each of dimension q. N is large in our case, q is fixed. I mean, not quite, but it cannot grow faster than n. That is the important thing. It cannot grow faster than n. You can make it qn, but it has to be still little o n. X is the design matrix, n by p matrix of covariates. B is the p by q regression matrix. And we are assuming the error matrix, IID normal 0 sigma. So what is a matrix normal distribution? A random matrix Y is said to have a matrix normal, and we are writing it in the notation NUV. The mean is N. Now what about the U and V? The way to think about it is that if you write the whole set of samples, Y, Y1, Y2, Yn, as a straight vector, NQ dimensional vector, then the variance covariance matrix takes the form U cross V. So instead, we are writing it for the matrix Y, and this takes that particular form. It is equivalent to vec of Y is normal with mean N and variance covariance matrix U cross V. But we are taking the standard linear regression model. So the variance covariance matrix for the vector is I cross sigma. That means each sample, each Y, has a covariance matrix, sigma. And for the matrix normal, we are writing this particular version. Next slide, please. Now, what is the scaled inverse V-shot prior? Well, the B given sigma, it almost looks like a version of so-called Zellner's Z prior, G prior, and in our case, the G is lambda inverse. That is the G. Those of you who are familiar with Zellner's work can recognize it. If not, don't worry about it because we don't need it. But the sigma given delta is of the form nu plus q minus 1 C nu delta. The important thing is we are trying to cover Huang and Wand, O'Malley, Jaslavsky, Gelman, everybody with a single notation. So I take a diagonal matrix with elements delta I which have independent priors pi I. Now lambda looks like a tuning parameter, as we shall see even later, like the one used in ridge regression. Next slide, please. O'Malley and Jaslavsky suggested independent log-normal distributions for the delta I. C nu was equal to 1. Gelman suggested uniform prior for the delta I with C nu equal to 1 again, but Huang and Wan did something different. They recommended independent gamma priors for the delta I. C nu is 2 times nu. It depends on the nu which you have chosen for the shape, and the shape parameter is equal to 1/2. The interesting thing is nu equal to 2, that means C nu is 4, leads to independent uniform -1 to 1 priors for all correlation coefficients. That's one of the they have other interesting results here as well. But now I'm also introducing the matrix F, and that comes again in a uniform way, except you take a Wishart prior for, instead of a diagonal matrix, you are taking a Wishart matrix for sigma given delta bar. I'm not using delta. Delta was a diagonal matrix. Delta bar is a Wishart with degrees of freedom nu plus q star and using the scale parameter psi. It is generalization in some sense of the others. Next slide, please. Now, interesting thing is, as I was saying, you will be clear. The notations, don't worry, x transpose xn plus lambda iq is x lambda. So x lambda inverse is what? Xn transpose xn plus lambda iq inverse xn transpose xn. So what I said earlier, I'm now substantiating it. It looks like a ridge. What about SY? That is the error matrix, yn transpose I minus the, not quite the projection matrix, which is xn transpose xn inverse, but it is instead that ridge inverse of that ridge matrix and multiplied by yn. Now, the way to handle it is what? B given sigma delta yn is a matrix normal with mean Bn tilde, and Bn tilde is the ridge estimator. And then, if you write effect notation, it is xn inverse cross sigma. And sigma given delta yn is inverse Wishart also, except now the degrees of freedom has changed to nu plus q plus n minus 1. The error matrix has changed for the original framework. It is SY plus C nu delta. The more complicated thing, just a minute, the previous slide, please. The more complicated thing is the delta given y, which looks like that particular form. And as I said, Huang and Wan took delta I gamma half ai to the power minus 2. If you do that, you get delta I given sigma yn has a gamma distribution with shape parameter nu plus q by 2 and the scale ai to the power 2. And it is nu and the ith diagonal element of the inverse of the variance coefficients matrix. Next slide now. Thank you. The way to look at it is the joint distribution of pi b delta sigma delta given yn, and then do the usual MCMC. So far as the implementation is concerned, I won't say much about it. There is a little bit of trick which comes in the calculation, where you simplify the trace of sigma inverse, the top thing given, plus sigma inverse B transpose B, it becomes trace of sigma inverse SY plus trace of sigma inverse B minus beta and tilde, so that you can separate the two things. Next slide, please. For the matrix F prior, similarly, you do a similar calculation which I've given in the bottom. The top line are very similar up to the first, second, and third line. But then in the fourth line, because we have used an inverse Wishart-Prior instead of a diagonal matrix, it becomes, the structure is the same, but it is different because of the delta bar, which is a Wishart distribution. And that's exactly what it is. So now, the conditional distribution of B given sigma delta bar yn remains the same as before. Nothing changed for the regression matrix, but sigma given delta bar and yn is different. Next slide, please. Under the matrix F prior, the posterior density of B sigma delta is always proper. Of course, we have done it that way so that it has proper. So B given sigma delta tilde now, yn, actually given by that particular structure, Bn tilde, Xn tilde, and sigma given delta tilde instead of delta is given by that, and the prior for delta tilde is given, I'm sorry, it's not delta tilde, it should be delta bar, okay? The typo would be corrected. B given sigma delta bar yn is given by that, sigma given delta bar yn is that, and pi of delta bar is given in that particular form. There is no delta tilde, sorry. Delta bar. Thank you. Next slide. Now, posterior consistency of the proposed method, that's an interesting thing. The whole calculation, the whole motivation was done with a normal model. So start with a true model, x beta naught plus c, but do not assume normality of the errors, but something similar. All you assume is sub-Gaussianity of the elements of E. You may ask me later what sub-Gaussianity means, although I have given a definition. With variance covariance matrix sigma naught. A mean zero, random variable x, I'm writing one-dimensional, is said to be sub-Gaussian with parameter sigma square if its moment-generating function is less than equal to the moment-generating function of a normal zero sigma square random variable. That means what? The variance is smaller, right? So it has a lighter tail. An important property, there are quite a few things. The two books I would like to recommend to, actually, there are other places as well, but my favorite ones, the two books, one by Wainwright and one by Verschinen, especially the one by Verschinen. They discuss sub-Gaussian random variables at great length. And I'm copying one property of the sub-Gaussian random variable, which is the pth Euclidean, the expectation of absolute x to the power p raised to the power 1 by p, the Euclidean norm, is less than or equal to k p to the power half. But again, that's not what we have used. We have used a particular result from a book by Verschinen. What about the vector sub-Gaussian? Very easy. For every single linear combination, it is sub-Gaussian. That's all. Just like characterization of a normal distribution, if a multivariate normal, if and only if every single linear combination is univariate normal, if and only if. Next slide, please. We allow both q equal to qn, p equal to pn to depend on n, but we consider the true model yn equal to xn plus b0n plus e0n, which means 0 variance sigma naught n, and p naught is the probability measure. So what we mean by posterior consistency, definition is very simple. You take the tail probability of the posterior of sigma given the data yn, and then take its expectation. You don't have to, but it is the same thing because it is a bounded thing. So that thing converging in probability to 0, almost in probability, is equivalent to the expectation going to 0 because it is bounded. So it is the same thing under the true model. And what is the spectral norm? Now, for a symmetric, if it is a positive definite, it is very easy. It is the largest eigenvalue. But if it is only symmetric, eigenvalues are real, and then you have to take the max of the absolute, because the eigenvalues don't have to be all positive, because it is not a symmetric but not a positive definite matrix. You can have the spectral decomposition with eigenvalues and eigenvectors, but the eigenvalues can be negative, so you take the positive, the max of the positive of the minimum and the positive of the maximum. For B, it is the same thing. Instead of sigma, put B, and put B for sigma naught n, put B naught n, then the posterior converges to 0 as n goes to infinity. Next slide, please. A few assumptions. Qn is little o n. Qn is allowed to grow with n. The ratio converges to 0 as n goes to infinity. So it is a very popular thing nowadays. The high dimensional vector Qn much bigger than n, but they don't work here. There exists eta also not depending on n. That's easy. We just put the lower bound for the minimum eigenvalue of the true matrix and the maximum value, eigenvalue of the true variance covariance matrix. And I'm just quoting Bickel and Levina, well-conditioned covariance matrix. And pi I u, the prior, which is satisfied in all our examples, decreases in u for u, some number k. The k doesn't matter, just the tail is decreasing after a point, that's all. And the other condition is Pn square over Qn is little o, n to the power 1/2, little o n, if you square root. And then the usual assumption, x transpose xn over the lim inf and the lim sup are bounded by non-zero, bigger than 0 and smaller than infinity. Next slide, please. So under these above conditions, we have that particular posterior consistency result, sigma minus sigma naught, the spectral norm is bigger than Qn over n to the power half, given 0. For matrix F, need an additional conditions. The degrees of freedom nu q star has to be of the order q. So I'm making a condition between the degrees of freedom of the prior covariance in the hierarchical stage and the dimension of the random variables. And then under that condition, again, you have posterior consistency just like before. Next slide, please. Tools are, just quickly go ahead. It's not very important. If you have a sub-Gaussian random vectors with parameter, then if you take the quadratic form, P is a projection matrix, by the way. The Z is the random variable whose rows are independent sub-Gaussian, means 0, actually isotropic as they call it. You can write it as A transpose A, independent isotropic sub-Gaussian, with sub-Gaussian parameter given by that. Lemma 4, you may not have to worry about it, but I will tell you, this we took from Verschunen. The A matrix does not have to be actually even symmetric. You can see that number of rows are given by this, and number of is n plus something. Number of columns is n. Okay, the rows are independent sub-Gaussian isotropic with parameter sigma square. We still need P and Q to be little o n, but then you get an exponential bound, like you control the singular values of the matrix A. It is no longer symmetric, so you cannot talk about eigenvalues as such. The singular values are given by this bound. The tool has been used by others in many different contexts. That's why I brought it in, and we have used it as well, this lemma 4. Very critical lemma. Next slide, please. And then now the question is that if Q is bigger than n, suppose I relax Q equal to little n. So Q over n is actually converging to gamma, which is positive and finite. Then what will happen? The posterior mean will be an inconsistent estimator of the covariance matrix. Take a very simple setup. Samples are coming from an IID normal distribution with covariance matrix I. Next slide, please. So consider the model. That's what I said. 0 sigma, 0. Otherwise, you have to subtract off the mean, but that's not important. Using the same scaled inverse Wishart sigma, nu equal to 1, C nu equal to 1, assumption same as before. You can do other things as well, but Qn over n is going to gamma. Sigma naught is I. Then sigma n hat minus I bigger than W, that probability is strictly positive. Same setup as the previous lemma using the matrix sec prior, and nu q star is Qn. Qn over n goes to gamma. You get a posterior inconsistency result. Next slide, please. We'll illustrate some simulations, but just mainly to illustrate this point, posterior inconsistency for different choices. We took half t log normal and normal truncated, and Qn is n to the power quarter, n to the power half, n to the power 3/4. You are doing fine. As we shall see, we generate n observations. So sigma n hat estimation error, average over 500 replicas. For the inconsistency setup, Qn, you can see Qn over n is 1/5 or 3/4 or even some other. 3 over 40, 1 over 10. So next, there are two pictures, two sets of pictures. Next slide, please. You can see that posterior consistency is happening when sample size is growing. For half t log normal matrix F, no problem. It is going almost becoming identical. And next slide, same thing. Posterior consistency is still coming. So n by 4, 3n by, those are the three things which you have used to show posterior consistency. The next two slides will give posterior inconsistency. Next slide, please. You can see that. When we are taking Qn over n as a constant, fixed constant, it is not going, the inconsistency, and both just like that. There is nothing much to say except that it is illustrating the method. That's all. Next slide, please. The same thing, posterior inconsistency, as we shall see. Next slide. So what is the final thing? This is my final slide. We describe and examine the theoretical properties of scaled inverse Wishart and matrix F for the covariance matrix proposed in many different settings. Other priors are available in the literature. One which I have used in the past when I was working on case control, of course, in a very simple bivariate case, is a prior by Mike Daniels, our chair, and Rob Cass of Carnegie Mellon. Our analysis can be carried out under the assumption that prior on degrees of freedom should have. Now, these things actually, Partha did some calculations. Now, if you want to put some bounds on the degrees of freedom, I mean, actually not distribution, bounds on the degrees of freedom for those priors, and must be of order little o n. For unbounded support, some additional work is needed. Now that is different. Another plan is to extend it to the case when the true counter has an unbounded spectral norm. You can think about the compound symmetric. If you have a sample size n, it will be what? 1 minus rho. Think about the variance is sigma square, covariance is rho sigma square. So the the eigenvalues are 1 minus rho, n minus 1 of them, and 1 plus n minus 1 over rho, which grows with n, that kind of thing. It is not covered here. And the final thing is sparsity. The important thing about sparsity is when you have sparsity, still the number of, that means many of the covariances are equal to 0, then, even then, what will happen? This kind of results will not possibly hold. You possibly can get even posterior consistency, but the important thing is the number of significant variables, that has to be small. That, I mean, not significant, number of variables for which the correlations, the Q. Thing is, if you think about a regression, for example, in a high dimensional situation, P could be much bigger. Even it could be exponentially, what is called sub-exponential, exponential n to the power alpha, so that alpha is between 0 and 1. So log P over n goes to 0, but P could be much higher than n, but number of significant signals should be of much smaller than n. That kind of analogy. So when you have sparsity in the variance covariance matrix, what will happen, we still don't know. And topic of future investigation. Thank you very much for your attention. I really appreciate your invitation. Thanks a bunch.
Thank you, Professor, for the enlightened talk. You were talking of priors for this new model. You were considering for covariance matrix, and some of the priors are new to, I think, many of us, like matrix F. So far I have not used. I've done some work in econometrics, but matrix F we didn't use. So it's a new concept that we can look forward to using, and many others in this audience can also do that. And any questions from the audience? You gave a very good talk, very knowledgeable in the multivariate setup. Any questions from the audience?
Yes, if I may.
David,
I'm online. How are you? You mentioned two references. One was, I think, by Wainwright. Is this Martin Wainwright?
Yes. Yeah.
And the other one was which book?
Versionin. Yeah.
Thank you so much. I appreciate that.
Those are my favorite books in these days for high dimensional research.
Excellent. Thank you so much.
Any other question?
Malaida.
Yeah, Gauri.
Yeah, if I may. Gauri Shankar here. Malaida, great talk.
Go ahead, Gauri.
Great talk, Malaida. You know, I don't know if you're still 45 or 79, but yeah, it's a great talk. Yeah, learning so many things from you. I think there is a typo somewhere in the definition of BN tilde. Is
go ahead.
Maybe the data part there, I think. But
data part. Maybe, I'll take a check.
Yeah,
check that. Okay.
I think only the design matrix
tilde, which is wrong, and same thing must be. Something similar must be with BN tilde. Okay. So you're talking about the matrix F situation or the other one? But
yeah, the matrix that, you know, the regression coefficient, the regression of the matrix, I think B, the corresponding shrinkage version maybe, BN tilde, that you have Xn transpose Xn inverse.
Dr. Kumar, can you go back several slides? It'll be good. Maybe a typo. Go ahead.
Yeah, please.
Gauri wants to say something, and I think I'll correct it when I start. BN tilde.
Yeah, it's a small typo actually.
No, even further back, right?
I think where the BN tilde was introduced.
Oh, no.
Yeah, right there.
The next one, the next slide. You got it.
Is that?
Oh, yeah. Correct. YN is missing. Correct.
Yeah,
Thank you.
Corey, you are so smart.
Thank you. Thank you very much. Thank you. Thank you, Gauri. We'll correct it.
Professor Ghosh, I have a small query actually. It's just for my knowledge. Somewhere you mentioned
Thank
about
you.
horseshoe prior. You mentioned about horseshoe.
Very simple. You take for the standard deviation or any random variables. Oh, okay. Any random variable. A non-negative random variable, a half Cauchy. That means you take the structure of Cauchy, but it is from 0 to infinity. So there will be 2 over pi or something, 1 plus x. You take the square of that random variable, and it has that distribution they call horseshoe. Actually, some people call, even make it more general. That is the best way to think about, at least the way I think about it, that's the horseshoe. And it is a very special case of a what I call a type 2 beta distribution. A type 2 beta distribution is what? X to the power c minus 1, 1 plus x to the power, whole power, minus c minus d. And if you take both c and d equal to half, that is the distribution which you get by squaring the half Cauchy random variable.
Okay.
That's all.
Okay. Thank you, Professor. Thank you. Thanks a lot again.
Thank you.
So I think
Thank you.
everybody has benefited from your talk and got to know some new distributions and terms, like some Gaussian and all that. So thanks a lot, Professor Ghosh.
Thank you.
So over to organizers.
Thank you, Professor Ghosh, for your wonderful talk. Thanks a lot. Now, also, we would like to extend our thanks to Professor Kanchan for chairing this session and conclude in time. Thanks a lot. Thank you for this.
Thanks, Professor Satish, for giving me this chance.
Thank you. Okay. Now, without wasting further minutes, we can now 6:51. Now it's 6. I think 6:55. The 6. So 6 not 6:50. Yeah.
It's 6:51.
Yeah, 6:50. 65. Okay. By the way, we can I think Swapna is here in the group. Swapna.
Yes, sir.
Yeah. Let us move to the next session. Before moving to this session, please introduce the chair and thereby support the chair for running the session in a smooth way.
Hello, everyone. We are moving on to the technical section 9 of WSTA 2023, which is a special section in honor of Professor R. Krishna Pillai that shall be chaired by Dr. Sangeeta Arora. Now, Professor Sangeeta Arora is a faculty at the Department of Statistics, Punjab University, Chandigarh, from where she obtained her MPhil and doctoral degree in statistics. Dr. Sangeeta has made significant contributions to both teaching and research, shaping in the field in profound ways. She is deeply interested in the areas of applied statistics, income inequality, and Lorentz dominance, and so on. She has also received the 8th Venus International Women Award for Lifetime Achievement in Statistics in Science discipline in March 2023. She has worked as an executive member of the Indian Society for Probability and Statistics for the period 2014 to 2016. She has to her credit more than 15 publications in various national and international journals and over 40 national and international conferences, and chaired several sections and delivered talks as a resource person on many invited occasions. We are really lucky to have you with us, ma'am, the organizing this session today. Without delaying you further, I once again extend a warm welcome to you on the behalf of the organizing committee and kindly request you to take over the section. Over to you, ma'am.
Hello. Good evening to all of you. Can you hear me, please?
Yeah.
So I just thank, what's the name, Sapna, for giving a very nice introduction. So I am pleased that in this evening we have got a very distinguished statistician with us, and on this National Statistics Day, it will be pleasure for all of us to listen to such a distinguished statistician, Professor Thomas Matthew. I think he is already there. Welcome, Professor Matthew.
Thank you.
I just welcome you on behalf of the organizing committee for your distinguished talk. So before we start with this talk, I will take an opportunity to just briefly discuss about the just outstanding credentials of the Professor Matthew. Professor Matthew is a professor in the Department of Mathematics and Statistics, University of Maryland, Baltimore country, Baltimore, USA. And Professor Matthew has distinguished career starting from his PhD from ISI India in 1983. And then he has reached the top position in the University of the Baltimore, Maryland. And since 1985, he is a faculty there. His research interests include inference in univariate and multivariate linear models, inference in various component models, and bioequivalence testing, multivariate analysis, cost effectiveness analysis, meta-analysis, etc. To just quote a few. And he has got several honors. He is elected as a fellow of the Institutes of Mathematical Statistics in 1998, and he is a fellow of American Statistical Association, as well as he is a winner of 2005 W.J. Jordan Award in Interlaboratory Testing from American Statistical Association, jointly with Professor Iyer and Wang. And he is a co-author of the 2 books, Statistical Test for Mixed Linear Models and Statistical Tolerance Regions, Theory Applications and Computations, both with the Wiley publications. He is also he is a member of the American Statistical Association and has been the president of Maryland chapter of the American Statistical Association. He has more than 100 publications to his credit, and he has been the editor of many reputed journals like JASA, Annals of Mathematics, Statistical Methodology, Sankhya, etc. And he has reviewed many journals and books as well, and he has delivered invited talks and several international conferences, and he has guided 20 research students, and now we are very lucky to have him here in this evening. And this title of his talk is Cost Effectiveness Analysis, a Statistical Overview. So I just invite Professor Matthew to just deliver your lecture. Thank you, sir.
Okay, let me share my screen here. Let's see. You can see?
Yes, sir.
It is.
This content is not appearing.
Are you able to see?
We are able to see, but not the slides, sir. Slides are not seen.
Let me see. Why is that? Let's see. Let me try again.
So just open the slides.
Yeah, I was sharing the entire screen.
Yeah.
Okay, let's see. Share. How about now?
Now it's okay.
Okay.
Yeah, it's fine.
I assume everyone can see it.
Yeah, because
it's okay.
Okay. Yeah, so I want to thank the organizers for inviting me to speak here. And I noticed that this session is in honor of Professor R. Krishna Pillai, who was my professor and head of the department. So it's a great honor, Professor Satish Kumar, to be invited to speak here. And I noticed that my teacher, Kalyana Ramakrishnan sir, is there. So my honor is now doubled. So thank you. And I want to thank Dr. Sangeeta Arora for that very nice introduction. So I'm going to talk about cost effectiveness analysis from a statistical perspective. And this is going to be fairly non-technical. I will try to avoid most of the technical details in the interest of time. And my motivation behind giving this talk is to impress upon you the importance of this topic in clinical type applications in medical decision making, especially in the context of balancing cost and effectiveness of various new treatments. So here is an outline of what I plan on doing. I will introduce the topic to you through a series of examples. And the criteria used for cost effectiveness analysis, which I'm going to tell you what it is. There are criteria based on population means, which is what is standard available out there. And then there are recent criteria that are probabilistic. So I will mention both of those. And a little bit, very briefly, about the associated statistical inference. And if there is time, I will comment on some problems and future research on the topic. Let me start with this example. So in 2015, the US Food and Drug Administration, FDA, which is responsible for evaluating and approving new treatments, they approved 2 injectable cholesterol medications. So you inject them. One is called Repatha. The second one is called Praluent. I think you inject them maybe once a week or once in 2 weeks. They are extremely effective. And they are referred to as cholesterol busters because you can get dramatic reduction in cholesterol, bad cholesterol, if you are on these drugs. Lot more effective compared to what was there before this. However, there is a catch. The catch is that these are way too expensive. So here is the cost when the drugs first came out in 2015. Now they are cheaper. The cost was over $14,000 per person per year. So if you want to be on these medications, if you wanted to be on them, when it first came out, this is the cost. Obviously, somebody had to pay this either from your pocket, which is unlikely, it is a lot of money, or some insurance company had to pay it. So somebody looked into it and found that if all eligible patients who had a cholesterol problem took this, then this will add $120 billion annually to the US healthcare budget, a huge amount of money. So this article, which appeared in the 2016 Journal of the American Medical Association, came to this conclusion that this is the amount by which the US healthcare budget will go up if all eligible patients took these medications. Now, I have given a quote from that article, and there are a couple of terms in blue. One is incremental cost effectiveness threshold. I will tell you what it is shortly. Then you see another one, QALY, quality threshold. I will also tell you what it is. And then cost effectiveness is what my talk is going to be about. Roughly speaking, what it means is these 2 medications, they are effective. There is no doubt about it. But are they cost effective? In the sense, the huge amount of money that has to be paid out to be on these treatments, is it worth it? So can somebody afford it? That is what the area of cost effectiveness analysis is about. How do you balance cost of a treatment and its effectiveness? Because somebody has to pay for this. There are further updates on this, and the overall conclusion was that these 2 medications are not cost effective. They are effective, but they are not cost effective. So later we will see how one could come to this conclusion that these 2 are not cost effective. Is if you go online, you will see that the cost of these medications right now is for Repatha, it is about $505 per month. This is roughly on the average. It depends on which pharmacy you go to. And for the second one, slightly cheaper, $483 per month. Roughly, this is rough average cost. There is some variability depending on where you go to purchase this. If you think that was expensive, look at this one. So this is the most expensive drug on the market called Hemgenix. This was approved last year by the FDA. The approval was given to this company CSL Behring. This is a company from the UK, and they specialize in developing treatments for rare disorders. So this is to be given to patients with a rare disorder of hemophilia B. The price, $3.5 million per dose. I have no idea who will pay for this. And this article from Forbes magazine, 2022, December, says this sets a new record for the most expensive single-use gene therapy in the US. Here is one more. This was approved last week, June 22, 2023. So this approval was granted. The medication is called Elvidis, and this is used for treating muscular dystrophy. This is very rare. Basically, this affects young boys, and if a boy catches this, the life expectancy is something like 16 to 20 years. You basically start losing your muscle mass. And look at the price, $3.2 million for one-time intravenous treatment. So we have all these very effective new treatments coming out, but they are also very, very expensive. So what exactly is cost effectiveness analysis? Well, so this is a set of tools that you use to answer the question, is this new treatment good value for the money? Now, throughout my talk, the cost will be treated as a continuous random variable. Cost means in terms of dollars or rupees or whatever, in monetary terms. So this type of analysis is very important when you have, for example, the healthcare budget is always going up, expenses are going up. So how do you allocate resources which are limited to balance the health, the effectiveness, and the cost? So the cost we are going to treat as a continuous random variable. The effectiveness. Now, the effectiveness calculation is a tricky thing. Actually, I don't know all the details. I will give you some rough idea what exactly is effectiveness. If you want to be on a medication, let me give you the following explanation. If you want to be on a medication that is meant to reduce cholesterol, the effectiveness will not be just the reduction in cholesterol. It will be more than that. They measure it using something called a quality adjusted life year, or QALY. What that does is, suppose my cholesterol medication has a lot of side effects. It affects the quality of my life. If I am bedridden, all of that is taken into account when the effectiveness is calculated. It is not just how effective the drug is. In other words, is the drug offering me a quality life? So there is a way of calculating it. It is actually a weighted index, taking into account various things. So I have put a reference there at the bottom of the slide in case somebody is curious about it, how to compute the quality adjusted life year. There is also something called disability adjusted life year. If you're on disability and if the medication can cause disability, that is also another popular one. Then there are other things like a quality adjusted life weeks, especially for terminally ill patients. Then a health adjusted life year, survival time, then response or no response. The effectiveness can be binary, could be discrete or continuous. So this is a Wikipedia entry on QALY. Just focus on that sentence in red. One QALY equates to 1 year in perfect health. This is one way of thinking about it. So clearly, the larger, the better. So here is what is called a disability adjusted life year, or daily, according to WHO. Again, look at the first sentence in red. It says, one daily represents the loss of the equivalent of 1 year of full health. So smaller, the better. Loss of healthy life. So smaller, the better. Okay, now I'm going to give you two actual examples along with the data. So this is a medication, tamoxifen. It's already been in the market. This is used to treat early stage breast cancer. And if somebody is on a 5-year regimen on this, somebody with early stage breast cancer, it is supposed to be very effective. So it was approved by the FDA in 1986. And then this new medication came into the market. It is called exemestane. So what it is once you are on tamoxifen, the first drug, for a couple of years, and then if you switch to exemestane, it was noted that it becomes a lot more effective for early stage breast cancer. However, this new medication, exemestane, is a lot more expensive compared to tamoxifen. So if you continue on tamoxifen, the cost will be much less compared to switching. So the question is, the extra benefit you get from switching, is it worth the added cost? So here is some data. So based on a 5-year duration clinical trial, okay, look at the table there. This is the average cost for a 5-year period of treatment. If you switch to exemestane, it is little over $12,000 for 5 years. If you stay on tamoxifen, it is cheaper by about $4,500, $7,724. The average effectiveness, if you switch, you can certainly expect to be disease-free on the average about little over 6 months. If you convert that into a QALY, what you get is about 0.22 year. That I guess is about 3 months. So you can expect an additional 3 months of quality life if you switch on the average by paying an extra cost of about $4,500 on the average. Is it worth it? How do you decide that? Who will decide that? So remember that we are comparing 2 treatments, switching to exemestane or continue on tamoxifen. So in cost effectiveness analysis, typically you'll be comparing 2 treatments, maybe a new treatment with something that is existing, or 2 new treatments and whatever. Okay. Now this 2010 article by Greenberg et al., when is cancer care cost effective? One of the things you will see in the literature is that whenever a new cancer treatment comes into the market, somebody will immediately follow it up with a cost effectiveness analysis. So this article reviews 229 studies regarding the cost effectiveness of different cancer treatments. So I'll comment on this a little later. Here's a second one. This is actually a Canadian study regarding prostate cancer. So we are looking at, actually in the previous one, I forgot to include the sample sizes. So here, the 2 treatments or the 2 groups are people continuing on prednisone alone, 61 patients, or people who are on prednisone along with this drug mitoxantrone, and they are followed until death. So these are terminally ill patients. So their effectiveness is measured as quality adjusted life weeks because they don't have much to live. So the cost is in terms of Canadian dollars. So the situation here is actually quite nice. You can see that the prednisone alone, or if you combine prednisone along with the mitoxantrone, it is less costly on the average and a lot more effective, which is actually quite nice. This is a very rare thing. Less costly, less average cost, and more average effectiveness. Let me just point out one small thing here. Remember that all this analysis is done at a population level. So we are talking about population averages here, and this is sample data based on clinical trial. So as I said, we are comparing 2 treatments. Treatment 1, I will call the new treatment, and treatment 2, the existing treatment for the purpose of our discussion today. All right. Now, the parameter of interest is referred to as the incremental cost effectiveness ratio, or ICER. So this is a single number that will tell you how cost effective treatment 1 is compared to treatment 2 in terms of averages. So this is a criterion based on population means. Very simple to define. You look at the ratio of the difference in means for the cost, that will be the numerator, and the denominator will be the difference in average effectiveness. So the incremental average cost divided by the incremental average effectiveness. This is called the incremental cost effectiveness ratio, or the ICER. Little bit of notation. Let us write mu C1 and mu C2. So that the superscript is basically denoting the two treatments. It is not a square. So mu C1 and mu C2. This is the population mean under the two treatments for the cost. Mu E1 and mu E2. Again, the population mean regarding the effectiveness for the two treatments. So incremental average cost delta C, mu C1 minus mu C2. Incremental average effectiveness, similarly, delta E. You take the ratio delta C over delta E. This is called the ICER. It is widely used. Earlier, I mentioned that article that is on evaluating the cost effectiveness of cancer treatments. Every one of them uses the ICER. Now, as a matter of fact, if you go online and look up cost effectiveness analysis carried out in India, a lot of literature will show up, and you will see that the ones I looked at, they all use the ICER. In fact, one of the important cost effectiveness analysis that I noticed going on in India, several articles, is regarding diabetes management, and many of these articles I noticed uses the ICER. Okay, it's a single number, right? It's a single number that is trying to balance the cost and the effectiveness at the population level. So let us look at that criterion once again. You notice that when is the ICER small? So the ICER will be small if the numerator is small and the denominator is large. That means the new treatment on the average is not too costly compared to the existing treatment, but it is a lot more effective. So the ICER, smaller the better. So the ICER is below a specified threshold, you will conclude the new treatment is cost effective. So this is how you make a decision, which means what you need is really an upper confidence limit for the ICER. So if the upper confidence limit is below a threshold, you will conclude the treatment one is cost effective. That is how this is used in practice. Okay, let's go back to our first example. So here, this is that early stage breast cancer treatment comparison. So here the ICER is 20,000. What does this mean? So this means somebody has to pay out about $20,000 on the average for an additional year of quality life. For an additional quality adjusted life year, the cost is 20,000 on the average. So this is what we conclude from this number. Okay, pay attention to the confidence interval. I have taken actually what you need for the ICER is an upper confidence limit, but this is a two-sided interval. I took it from this paper, whatever they have reported, 2013. The ICER, it is a ratio of means, actually mean differences. And as we know, the ratio of means is a problematic parameter, and you see a very wide confidence interval. And this creates issues. So the lower limit is 12,000, upper limit is 59,000. So you see very wide confidence intervals for the ICER, ratio of means, right? So in this article, they are concluding that the new treatment, namely switching to exemestane, is not cost effective. It is way too expensive. So this is what they conclude by looking at the point estimate and the confidence interval. So I'm not going to get into the details of the confidence interval calculation. Now, being a ratio of means, some people were concerned about the inference aspect. So there is a new criterion. Well, I shouldn't say new criterion, an alternative criterion. That is called the INB, or the incremental net benefit. This requires the specification of a quantity which will denote by lambda. This is referred to as a willingness to pay parameter. So this is the amount that a policymaker or an insurance company is willing to pay for the new treatment. Roughly speaking, this is what we are willing to pay for an additional year of quality life. So obviously somebody has to make a subjective decision. So this is the definition of the INB. You look at the incremental effectiveness, delta E, multiply that with the lambda. Then subtract the incremental cost. So roughly speaking, what I'm saying is, in monetary terms, if the INB is positive, then in monetary terms, I gain by going to the new treatment. So this is the benefit of giving a patient treatment 1 rather than treatment 2, expressed in terms of money, monetary terms. So this is what the INB is. Larger the INB, the better. So INB positive, you will conclude the new treatment is cost effective. INB negative, the opposite conclusion. So typically people will compute a lower confidence limit for the INB and verify if that is positive. There's extensive literature, truly extensive literature on the topic, and this is probably the only book that addresses the statistical aspects of cost effectiveness analysis. The second example I took from this book, that Canadian study. Now, the models used for cost effectiveness analysis, it is pretty well accepted that the cost usually follows a log normal distribution. And you can easily verify that. Typically, people have noticed that log normal cost is a appropriate assumption. The effectiveness can be anything. You may have normal or log normal, then discrete, anything can happen. So one popular model, in case the effectiveness is normal, is what is called a log normal model. That means the natural logarithm of the cost and the effectiveness jointly follow a bivariate normal distribution for each treatment group. Remember, you have 2 treatments. So you have 2 bivariate normal distributions having their own mean vectors and variance covariance matrices. And if you are in a parametric setup like this, you can easily work out you can easily express both the ICER and the INB in terms of the population parameters. So basically, when it comes to the average cost, it will be the average or the mean of the log normal distribution. Then you can use various standard methods for computing the confidence intervals. You can use asymptotic normality, then the ratio of means. You can use Fearless theorem, various bootstrap methods, and you can also use a fiducial approach for computing confidence limits. Let's look at that second example, the Canadian study. In the study, the Canadian government, actually, the willingness to pay was $500. This is an actual study, by the way, and this is also an actual amount, $500. So that means $500 for an additional year of quality week, quality adjusted life week. By the way, it's for 1 week. So the ICER estimate is negative, which is very good. So this simply means it is less costly and more effective, which is very good. However, if you look at the confidence interval by the various methods, which I'm not going into the details, you can see that the intervals come out very, very different. Not only they are wide, they look very, very different. One of the FLR approaches gives you the union of 2 segments as the confidence interval, which is typical when you apply Fearless theorem. Anyway, if you look at the coverage probabilities, which I'm not reporting right now, only the fiducial solution gives accurate coverages. The rest of them, the coverages do vary. Obviously, if you increase the sample size, most of them are close to the nominal level of 95%. The thing to notice is that the willingness to pay quantity is $500. The upper confidence limits, they are all more than 500. So given the variability, even though this example is kind of rare, less costly, and more effective on the average, still you cannot conclude it is cost effective based on these confidence intervals. This is the confidence interval for the INP. Let me skip that. Okay. I'll spend a few minutes to introduce some of the probabilistic criteria to you. It is very simple. You look at the proportion of patients for which the new treatment is less costly and more effective. So the probability, cost for treatment 1, new treatment, C1 less than or equal to C2, and E1 greater than or equal to E2. So obviously, a large value of CEP will be good, cost effectiveness probability. Now, this is too much to expect because the new treatment may be more effective, but you cannot also expect to be less costly. So you can modify this by adding a threshold. So here is a modified version. The new treatment may be more costly, but up to a threshold delta C, and it is more effective. So you can choose the delta C. And what is the corresponding proportion CEP? Obviously, larger the better. You can also modify this as a conditional probability. So look at you can also include a threshold for the effectiveness. So the conditional probability at the bottom says, well, we do know the new treatment is more effective. So given that, what is the proportion of patients for which it is less costly or less costly up to a threshold? So the nice thing about this criterion is there is a lot of flexibility here. You can do a parametric inference, assuming the bivariate normality for the log cost and effectiveness. You can do non-parametric, and we found a U statistics-based approach to be especially accurate for reasonable sample sizes. Bootstrap will also work, but we found that you need a bit more in terms of sample size. Okay, this is that second example where we saw that the new treatment is not exactly cost effective based on the confidence intervals for the ICER. But you can look at the CEP. So this is the, remember, this is on the average, this is less costly and more effective. So let us look at the proportion of patients for which it is less costly and more effective. So the estimate is about 24%, and we have a confidence interval about 17% to 30%, 31% by both the fiducial approach parametrically and the U statistics-based solution. So this type of information you cannot get from the ICER or the INB. You're trying to identify the percentage of the population for which the new treatment can be more effective and less expensive. And you can similarly do a conditional probability calculation as well. So this 40.3%, this is the proportion of patients. Look at the proportion for which it is more effective. Then it is also less costly for about 40% of the patients. So we introduced these measures in this 2016 article. Okay. Now you can extend this to multiple effectiveness outcomes. There are many studies where the number of outcomes to be measured is multiple. That means from bivariate, you will have a multivariate distribution now. I will not go into this in the interest of time. This study we took from this article in the New England Journal of Medicine, 2008. We also got all of the data. This is called ACCORD, Trial Action to Control Cardiovascular Risk in Diabetes. The number of patients actually quite large. And there were two effectiveness measures. So there is an intensive treatment and a standard therapy. The intensive treatment was aimed to reduce the hemoglobin level to less than 6%. The standard therapy reduced it to the range 7 to 7.9. It was a multi-center trial, several centers in both the US and Canada. Okay, let me just mention about the two effectiveness measures. Two effectiveness measures were obtained. And by the way, the cost was total cost per day. There is even the reduction in cholesterol and E2, the reduction in the hemoglobin levels. So obviously, E1 and E2, larger, the better. The examples I gave you up until now, there was a cost and a single effectiveness. Now we have a cost and two effectiveness measures. What they do in the literature on cost effectiveness analysis, I found that fairly strange because it's a very, very subjective analysis. They call that a multi-criteria decision analysis. And there is a lot of subjectively specified input quantities there. And depending on how you put it, the conclusion could very easily change. You can manipulate the criterion the way you want, which I found that very surprising. But that seems to be common practice in the literature when you have more than one effectiveness measures. Anyway, I will not go into the detailed analysis of this. I have that here. So we propose this in this 2023 article that will appear in Statistics in Medicine. Okay, let me make some final comments here. There is also another probabilistic measures. So these are recent, introduced in these two articles fairly recently. Now, these probabilistic measures, one thing I want to point out is that no matter how you argue, the ICER probably will never be replaced. It is a well-established criterion. So we look upon some of these probabilistic measures as providing extra additional information, not as a replacement for the existing criteria. Suggesting them as replacements will never sell. There are a number of topics that are brought up in the literature in cost-effectiveness analysis that require research. There is a cluster randomized trial where the unit of randomization will be like a cluster of patients, right? All patients treated at a hospital or treated by a doctor or covered by an insurance carrier and so on. So some people suggest you introduce a random effect into the model. So that has been discussed and disputed in the literature. Quite a bit of recent literature pointing out the issues there and why it needs to be looked at. Then there is meta-analysis. A lot of issues in meta-analysis in the context of cost-effectiveness analysis. Let me go to, I have cited some of the, here it is. This is a 2020 article. They say that meta-analysis is rarely feasible or robust. There are a lot of methodological issues apparently. And this article last year, it is also highlighting the methodological issues when it comes to meta-analysis in the context of cost-effectiveness analysis. Then there is personalized medicine. Remember, what I mentioned to you so far was a population level analysis. So the question is, if you know that the treatment is cost-effective for the population, what about me at an individual level? So that has been addressed by a lot of people, especially incorporating covariates. So this has been an ongoing area of research, and it will continue to be so because the healthcare expenditures have been going up. So you want to balance the health and the effectiveness, so that immediately emphasizes this type of research. If you are interested, the articles have appeared not in mainstream stat journals, but various other. The top journals in the field is Health Economics. I think it is from the UK. And I have listed a bunch of journals that publish articles on cost effectiveness analysis. There are more, by the way. Then there is a World Health Organization manual, actually. It is a bit old, 2003, but it will give a step-by-step guidance on how to carry out a cost effectiveness analysis. So here is something I have found very valuable. That Accord trial from the New England Journal of Medicine. We got that from here. This is a cost effectiveness analysis registry maintained by the Tufts Medical Center in Boston. If you go to their website, you will see that you can search. For example, if you want to get hold of various publications on cost effectiveness analysis, say in cancer, you enter the word cancer in the search box and it will produce all the articles. And you can follow it up and probably get some data also, which is what we did. So their website says the CEA registry is a comprehensive database. It is constantly updated. Over 10,000 published analysis reported for various diseases and treatments since 1976. So if you have any interest in this topic, it's very easy to track down the literature on a particular disease. Just go to this registry maintained by Tufts Medical Center. And thank you.
Thank you so much, Professor Thomas, for a very, very interesting lecture. I really enjoyed it very much. With so much new information.
Thomas, it was a great talk, actually. This is real statistics. This is very interesting. The first one is a non-statistical one. Even if the price of Repatha and Proland is becoming about $500 a month, are there many people who are taking it? Is it much more effective than the oral medicines?
I will comment on that. Even the 500 is too much. It is per month. It is per month. Here is what is happening. Here is what is happening. You brought up a good point. Now, I was told that stroke patients, if stroke patients have a cholesterol problem, most of the traditional medications will not work. But these two will work. But here is the thing. Insurance companies refuse to pay for this. So the doctors have to call the insurance companies and fighting with the insurance companies. Yeah, that is where it is.
Yeah, there are some people who can definitely pay that.
Right.
The second question is a technical little bit. Whenever you talk about fiducial,
yes.
I think of a Bayesian with non-interpretive priors.
Yeah.
So is there any Bayesian word done?
Not that I know of. I like to think of it as posterior without a prior, if you will. I'm
talking about a full Bayesian analysis.
No, I understand. I have seen that on a case-by-case basis. As a general theory, I have not seen. Probably you may want to look at some of the work by Ryan Martin.
Okay.
Yeah, Ryan Martin probably has some results along those directions.
Okay.
Yeah. I am not familiar with it. I'm not aware of it, but I think he certainly have made an attempt. Maybe he has done in some cases.
Okay. Very good. Thanks for the.
Sir, I just want to ask one thing. So out of the various, you have given the ICER, and how threshold level is being decided? Because generally,
well, let's say that depends on who is paying for it.
Okay.
Right? How much can you pay? Tell me. I will tell you the threshold. That's what it is.
But it is something subjective for it.
Well, it is subjective. It is decided by the government. If the government is paying for it, like in Canada, I assume.
Yeah.
And in the US, the insurance companies will pay for it. So they will say, this is like what Dr. Ghosh just asked, the Rapata. The insurance companies say, this is all we will pay.
Then it is effective.
So they decide.
Yeah.
Effectiveness versus the cost, that is somehow subjectiveness is also there.
Yes, there is subjectiveness. But the thing is that many countries, like some European countries and Canada, I was told that before a drug can be fully approved, the manufacturer has to carry out a cost effectiveness analysis before it can be approved. That is not the case in the US. I assume that is not the case in India either.
India, I have not heard about it. Anyway.
Right, but if you go online, you will see a lot of articles investigating cost effectiveness analysis in India. I was surprised.
Can make interesting study. Anyone else, please? Anyone from the audience? So, if there is no other question, so we must thank Professor Thomas for very, very interesting, very illuminating talk. Thank you, sir. Thank you. Thanks a lot.
Thank you.
Thank you. Thank you, sir. Over to the organizer, Professor Satish.
Thank you, Professor Thomas Matthew, for a very informative talk. In fact, it is very helpful to the researchers. No doubt about that. We are very much grateful to you, Professor. And also, we would like to express our thanks to the Professor Sangeeta Arora for chairing the session in a very nice way. Thanks a lot.
And also 5 minutes is not enough. Yeah.
Yes, absolutely.
Oh, right. No.
Malai, I really enjoyed your talk, and I was looking for the Martin Wainwright book while Thomas was talking.
The version in book is more easily, in some sense, readability. But there are things which are in the Wainwright's book, not in version in, and vice versa. I use version in more than Wainwright, but there are occasions when Wainwright has this material, the version in doesn't.
Very good to know. Thank you.
In fact, about the convergence that given in version in, and that is also given in that new book, actually, the new edition of Wsta, Tibshirani, and Wainwright. I think the chapter is written by Wainwright, and the proof is much, much simpler. It doesn't introduce too many new concepts, just like what Verschunen does in his book. They both give the posterior consistency of the lasso estimate. Consistency of the lasso estimators, but They're both very good books.
You are amazing, Mal. Your ability to stay on top of current literature is just astonishing.
Thank you.
And I know that Gauri Datta is online. Gauri, I'm going to apologize. I'm going to have to miss part of your talk, and I'm sorry about that.
No problem. Absolutely. Okay. Thank you. Good to see you.
It's good to see you too.
Thomas, I really like to know the trick, how you share the screen. I struggle.
Oh, Gauri, what I did, I just clicked that arrow which says present your entire screen.
Yeah.
And then that worked.
That's it. Okay. I'll try.
Try that.
Let's see.
Yeah, try that.
Okay, maybe I'll try it now. Let's see what happens.
Yeah, let's see.
Your entire screen. I see. Okay.
Yeah.
Google like to record. That's the problem. Open system.
Then you click on that screen, and I think at the bottom it should say share or something.
No, something else is going on here. That's the thing I don't understand.
But Gauri, what happens if you click on present your entire screen? What shows up?
Well, actually, it was asking for some settings, permission in the settings. I'm trying to do that. Let's see.
Oh, how come?
Well, it's
maybe somebody else has better knowledge on the technicalities here, because that's what I always do, and it works. Sometimes a different browser works for me.
Yeah.
I used Chrome, and I have no problems.
I'm using Chrome too, but I don't know. Let's see. Nope, it is share the entire screen, but it's not.
Why don't you email your talk to Dr. Satish
Can
Kumar?
share your screen. I already emailed the talk. I knew that.
So don't worry. If there is any difficulty, we can share from here.
Yeah.
It is already.
Yeah.
That's the best.
I didn't want.
Don't worry about that. You can share if you want to share. You have to go to the bottom arrow. Whether it is shared.
I tried. Maybe I'll follow Thomas's advice. Maybe I'll try another browser. Okay, and let's see if I succeed.
Yeah.
In that.
No, we have time, no problem. By this time, just to try, or otherwise we can share from here.
Yeah, I'm trying a different browser.
The bottom arrow, you can just click and enter screen. Then the share button.
I have to.
Before starting itself, you have to open the slides. That presentation.
Yeah.
And minimize or move to the.
Oh. Okay. Yeah. Let's see. Why? Not now. Let's see. Dr. Satish Kumar.
Yeah, Professor, we shall proceed.
So, let me see.
Yeah, don't worry, Professor. Let us present him from here.
Satish, I shall mail my slides to you for tomorrow in case I have similar problems.
Okay, Professor. Okay, Professor. Can do. Yeah.
Thank you.
My son Nikhil is with me. He will do support in all the way. Professor Pandit, whether joined, Sir Parameshwar Pandit. Professor, if Professor Parameshwar Pandit has agreed to chair the session, just 1 or 2 minutes, let us wait for him, whether he join or not. Otherwise, we can move to the session. Probably Professor Parameshwar Pandit has some network issues. Let us move to the session. Professor Parameshwar Pandit from Bangalore University has agreed to chair the session earlier, but probably there may be some network issues. I hope to let us move to the next session without wasting time. I think it will be better. We have two eminent speakers in this session, today's last session, in fact, in which Professor Gauri Shankar Datta is a professor of the Department of Statistics at University of Georgia and is a mathematical statistician at US Census Bureau. He earned his PhD in 1990 from University of Florida. His research interest is in Bayesian statistics, model-based inference in survey sampling, small area estimation, large sample theory, etc., etc. He serves in the editorial boards of several reputed international journals, including Journal of Royal Statistical Society. He is also an elected fellow of the American Statistical Association and the Institute of Mathematical Statistics. With due respect and great pleasure, let us invite Professor Datta to this webinar for his presentation. Shall I share it from here, his presentation, Professor? Please. Professor, please. Professor Gauri Datta, please. Excuse me, can you hear me?
I see Gauri in some other mode. I don't know what that is.
Okay. Oh, combining mode.
You might want to send him a chat or something. I don't know.
Okay. Let us wait, no problem. No, he's in the group, isn't it? Yes.
Let me try calling him. I have his phone number. I will try calling him, okay? Dr. Satish Kumar, you are muted.
Okay, Professor, please. Is it possible for you to call him?
Yeah, let me try calling him.
Okay, Professor.
Gauri, are you on or? Because we cannot hear anything. It says you are on companion mode or something. Yeah. Yeah. No, we cannot hear anything. We cannot hear you. No. You might want to go back to wherever you were initially when we could hear you. Yeah. You join again from. Yeah. Okay. All right. Okay. He will be back on, I think.
Okay, very good, Professor. Welcome. Thank you, Professor Thomas.
Okay, you're welcome. Yeah.
Can you hear me now? Hopefully.
Yes, we can.
Yes. Good.
Yeah, we can hear you, Professor. Yeah, please.
Okay, I was actually waiting. I could see the slides, but I could not hear anything anyway. So now I do not know. I mean,
you just direct next. Just to send next so that he will move the slides, Professor.
Okay, so we're ready to move. I'm going to start now, or
Professor. In fact, I have introduced the audience, Professor, just before. I don't know whether you heard the introduction.
No, I did not actually hear it. All right. Okay. Thank you very much for.
So once again, Professor, welcome to this.
For the kind invitation, it's good. All right. Last year also I presented a talk here, so this is really very good. And this year I'm making it's on a different kind of models, bringing in dependence among the random effects in small area estimation. And I changed that approach name. Previously I call it pseudo-based, and now I changed it to quasi-based. Somebody told me that pseudo is more pejorative than quasi. I don't know. I can ask David one day about that. So anyway, I changed that thing to quasi-Bayesian small area estimation using special random effects. And this is a joint work with my former student. He just graduated, Jia Cheng. And this is the work we are going to, and as part of Census Bureau and University of Georgia. So there is a disclaimer here. So can we move to the next slide? Thank you. Yeah, here is the standard disclaimer. So can we go to the next slide, please? Thank you. Okay, so thing is that some 12 years back, Jiang, Sunil Rao, and Tuan, they presented an alternative to the eBluff for small area estimation, and they call it observe-based prediction. And they actually had quite a bit general model, mixed effects model. But here we are going to specialize to the Feherian model, a very important model in small area estimation for summary statistics collected from various surveys using area level covariates. And what they said that their proposed method, overall based observe-based prediction, is more robust than eBluff, empirical based linear unbiased predictor, to model misspecifications. And they had uncertainty estimates, in small area estimation, the eBluff, a bulk of the research is actually estimating the mean square error. And most of the estimates of mean square error for eBluff actually proven to be asymptotically unbiased and non-negative also. However, that MSc estimator proposed by them actually underestimate or sometimes maybe negative, and consequently the prediction interval will undercover. So what we are doing here, we are looking at a Bayesian alternative to the OBP, and we are focusing on special random effects model. And this the Bayesian alternative is kind of easy to implement, and asymptotics not needed. And Bayesian, you measure uncertainty by posterior variance, so they are inherently positive, and you can create interval estimates based on quantiles of your simulation for the posterior distribution. And we did some simulations study and data example where show that special random effect models predict better than independent variant model if we do not have good covariance. Next slide, please. So here is this, I call this independent variant model. This model was introduced, by two census bureau statisticians, Bob Fay and Roger Harriet, in 1979 JASA article. So what we have, like for the small area, small area, the population characteristic is theta I, and you based on survey you get YI, direct survey estimate. It could be the mean or proportion based on Horwich-Thompson estimator, like that. And so we have that estimate. But sometimes the sample size for corresponding small areas may be small. And as a result, the coefficient of variation associated with YI might be large, and precluding the publication of such estimator. So in the smaller estimation, sometimes you have also covariates, and this population parameter theta I, maybe a big variability of that can be explained through covariates. So we have this linking model for theta I with these covariates, and the random effects VI are kind of in the variant model is IID normal, and the sampling error EIs are also normal, independently distributed, and sampling variance is known. And we have the vector of covariates. Typically, we also have an intercept parameter there. And beta is a vector of regression coefficients. So parameters are A, modular variance, and regression coefficient vector beta. And goal is to make prediction of the theta I's. Okay, next slide, please. Thank you. So, because we are estimating many similar components, theta I, so the Stein's estimation, based on sum of squared error loss, if we derive best predictor for theta I, assuming the model parameters beta and A known, then you have this shrinkage estimator theta I B tilde, the base predictor of theta I. So gamma I is di divided by di plus A. And for you need to estimate the parameters beta and A to make it useful. So EBLAP, you estimate beta and A by maximum likelihood estimators or certain method of moment estimators. And SAA literature extensively considered derivation of the mean square error of EBLAP and estimation of that MSC. So EBLAP is basically first you assume the model parameters known, get the best predictor of theta, and then also estimate the model parameters using best approach like MLE. So next slide, please. So Jiang et al. Argued that the EBLAP is less suitable for prediction of theta I, particularly for those areas where YI are less accurate. Because, in determining the model parameter estimates beta and A, that if you look at the maximum likelihood estimate of beta, you are giving much less weight to YI if its DI is very large. In other words, that less accurate estimator will have less say in determining the model parameters. And they argue that these are the small areas which will need more help from the model. And if you do that, then maybe they should also have a bigger say in estimating the model parameters. As a result, they said that instead of estimating the model parameters using maximum likelihood or the existing approaches in the eBlob, they said that we should look at the total mean squared error in predicting the small area by the best predictor, and you try to determine the model parameters by minimizing a sample version of this total sum mean squared error. So so please go to the next one. Thank you. And so, if you will make a little bit of simplification, what they came up with that to estimate the model parameters, basically, you look at this objective function, and that objective function has actually two components, okay? One is Q0, depending on both beta and A, and other is Q1, which depends only on A. And so, for given A, Q0 beta is a nice, positive definite quadratic form in terms of beta. You just minimize that thing, and you get an estimator of beta, but it depends on A. Then you plug that thing, then you have a function of A only, and you try to minimize that to estimate A, and together you get the best predictive estimator for beta and A, and you substitute that in the best predictor of theta, then you get what is called this overall best prediction of theta. So please go to the next slide. And so, here is this expression for the observed best best predictive estimator of beta 0 and then A, and you plug that thing, you get that theta I hat OBP. So please, next slide. So, if you look at it, the eBlob and OBP, in both the cases, actually, we are obtaining these things in two stages. First, we get the best predictor of theta I, which depends on the model parameters beta and A, and we get the best estimator from MLE or REML, like that. On the other hand, if we do hierarchical based prediction, we do that thing in two steps. First, generate psi from the posterior. Psi is the beta and A together. And then for the generated value of psi, we generate theta I from the conditional posterior of theta I. And typically we use a flat prior on psi, or we might use some other prior. And so basically hierarchical Bayesian methods, these steps mirror the eBlob steps. Whereas the eBlob and HB are similar, eBlobs and OBPs are very different. And the OBP diverges from eBlob through the estimation of psi by minimizing the objective function, which is very different from the negative log likelihood or log residual likelihood, which is negative L psi. And that is used in the Bayesian, hierarchical Bayesian method. So next slide, please. Here is actually just, for the smaller estimation of, this is, for from the 2000 census estimation of 4% family median income for the year 1999. And you see a map there, and in the map you see kind of from the color coding, that neighboring states actually they have kind of similar level of median income. So given that this spatial dependence, spatial similarity in the true mean, true because it's based on a much larger sample. So so there is some kind of spatial similarity there, and if we do not have some covariates to explain the similarity, that standards Fairriad model where we assume IID random effects might not be appropriate. May I have the next slide? Thank you. So so we are going to generalize this Fairriad model. So what we have is for the data Y, regression matrix X, and we have the random effects V and sampling error E. Sampling error as before, normal mean 0, variance square matrix D, and V is normal mean 0 and variance square matrix G. This kind of a general structure, and for this talk we are going to use special models variance covariance matrix. Next slide, please. So in the special model, we have an important matrix which is called the adjacency matrix W. Basically, you look at the different small areas. If they are neighbors, then we typically indicate it by the area I and j neighbors by using Wij equal to 1, and otherwise we say it 0, and by convention Wii, the diagonal element 0. So we have this M by M matrix, and we are going to have a few facts about this this matrix, which is used to define various special random effects distribution. Next slide, please. So the first thing is that matrix W is symmetric, and that means that eigenvalues will be real. And given the trace, because diagonals are 0, trace is 0, so smallest eigenvalue will be negative and largest eigenvalue will be positive, like that. And then we are defining a stochastic row stochastic matrix from W, basically dividing each row by the sum of the elements on that row, and then we get this W tilde matrix. And similarly, W tilde has the property that the eigenvalues are again between -1 and 1. Actually, the highest eigenvalue is 1, and it has at least one negative eigenvalue. So next slide, please. So based on this W and W tilde, we have actually 4 different special random effects model, and we are specifying this thing through the variance square matrix G, which is sigma square times G inverse is related to this precision matrices omega, various omega matrices 2, 3, 4, and 5, and omega 2 is corresponding to simultaneous autoregressive model, and it is defined through this W tilde matrix, the row row stochastic matrix. And simple conditional autoregressive model is defined through the adjacency matrix W, and conditional autoregressive is through L minus rho W, and then Leroux conditional autoregressive is defined through the precision matrix omega 5 R. And you know that R matrix is L minus W, which is actually a non-negative definite matrix. So, and for the Fayet model, that omega 1, we call it its identity. So we have 5 different models, and omega 1 is corresponding to the Fayet model. So next slide, please. So in general, if we define the B matrix, shrinkage coefficient matrix, D sigma inverse, sigma is the total variance of Y, then this is your best predictor of theta. And then following again this Jiang et al. And Rao and Molina, we can come up with an objective function Q beta delta Y, and delta involve A and the special parameter rho. And you know, as before, it has 2 components, Q0, which involves the beta and the variance parameters, and Q1 involves only the variance parameter and the special parameter. And we can minimize to get estimate of beta and estimate of delta, and we can get the OBP for the special models. Next slide, please. Now, we want to have a Bayesian alternative to the OBP, and I'm calling it quasi-Bayesian. Thing is that for the regular Bayes case, in the regular Bayes, basically we update the prior PDF, suppose it's a proper prior, for the parameter phi by multiplying by the PDF of the data, okay? So PDF of the data is giving you the information about the parameter. And this thing, you can write it like proportional means kind of an awkward looking thing I have in red. This exponent negative W SVD negative log pi phi star by pi phi. But SVD is nothing but the negative log likelihood. And W is equal to 1 is the right constant for the regular base. Now the thing is that negative log likelihood is like the penalty. Now instead of the likelihood, sometimes we have some kind of loss, like the loss we specified through that OBP. So now using this loss, if we have prior distribution on the parameters beta, A, and rho, how can we convert that prior in light of the loss given by Q0 beta A rho to get a posterior? Okay, that's basically this the approach. I'm going to follow the framework by Bishiri et al. In 2016 JRSSB. Basically, we have to calibrate the information that we get from the loss function and use that information to update a prior on the parameters. Next slide, please. In light of, given that I don't have much time, I cannot go over all these things. But important thing is that we have to get the appropriate scaling when we have a loss function L phi D, which is non-negative. We have to have a factor W positive, suitable constant, so that W times this loss and negative log pi phi, again, you take the log of the prior, which is like information, put a negative, like there are two different losses on the parameter, and they must be kind of in some way comparable. Okay, so Bishiri et al. Suggested that you solve for W from equation 10, and that's the thing we are going to do here by for this L, the loss function is through this Q function, and we specify various priors and we get the W, and then eventually we get the posterior, which we call quasi posterior. And basically the version of the L phi D we are getting, that will give us what is called a quasi likelihood. Next slide, please. For this loss function, this W0 came out to be for beta is this expression, which depends on A and rho, but it's otherwise it's a known quantity. And corresponding to that, if we use a multivariate normal prior on beta, and in the limit we make this multivariate normal very spread out so that it's like a improper prior, then the posterior, the pseudo posterior, is going to be a multivariate normal. Next slide, please. Now, once we have that, we are going to use that loss function for A and rho, which I call Q star, and we are using the rho, that special parameter, a uniform prior. And for A, we can use any prior, but in particular, we are using this prior d bar divided by A plus, like some Pareto kind of prior with scale parameter d bar. D bar is the average sampling variances. So with respect to that, we kind of we can calculate this this calibration coefficient W star, and it's a numerical value for the prior and for the model, and you have to do this calculation only once. And once you have that thing, then you get the pseudo or quasi posterior for A and rho is given by this equation 12. And now here the expression for Q star in terms of A and rho is not that complicated, and we can generate a sample from this posterior through rejection sampling fairly easily. And once we have these samples for A and rho, we can generate samples for beta, from multivariate normal, and then we can use this generate sample for beta and rho. We generate sample for theta from again the multivariate normal, and we have samples for the theta. We can make inference. Next slide, please. So we are going to talk about an application estimating this 4-person family median income for the year 1989, and we have the data from the current population survey in 1990, which is estimating the 1989 year income for 4-person family. The reason I'm using for the 1989 is that corresponding to the 1990 census, based on very large sample, we get estimate of this same quantity, and those are practically free from any sampling error, so they might be considered as the true values theta I that we are trying to estimate, and so that we can compare various estimates with the true, so-called truth coming from the 1990 census. And in doing that, we have two covariates. One is that the similar the quantity coming from the previous decennial census in 1980. However, those numbers for 10 years back kind of little bit outdated, so they are adjusted by using the per capita income published by the US Bureau of Economic Analysis. So we have two covariates, X1 and X2, and X2 is more effective than X1. Next slide, please. So, all right. So we exclude Alaska and Hawaii, and then we are going to estimate theta based on various models. So next slide, please. I cannot see anything actually. It's not. I hope you can see it, but I do not see these. It's not moving for me. So yeah, okay, all right. It moved quite a few actually. Anyway, we are talking about evaluating various models in the spatial models as well as the Fayharian models. So what we are doing, that as I said, CI 89, that's the 4-person family median income coming from the 1990 census, which is kind of treated like the ground truth, and theta I had is the estimator of the theta I based on various models, and we are looking at over a set of areas. We are just evaluating. This is a mean square prediction error, kind of empirical, and also we are looking at the average posterior standard deviation. Next slide, please. So we compared actually these 5 models. The first one is Fayharian independent, and then we have the simultaneous autoregressive and simple conditional regressive, and Lerukar model. And when we have all the covariates in the model, and you can see that that the Fayharian model is really competitive in terms of the mean square prediction error and in terms of average posterior standard deviation. So it really does not make sense to include any of these spatial models. And also, as I mentioned, that the X2, the covariate is a very good covariate. And so when you use this covariate X2, in that case, also you see that Fayharian model is at least as competitive as the other spatial run-of-a model. The last column, last block actually, I say that if we did not have access to the better covariate, the strong covariate X2, if we had only access to the covariate X1, which I call weak covariate, in that case, I can see that the random effects model based on the Fayharian independent model is doing much worse compared to the spatial random effects model in terms of MSP and APST. So
what is the recurring theme of this data analysis and simulation is that if we do not have effective covariates accounting for special pattern in the population characteristics of the small areas that we are trying to estimate, in that case we can gain significantly by using one of these special random effect models. But if we have good covariates, we really do not do better than the standard variant model. Next slide, please. What we are doing here, we are also estimating non-sample statements. So you know that for the standard variant model, sometimes in smaller estimation, you cannot really plan all the small areas. Sometimes you have unplanned domains, and for those cases you have no direct estimates. For the standard variant model, that estimator is simply the synthetic regression estimator. But for if you have the special random model, you actually update the synthetic estimator for the variate by using the residuals for the neighboring small areas. Next slide, please. So we are just comparing the special models. We are looking at this MSP ratio and the average posterior standard deviation ratio.
Professor,
yeah.
Professor, 5 more minutes you can take, Professor.
5 more minutes, right? Yeah, okay, all right, okay. That's fine. So please go to the next slide. So these numbers, smaller the numbers, less than 1 means that the special models are better than the independent variant model, and larger than 1 means the special models are less effective than the independent variant model. So if we look at the first, so we created actually from this median income like 12 different data sets, arbitrarily removing some states. We did not use their CPS estimates in model fitting and prediction. So if we have the better covariate in the model, you can see that most of the numbers are actually bigger than 1. And overall average in the last row corresponding to the first block is close to 1. That means that by using special model for the random effects, we do not gain. But if we go to the second half of this table, corresponding to the weak covariate, most of the numbers are actually smaller than 1, and overall average is actually less than like 0.5 or maybe like 0.6. Basically, that by doing the special random effects model, you are coming up with better prediction than this independent variate model. Next slide, please. The same comparison in terms of the posterior standard deviation. Again, you can see that for the first half of the table, this overall average is like close to 1. That means you do not gain much. But if you go to the second half of the table, you see that these numbers are less than 1. It could be between 15% and 35%, something like that. So by doing the special random effects model, you are actually improving over the independent variate model. Next slide, please. And we are doing a simulation. What do we have? We have 2 covariates, X1 and X2, generated from a special pattern, and based on those we define the regression function mu, and then we generate theta based on the regression function. But thetas, they have independence, but you know that there is a special pattern in the theta through the special pattern introduced by the mu, and then we generate y. So next slide, please. So there is a special dependence in the theta. Next slide, please. So what we have here, we are showing it that if we use the strong covariate in terms of mean square prediction error, average posterior standard deviation, we can see that
all these 5 models are kind of comparable. On the other hand, if we go to the second half of the table, based on if we fit the model only using the weak covariate, then we can see that because there was a special pattern in the theta through the simulation, we can see that all the special models are actually producing more accurate estimate compared to the independent covariate. And that is also true for both the criteria, MSPE and average posterior standard deviation. Next slide, please. So, this is for the unsampled areas. Basically in the model fitting, we are not using some of the states, and we are just doing that. So next slide, please. So, again, what we have for the non-sample areas, we are just doing this prediction in terms of the average mean square prediction error. And if you look at here, if you have the strong covariate for the unsampled states and sample states, you see that it's not a significant improvement. But if you have the weak covariate, if you go to the second half of the table, you see that the ratio for the mean square prediction error for the sample states is like maximum like 0.89, and for the unsampled states it's like 0.96, or sometimes maybe like between 5 and 15% or 14% you are improving by doing this special random effects model. Next slide, please. And it is doing the same thing in terms of the average posterior standard deviation. And again, we see that if we use weak covariate, we gain by using the special random effects model. It's particularly for the unsampled states, which is the very last column. Next slide, please. Okay. So this is basically some final remarks here. That what we did, we created a Bayesian version of the OBP method, okay, which I call quasi-Bayesian, because for estimating the model parameters, I did not use the likelihood. If I had used the likelihood, then we had the full Bayesian. I mimicked the Jiang et al.'s method. I used their loss function, which they minimize, to estimate the model parameters of the small area. I used that thing to come up with a comparable quasi-likelihood for the model parameters, and use default priors for the model parameters to come up with a quasi-Bayesian version following the approach, the paradigm suggested by BCD, Walker, and others. And we actually generalized our Bayesian special method in Chang and Data paper. And in this case, it's straightforward to create reliable measures of uncertainty, unlike the OBP, where you have to estimate, approximate the mean square prediction error. Here you are doing it by generating sample from the posterior distribution, and you can use these things to create credible intervals as well. And so we evaluated the proposed method based on the actual data analysis and by simulation, and the method is quite competitive. And the method also enjoys it's a dual interpretation of Bayesian and frequentist, because frequentist properties I show by a simulation, and the method is created through a Bayesian argument, a quasi-Bayesian argument. So it's an important model. I think there might be one more slide, or that's the last one.
This much,
okay. That might be the last one. Okay. Thank you.
Yeah. Thank you, Professor Gauri Datta, for your
nice presentation. I hope anyone needs any clarifications. One can be permitted for the time being because we are a little bit late. Yeah, Professor Malay.
Yeah, Gauri.
Yeah, thank you.
What do? You possibly do both, right?
I could not hear your question.
Given situation, can you hear me?
Now, yeah, please.
Yeah, in a given situation, when you have covariates, okay?
Yeah.
You can use possibly both and decide on the basis of, is that the message?
The message is basically, it has been.
You never know, weak or strong.
Yeah, that's right. Yeah, if you do not have good covariates, sometimes you may not have covariates. In such case, you gain by using special random-based model.
Sure.
But if you have effective covariates, then there is not much to gain by using the special random-based model. That's the message.
Yeah. So in a given situation, you will do possibly both, right?
You can do that thing, if you look at the penalty for using the special models, is at least for these models, you have just one additional parameters, and model fitting is actually not that complicated. However, because of one additional parameter, maybe you will have to spend some information, and that might be the reason for, you see that average posterior standard deviation for the failed model coming out to be smaller than that thing corresponding to the special random-based model. So you can do both, but if you have good covariates, there is no need to use any special modeling.
I understand. Yeah.
If you do not have any covariate, then you use that.
Yeah. So maybe some, yeah. Well.
Oh, okay, Professor. Anything more to add, Professor? Professor David Banks has anything to?
I would like to read the paper, Gauri. Where is it coming out?
Oh, that I'll email you that one. There is this special issue in Calcutta Statistical Association Bulletin. Okay.
Oh.
So.
Okay.
Yeah.
I'll email you it.
Yeah, I'll send you. We're working on the revision. It will be done maybe in a day or two. Okay. I'll send it.
Excellent. Thank you.
Great. Thank you, Professor. Thank you. Now, let us give a big clap to Professor Datta for his excellent presentation.
Thank you.
Now, let us move to the next speaker, Professor Kibriya. Professor B.M. Ghulam Kibriya is a professor in the Department of Mathematics and Statistics of Florida International University. He taught at University of British Columbia and University of Western Ontario, Canada, and several other places as well. In fact, he's a very active researcher, working in several areas: applied statistics, biostatistics, computational statistics, distribution theory, environmental statistics, etc. And he has more than 250 research articles, and also he has guided several masters as well as PhD students, and he has several credits, several awards also he has. I'm not going to the details because of the time short. All those things are available online. He's a member of, in fact, he's an editor-in-chief of the Journal of Probability and Statistical Science, and editorial board member of several international journals, including Communications in Statistics. And he's also the elected fellow of Royal Statistical Society and recipient of the honorary doctorate at John Hopkins University, Sweden. And he has been listed the top 12% scientists category by the compiled by the Stanford University, and several others. With great pleasure, I utilize this occasion to invite Professor Kibria to this gathering. For we are all waiting for your nice presentation.
Okay, Dr. Kumar, thank you so much for your nice introduction. Can you hear me?
We can hear you.
Okay, so I am going to share the screen. So I don't know whether you can see my screen.
It is it is coming, but you can make it full screen if possible. Okay.
How about
okay,
now?
It is fine.
Thank you so much for invitation and remembering me. I was here last time also probably. So my talk will be on some modified statistics for testing the population signal to noise ratio. This is one of the area I work, but my main research is on linear modeling and distribution theory. But sometimes I do some kind of simulation study. This is the work with one of my student and colleague. They are hopefully here. So further ado, let us start the presentation. So first I'll introduce about the topics of this talk. Then we'll have some objective, literature review, simulation, and conclusion. Introduction. About the SNR, the Pearson first introduced the coefficient of variation, which is a dimensionless measure of variability related to the mean. And the population CV is, as you see, which is sigma by mu. And SNR, which is the title of my talk today, SNR. So SNR is the reverse of the CV. And the ratio compares the level of desired signal to the level of background noise, or more refined, it is a measure of the magnitude of data set relative to the standard deviation. And in reality, about the coefficient of variation, there is a lot of literature review, especially for the hypothesis testing and confidence interval, because these are the parameters, eventually you're going to estimate them. So there is a lot of literature on CV, but very few are on the SNR. But this paper is talking about the SNR. The SNR, or signal to noise ratio, has been applied in many fields such as quality control, image processing, medicine, and business. In quality control, the SNR expresses the degree of predictability of the performance of a product process in the presence of noise. Kapoor and Chen 1988. In image processing, the SNR of an image is usually computed as the ratio of mean pixel value to the standard deviation of the pixel value over a given neighborhood. In medicine, specifically magnetic resonance imaging, it has a lot of use. In business, to improve the service quality in the hotel business using collective quality function deployment and SNR, they have some application over there. So a high SNR means that the signal strength is stronger in relation to the noise level. Having higher SNR means there is more useful information than unwanted noise. This can also be seen when putting SNR into practice. The larger the standard deviation, the smaller the noise. In literature, there are various methods available for estimating coefficient of variation, such as parametric, non-parametric, modified, bootstrapping a lot. Now, idea is here, since SNR is the reciprocal of CV, we can use all methods or some of them from CV to make inference about the SNR. That is the basic part we did here, and mostly based on our paper. What is the objective? The literature on testing the population SNR is limited. Very few people has done, maybe 3 or 4 papers, including our paper. So in this presentation, we have 15 different test procedures. All are approximate, most of them. These tests are developed based on the confidence interval, because, when you have the confidence interval, we reject null hypothesis when go above or below the confidence limit. I'll explain later why I'm using CI. Since theoretical comparison is not possible, we do a simulation study here, and considering both empirical power and power of the test, empirical size and power of the test, we'll compare them. So the main objective is to find some appropriate method for the practitioner. So what is the population SNR? Suppose I have a random sample of size n, so you can estimate SNR by x over s, which is reciprocal of CV. Later on, since the literature on CV are available, we can use that information to make the inverse for the SNR. So our objective to test this hypothesis, SNR is equal to some specific value. Now we have this following available method. Basically, Kibri and George, they review all of the previous method, and all of them did for CV, the coefficient of variation and confidence interval. So we make them CI for SNR, and that paper was published. In this work, we have some new modification of this 4. So total 15 test procedure for testing population SNR. So I'm explaining 1 or 2 and remaining will be followed. So Miller, 1991, he showed that for large sample size, the S over X bar, which is sample SNR, has a normal distribution with mean and variance of this. So immediately you can find the confidence interval for the population SNR. So we'll be rejecting anything below than that number or anything bigger than that number. So we'll use a 2 limit, upper and lower. Reject something above the upper limit and something below the lower limit. Sharma Krishna developed asymptotic sampling distribution of the inverse of the coefficient of variation. So from this inverse coefficient of variance, we found the lower and upper limit and used them as a critical value for our test procedure. Now, Carto and Pinto using normal approximation for the CV, which is basically inverse of SNR, and they have different kind of upper and lower limit. And then Mackey in 1932, he has a interval approximate distribution of the CV. From the CV, he found the interval, and from the interval, we found the SNR. And this method has a problem, like this term, chi-square n minus 1 alpha by 2 by n, something could be less than 1. Then you cannot find the square root. So what they did in the next method, which is modified Mackey. Modified Mackey method was considered by Engel. He just add 2 points. So the simulation study, he found that then it become positive number. So there's another method you can consider. Now, by the way, these are all methods from the CV, so we convert them to SNR. And that is Panikitkos Gulkul, 2009. He modified Mackey method using a constant K, which is function of sample data. And he found interval for CV, and we convert to the SNR. Now, yeah. Here in Cuvier Florence 2014, what he did, in the previous method is all where you have the standard deviation. This is the standard regular standard deviation, which is 1 over n over sum of like standard deviation in terms of X bar. What we did here, I showed in 2006 that when data are skewed, the sample standard deviation perform worse compared to if I define my standard deviation in terms of median. So what I did, I modified standard deviation. Instead of making X bar, I used the X, median of X. So I did a simulation, and I showed a couple of table and showed that statistically when data right is skewed, median in terms of standard deviation perform better than the mean. So based on this concept, we modify the Miller method. Method we call here method number basically 8. Then we did Same thing for modified McKay. And 2014, what we did, we found the exact, we know the exact CI for the sigma square is this, standard known in any book here. Then I found for inverse of 1/sigma square, and we multiply both sides by mu square, we find the exact estimate for normal distribution. And we showed some simulation, it was doing perfectly, really good. And then we modify other stuff with this modified SNR. Here, modified SNR means standard deviation in terms of the median, not the mean. Now, Kibria and George modified Sharma-Krishna method using bootstrap technique, which is computationally expensive and time-consuming, and did not improve that much. So what we did, since this performed the best among previous 10, and their critical value come from bootstrap sample. So we say bootstrap is time consuming. Why don't modify this stuff, the Sharma-Krishna, using modified MAD, mean absolute deviation, and other method that showing here. So we can modify George and Kibria using SNR. This SNR based on the median, not the mean. Similarly, standard deviation used by MAD, which is little bit modified, that Rosens and Crocs, they put here median, we put the mean. Similarly, Sharma-Krishna method, we modified the modified MAD 14. Another one we did like using the modified standard deviation. So basically, we modified this further with modified standard deviation. So now all of this method approximate, and it is not easy to know way to compare them theoretically. So we have to go for the simulation. But for simulation, we check for all small to large sample size 15 to 100. In fact, we should do more because of sometimes data is very skewed. Repeating 5,000 times. So we like to find the empirical power and size and see which method give us level 0.05, close to 0.05, but high power. So empirical level should be corrected first, then the power. So we generate that from normal distribution using SNR1. So that means in normal case, mean is mu, sigma is 5, so SNR will become 1. We generate data. So when SNR1, this column will give us our desired nominal level. And you can see except method 2 and purpose, all are fine, close to 0.05. And since simulating 50,000 times, level 0.05 means you can go until 0.06 or 0.07. And you can see the method 10 is still performing really better than others. This one is doing high power, but level is not close to 0.05, so you cannot accept it. Then normal distribution sample size large. When sample size large, it give the same result. It didn't change that much, but power improved. As per sample size large, power should be larger. It is improving, but level also getting better. So those has consistent power with level 0.05, as I said here, number 1, 3, 4, 5, 6, 7, 8 until 10. Those are showing here. And these are basically unstable, so we cannot believe that. But some of them good, but upper tail test basically. Here I am showing 2 tail test. The normal distribution SNR is 5, and you can see now SNR 5 means I am going for this column, and the proposed method 12 give really good nominal size, except method 2 and 13. Method 12 is really doing good, but power is reasonable also good. But method 10 is performing the best in both sides. You see, 0.47, and method 12 is good, not as good as number 10. For normal distribution, same characteristics. Now, it's number 5. No. Normal case, as I say, now when data from right skew distribution, gamma distribution, and sample size 30, and you can see again method 1 to 10 all attain the nominal level 0.05, but method 10 perform only method 2 performing well in both tail of the critical value. You see, so in this case, method 2 is better than others when that is right skewed and nominal 1. And also method 13 is alpha is 0.08, little bit bigger, but not that big, but giving the good power. Sample size 100, our power goes up in both sides, and level become 0.05 or below, and method 13 is level 0.07 or 0.08. I mean, it is not that bad. So this is my graph for gamma distribution. When SNR 2, the performance change, like all method 1 to method when the 11, all attaining level 0.05. But power, if you see, method 10 for both sides is very high. But method 12 is high power, but since level is not close to 0.05, we cannot accept it. Again, it's almost same for SNR 2, sample size large. We have more power both sides because sample size is large, and level become very close to 0.05 until method 11 in a close to. And so large even the large sample size, when data from gamma, method 12, 13, 14 does not improve that much. So this is the graph for 100. Gamma, when my SNR is 5 and the sample size 100, method 12 is performing well. It's close to other 0.05. And power is also both sides is high. And this level, you see, method 12 proposed one when SNR is really 5, but high. In fact, when SNR goes up further more 10, proposed method perform better. This is the graph. Now, this is the beta distribution. I am looking some data from left skew distribution. It is hard to generate, but beta is only distribution like available in R, and we use every day almost. So we use from beta distribution with the skewness, I think something 0.67 or less. And you see all method except 2 and 11 to when SNR is 2. Method 2, 10 is performing best. This method was proposed before with based on only normal distribution in Kibri and George, but this is under the left skew. Still they're doing good. Then I was trying to do a simulation today, like if SNR is smaller SNR I'm testing 0.5, and you see the all method, the proposed method perform really well when you are testing for SNR less than, here I am testing SNR 0.5. And method 15 is the best. I did other simulation I didn't show here for smaller testing for smaller SNR. So I am showing here one application, not 1 or 2. Here you consider the failure time data from ARSET, the 50 failure time data. And we plot them. It looks like uniform. Then we did case goodness of fit test and p value 0.30. And estimated parameter alpha is 0.1, beta is this. So we assume this is a possible population SNR from the data, but assuming. So then I find the lower and upper limit. So we found that the 1.73 is in all of them except method 12 and why I cannot show you. No. No. Okay. You see, 1.73, 1.05 is captured by every methods. But we know that when SNR is 1, method 2 and method 6 to 8 was not working well. So what it is? Okay. So conclusion, we consider 15 different test statistics existing and proposed for testing the population SNR. A Monte Carlo simulation study has been conducted to compare the performance of the test statistics. We make them empirical power and size to compare them. And from the simulation study, we found that method 1, 3, 4, 5 to 10, 12 to 15 performing well, especially when SNR is small. But method 10 was performing the best in all scenarios. What is the limitation? The conclusion of this research restricted to the given simulation condition of the paper. For a definite statement on might need more simulation condition and more sample size and do a simulation under various distribution condition. Now, another thing is you consider approximate distribution for most of the test statistics. It might be interesting if to find the sampling distribution for the test statistics under different distribution assumption and match your level and then compare the power. Thank you.
Thank you, Professor Kibriya, for your very nice presentation, and it's quite interesting. And I hope someone may have may need some clarifications. Or
yeah, please feel free to ask me. I did quick because I thought we can talk more after the talk.
Yeah.
This is
typical. If there is anyone,
not like critical one.
Yeah. Yeah, I think Professor Devendra Kumar, do you have anything to mention?
No, sir.
Okay. Anyone else?
This is the easiest talk. You must have a question.
Yeah.
I don't know why.
Yeah.
You know, I didn't talk some math, no math at all.
I hope several questions probably, but they will contact you, Professor, via online in future.
Okay.
If anyone else will awake, let us wait 1 or 2 minutes because we have to wind up at 9. Yeah.
So I'm stopping sharing or?
Yeah, whether okay, Professor. Okay.
You have a chat message anyway.
Huh? Oh.
You have a chat message.
Dr. Kumar, Florence George, she is our colleague and she is from Kerala.
We cannot hear you, sir.
Dr. Kumar, you are on mute.
Sorry. Mute, just mute.
I'm alumni from Kerala University. I'm from Kerala University.
Great. Okay, Professor. Yeah. You are most welcome to the conference. In fact, I think you last year you mentioned something, isn't it?
Yeah.
And you studied in the computer science department, isn't it?
Yes. Yeah.
I remember. You can also join with us the conference. Some presentations.
This work was with her also. Now we have remembered two more contributing talk, but that time I have to talk to you. It is like midnight in Miami.
Okay, Professor. Okay. Yeah, I hope that's fine. You can organize a session itself with these people in future.
Sure. It's always pleasure to see you, at least from the doom. We don't have to go there.
Okay. Let us give a big clap to Professor Kibria for his nice talk. And also, we are very much the last session from Professor Gauri Datta as well as Professor Kibria. We have very good presentations. And
thank you so much.
Thank you, Professor. Thank you, Professor. I hope everyone can join tomorrow. Let us wind up now today's talks. Join tomorrow early morning, I think by 8:30 itself, or 8:30 to 9. At 9, Professor Daddy's talk. We can start with Professor Daddy's talk. WCR now. Thank you so much, Professor. Thank you. Thank you all.
Okay. Take care.
Bye.
Bye.
Thank you, sir. Thank you. Bye.
Thank you. Bye, Professor Devendra Kumar.